Embark on a digital odyssey through the cloud cosmos with our comprehensive course on Google Cloud Storage. Picture yourself as a cloud navigator, charting a course through the vast expanse of data storage options. In this course, I'll select the perfect storage class as if choosing the right gear for a space mission, ensuring efficiency and cost effectiveness. Discover how to strategically choose bucket locations akin to picking the best planets for establishing colonies, optimizing for latency and compliance. Then, I'll encounter how to configure storage settings with the precision of a spacecraft engineer, managing object lifecycles, secure objects with access control. Then, I'll transition to exploring Google Persistent Disk and Google File Store. Finally, I'll navigate through the pricing of Google Cloud Storage. By the end of this course, you'll be adept at utilizing Google Cloud Storage solution, ready to tackle the universe of data with confidence and skill. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, I'm going to be discussing the type of Google Cloud services that are used to store unstructured data. Let's first get started with understanding what exactly is unstructured data and the types that come in it. So, unstructured data just refers to information that doesn't fit into a tabular format. So this could include things like images, videos, audio files, documents, and content of general, other content formats such as social media posts, emails, web pages, really any data that doesn't conform to this rigid structure. So when we think about these types of files, we're really just referring to unstructured data. So then the concept then becomes is, well, if we're not storing them in tables, how exactly do we store them? Well, this is the essence of what object storage is. Objects being a file, so it'll manage data as discrete units called objects, so we could have a single audio file, a single video, a single image, those kind of things. These objects typically consist of the actual data and its associated metadata, things like the file size, the file name, those kind of information about the object itself is attached to it. And this is where you'll see it saved generically as this unstructured object. And the format really just refers to it's unstructured. So it'll handle large volumes of this unstructured data accessed over an entire network. So this is really important because not only are we just storing this somewhere on a machine, but we're actually putting this over an entire network can access it. And it scales very well so that it can handle very large volumes of data. Now, these use cases can include things like scenarios where data needs to be accessed remotely over a network. You can have commonly used for storing large volumes of unstructured data, such as multimedia files like videos and images and audio files, or you could use them as backups or log files. The interesting thing about this, though, is that it's completely scalable, durable, and it's metadata enriched. So scalable in the sense that it can handle massive amounts of data, durable in the sense that data is redundantly stored across multiple locations. So if one location goes down, no problem. We have it in another location that we can retrieve from. And the metadata allows efficient organization and search and retrieval based on this metadata attribute. Now this is where we'll get an example here where we'll talk about as Google Cloud Storage, which is just object storage for unstructured data that's totally scalable on the Google Cloud platform, and that's a service that we can actually use. Another thing that I want to discuss is the concept of block storage. Now, block storage divides data, such as files or database entries, into blocks of equal sizes. Now, a block is just a space in memory, and these blocks are then stored on underlying physical storage. So storage that divides data into blocks of equal size is known as our block storage. You'll also see that in our format, we'll have structured data that's divided into fixed size blocks. And what happens is that we can actually put this in random and fast access, such as for databases and virtual machines. And this is where we want to use these things. So if I'm trying to attach storage to a virtual machine, I would use this. If I'm trying to attach storage to a database, I'd use block storage. These are the things that make us persistent storage in cloud-based VMs as offered by block storage, so that if the machine goes down, no problem, it still remembers its information, it's persistent. And the interesting thing about this is that it's performance optimized for fast access and retrieval. and it has predictable latency so that it's consistent performance for read and write operations. And that's the important thing here, is that we want to be able to consistently access and write to this system. Now, here are some examples that are available on the Google Cloud. Things like persistent disk and local solid-state drives are all examples of block storage. So the next thing I want to talk about is known as file storage. Now, file storage refers to the servers and applications with access to data through shared file systems. And this provides servers and applications so that we can actually access them throughout an entire network. The format here is that it's organized into files and directories, similar to what you'd see in like a Linux operating system. The use cases here allows us for requiring shared access to files, such as collaborative workloads or content management systems. And it's often used for home directories or application code and shared resources. And you'll notice that there are a few different advantages that it's offered. One, it's very versatile and easy to use. And because of its ease of use, it has a familiar file system structure, so it makes it very easy for anyone just to pick up and run with. No need for any complicated programming languages. An example of this is known as the Google Cloud File Store. Now, another one that's really important is known as memory storage. Now, this provides several memory cache storage options to enhance performance and data access speeds. These memory services are just meant for us to provide fast caching solutions. Think of them as key value pairs in RAM. And you'll notice that we're going to be using this thing known as transient cached content. This is where we can use things like, for example, memory store, which is using Redis and Memcache, where we have sub-millisecond data access. It's very scalable and highly available. And this service is the focus for its integration with data warehousing needs, because it's very important for us to actually read and write very fast, and we can actually store this in memory somewhere, and this is where the transient cache content is used. You'll also see, because of its very low latency retrieval, it's used to remember pieces of data that are static, that they don't change very often, like a lookup table, for example, that doesn't really change. We'll usually put that somewhere in a very low latency retrieval system, such as Memcache or Redis, so that we can actually get this information. And this is what you'll also notice is when we start using things like CDNs, it actually will integrate with memory storage, and it uses globally distributed edge points to load this balanced content because it's in memory storage there. And those are just some of the use cases for actually using memory storage, and there's quite a few different ones that we could talk about. But these are basically the pieces and types of data that are used for unstructured data in Google Cloud. In this video, we're going to list the benefits and the parameters that are associated with Google Cloud Storage. Take a look at something here. With Google Cloud Storage, all this does is it provides a simple, secure, scalable, and globally accessible solution for storing and managing our data. Think of this as like a data warehouse where I can store digital stuff such as images, videos, documents, files, those kind of things. It's almost like a way for us to keep our things just safe, organized, and just easily accessible. And this is the essence of what Google Storage is. It's a lot like a Google Drive account that you have on your regular Google account, where you can actually store files in that Google Drive and pull information out, and there's some folders and structure that you've got to organize your things. This is exactly what Google Cloud Storage is doing. So there's different components inside of a Google Cloud Storage. So the first one is our objects. Now this is just represents an immutable piece of data, such as a file, and it could be in any format and could represent anything. And these objects are unpredictable by their nature, and they're unstructured because they don't really follow a source like a table, tabular format, right? So that we refer to things like images and videos as unstructured data. Now, the objects live in these systems called buckets, and this is the fundamental storage unit. They act as our containers for these objects. So each object is globally unique, and it has a name that's globally unique and is associated with a specific project. Now what I can do is I can create multiple buckets within my project so that I can organize the data. So maybe I'll have a bucket that's just for videos, a bucket that's just for images, a bucket that's just for documents, those kind of things. And so what I want to think of is each bucket has a unique name that's associated with it, like a labeled box on a shelf that you might see. And then this is what we're trying to do here, is store the right objects in a certain bucket so that we can organize it in some way, so that we can easily search for it or access it later on. And the Google Cloud Storage hierarchy starts at the very top with the organization. This is where I'll have like my company name, and so it can have multiple projects associated with this organization. So maybe each project represents a product for this organization. So I'll have projects underneath it. So it'll be a specific application or a use case. And these projects will contain resources just like our buckets or virtual machines or APIs or Kubernetes clusters. Really just any service is now associated with that project. Now within that project, like I said, we could have a managed folders that are there. And this is where we can have a system of buckets that can contain managed folders, and they allow additional access control for objects within a shared name prefix. So this will be animals would be a folder, and that would live inside of a bucket. Now what I'll do here is I'll have buckets as well. A bucket is within our project. I can create buckets to store your objects, and so buckets are identified by the unique names like I was saying before. And then at the very final step, we've got the objects that could live inside of a managed folder. And these objects contain these individual objects, such as files and videos and images, and they could be PNG files, JPEG. It doesn't really matter what format they're in, so long as they're indivisible files. And we refer to these as objects inside of this Google Cloud Storage. Now, there's different types of Google Cloud Storage that I want to discuss. The first one is known as public cloud storage. And this just means that we're sharing a storage unit with other developers, right? So it's like a big public closet or a big public container where everyone can keep their things. So not just people from my organization, but people from other organizations, and they are paying for these shared uses. So you pay based on how much space you use in this container. Another one is, imagine if we had data that's super sensitive and we don't want to have it stored on the same publicly accessible system as another organization can access. So what we'll do is that we'll actually use a private cloud storage. And this is like having our own private storage room where we only have one key and we can get in and out through that key. And so you only have this key and it's super secure. No other organizations can access it. And so this is useful if you need extra control, and people will use these things if they're trying to be some type of compliance measure, such as HIPAA. And there's hybrid cloud storage as well, which is just kind of a mix of both. So I can have a shared container and a private container, and I'll put the really sensitive things in this private container and put the not so sensitive things in the public container. Usually the public cloud storage is cheaper than the private cloud storage, so it's a way just for us to minimize cost. Now, how do we interact with Google Cloud Storage? Well, the first thing that we have is, of course, the Google Cloud Console. We can log on to the web, log in with our Google account, and then access the Google Cloud Storage service. And through the console, we can upload files, download files, create new folders, subdirectories. Really anything can be done through there. However, we also have access to the command line interface, or the gcloud CLI. And with just a couple of Linux commands, we can actually create buckets. We can create folders, upload objects, download objects, maybe change some permissions. And that can also be done with the gcloud CLI. But it's not just limited to the Google Cloud Console or the Google Cloud CLI. It also has client libraries. This is where I can use client libraries in languages like C++ or Java or Python. And these are all ways for me to actually use these SDKs within that programming language to download files and upload files, change permissions, delete files, create buckets. That can all be done through a programming language and a script, like a Python script. And then finally, we have the REST APIs, where I can manage data using the JSON or XML API, where I can just authenticate with an endpoint, send in my request, either a post request, GET request, that kind of thing. And I can just call the API directly to do a certain action, and I can do it through there. And that's useful if I'm trying to do like a webhook kind of interface. So that is a little bit about Google Cloud Storage, its components, and the hierarchy of Google Cloud Storage terms. In this video, we're going to choose some storage classes. We're going to describe some of the ramifications of choosing a specific class for Google Cloud Storage. Let's start with the Google Cloud Storage classes. So what is a storage class? Well, the storage classes will just determine availability and pricing within our Google Cloud Storage account. Now this will offer different types of storage, and think of them as containers for our data, depending on how often you need to access it and the budget that we're working with. So it's just, think of a storage class as just like a piece of metadata that's used by every single object. So storage class is assigned per object through this metadata, and these storage classes are inherited by default. So if I don't specify a default storage class when I create a bucket, the bucket's default storage class is set to standard storage. And there's different types of classes, and they'll have different ramifications on what we want to, how we access our data, for example, or how the data is stored, and the cost, and all these things. So we have to choose the storage class that is going to match up to our business use case that we're trying to use. So let's talk about the first storage class that's there. This is the first type of closet or container that's offered, and this is known as the standard storage. This is like our everyday container, our everyday closet. So we'll have things like high availability, and it's easy to access, and you keep your frequently used information there. It's always available and reliable, and so this is very good for this high availability step. You'll also see that it has very low latency as well, so it's great if we were trying to frequently retrieve information for an application. But there is a bit of an issue that we want to talk about. It's that there's a high cost. The cost for this is actually quite high compared to some of the other storage models. So you have to understand that, yes, you are getting low latency. Yes, you are getting high availability, but there's a cost for everything. And this is where you have to sort of weigh the cons of, is this worth it? Do I need this information highly available and with very low latency? Am I going to be accessing it very frequently? And so the thing that also you should know is that there's no minimum storage duration or retrieval fees. So this refers to, when I talk about minimum storage duration, what I'm talking about here is the shortest period of time that the data must remain stored in a particular storage class. So there's no fee like that that's available, but it is very durable. 99.99999% annual durability is what it is. So essentially 100% durability. So there's nearline storage as well that I want to discuss. So for infrequently accessed data at lower cost than our standard storage, this is great for this. This is like a storage unit where you store your things, but you don't need every single day. So you wouldn't keep it in your house. You'd maybe put it in a storage locker across town. This is what you'd use it for. So it's something that you go through every 6 months. That's an example, right? So for infrequently accessed data, you'd store it there. And so the thing here is that it has good availability with modest latency. Again, it's not as good as our standard storage, but it's still pretty modest. You can get the information relatively quick. And then there's these 30-day minimum storage duration and retrieval fee. So you can pull it out before that duration, but you will be charged for doing that. So whatever needs to go in there needs to stay there for at least 30 days before you have to retrieve it. So think about that before you actually store information in there. Am I going to need this within the next 30 days? If you do, nearline storage is not for you. Maybe you should put it somewhere else. Another thing that you'd want to look into, and this is the second longest one, is called cold line storage. Think of this as your basement or your attic where you keep stuff that you rarely use in your home. This is what cold line storage is for. It's very affordable. It's great for long-term, rarely accessed archival storage at an even lower base cost than the ones that we've talked about before. We have things like the high latency, but still highly available. So it does take some time to retrieve information from it, but you do get this high availability with your data. But there is a 90-day minimum storage duration and higher retrieval fees if you store information there and then have to retrieve it within those 90 days. So think about that. Am I going to need this information within the next 90 days? If you do, stay away from cold line storage. Another thing that I want to discuss here is called archive storage. Now, this is the lowest cost, but long-term archival storage. It's the lowest you can do. There's a bit of a catch though, okay? This is like a vault where you store precious items, but you will never, barely ever touch them. So this is the cheapest option, but requires planning ahead for your retrieval. And here's the thing, it has microsecond latency and high availability. So that's really good for what we're trying to do here. It's very quick, very fast to retrieve, but there's a trick here for this, is that there's a 365-day minimum storage duration and highest retrieval fees are associated with this storage class. So this means if you're going to store an object in this archive storage format, there's a bit of an issue. If you need that piece of file, that object within the next year, you're going to pay a high retrieval fee. So you have to stay away from those kind of things if this is something that you don't need to touch. This is what cold data storage is for. It's meant for archive data, such as data that's stored for legal or regulatory reasons, and it can be stored at a very low cost at archive storage. Yet it's still available if you need it, but if you need it within the 365-day minimum, you're going to pay a little extra for that. So the thing here is that there's high redundancy here. So it's redundant across regions and multi-regions and dual region storage, so that if something were to happen from one region, your archive still exists. So this is the idea. So we've got archive storage, cold line storage, near line storage, and we have our standard storage classes that are available with Google Cloud Storage. Each of them have their use cases and when you should use one or the other. So that's a little bit about the storage classes in Google Cloud Storage. In this video, I'm going to describe the ramifications of choosing a specific location for a Google Cloud Storage. Just as in real estate, location, location, location is very important when it comes to our Google Cloud Storage buckets. So choosing this correct location for our data storage is going to affect things like our performance, our cost, and even our legal compliance. In fact, depending on what kind of data we're storing, there might be actual systems in place or compliance measures in place so that we have to store the data in the same location that the user is creating that data. So that's really important. So it's important to consider the specific needs of the project, the organization, the legal ramifications, and when you're making this decision. So let's talk about some of the location options that are available with Google Cloud Storage. One of them here is known as the region. The number of regions used to store your data are going to play into things like our high availability, durability, latency for distance users, and overall cost. And so each of these things are going to affect us. The first thing I want to talk about is called the region. All a region is, in Google Cloud computing terms, is that it's a specific geographic place, such as a country or a city, and data is stored in a single region. And it's usually just great for applications that require data to be located in a specific area. Now, there is another version, and that's called a dual region. This specifies not one, but two regions within the same continent, keyword continent. So I can have two cities on the same continent like Tokyo and Osaka. Objects stored in dual region are replicated in both regions. So you're going to offer redundancy across those regions, and this is going to support business continuity and disaster recovery as well. You'll also notice that there's not just a single region or a dual region, but you'll have a multi-region one. Again, this is now a very large geographic area, such as the continental United States, and this can contain two or more geographic places. So data is what's going to be dynamically stored across multiple regions within a continent, and therefore provides superior availability and redundancy, as you might expect. Without having the higher price of a dual region storage, you can have this in a multi-region. But there is a catch though. Can introduce unpredictable latency and higher network egress charges. So you have to keep that in mind when you're trying to determine which one of these options to use. Now, another thing that you should talk about is the effect of location it has on latency. So real-time access demands lower latency. That means the physical distance between the data center and the users accessing the data at that data center matters. So it can affect the time it takes to access or transfer data. Think about this. It's actually kind of common sense. You have a data center in the United States and there's a user in Tokyo. Well, now they have to send a signal to go from Tokyo all the way to the US to retrieve an image or an object or some piece of data, and has to send that information back. So that's going to take a very long time compared to someone who lives in France, who is a little closer to the United States, right? So you have to now think about spreading your information, the same information, across many different regions to sort of reduce those latencies, because the closer the users are to their data center, the easier the retrieval is going to be and the better user experience they'll have. So choosing one or multiple regions for storage closest to storage users can reduce our latency, and that's something we should think about. Another thing that we should talk about is the effect that location and cost has. Okay, so cost definitely affects it. Different locations will have varied base costs due to their localized expenses. For example, electricity costs are different in different parts of the world. Therefore, if you're running a data center and it's higher electricity costs are there, well, guess what's going to happen? You're going to be paying a lot more for your storage because it's using more electricity. its cost of electricity is higher than it is for another location. So you have to think about those kind of things. Another thing that we should talk about here is they're going to access data from more distant locations will bring higher network expenses. So it can be easier to store information at certain locations. However, the further away that location is than to the end user, the higher your network expenses are going to be. So you have to, it's a double-edged sword. Yes, you want to be able to store them in certain locations where they're cheaper cost of localized expenses that are there. However, the further away they are, you're going to be paying that in terms of the network expenses associated with it. So you have to think about those kind of trade-offs when we're actually dealing with location and cost. Is yes, minimize the localized expenses as much as you can because that's going to minimize your storage, but also keep it as close to you as possible because it's also going to minimize your network expenses. So there's a location and compliance that I want to also discuss as well. So you'll have things like regulatory requirements where we have to adhere to certain laws and regulations that apply to their physical locations and those of the customers that we're trying to see. So, for example, if we're dealing with health data in the United States, health data in the United States has to be stored within the US. That's if we're collecting it on a US-based customer. Okay. You'll also talk about data sovereignty, where some regions will have strict data sovereignty laws that require data to be stored and processed within the country's borders. So this would be a non-compliance can lead to legal penalties and actually cost you a lot of legal fees as well as customer trust. Privacy laws are another issue. So with regulations like GDPR in Europe, organizations need to ensure that their data is aligning with those GDPR privacy laws, which can dictate, for example, how and where personal data can be stored and transferred. And then we'll also have things like encryption and key management. Now, it's not just that we are kind of keeping things stored in certain locations, but we also now have to start using things like Google Managed Encryption keys from the key management service that are compliant with standards that need to be there. So you may have customers may opt for customer managed encryption keys for added control on their Google Cloud storage and location, but all of these things will affect the cost and as well as the latency, as different options in our regions are going to either increase the user experience, increase our costs, or decrease our costs. So we have to make sure that we're choosing the right locations for these buckets as best as we can. So that's a little bit on the location parameter when it comes to Google storage. In this video, we're going to identify the process and reasons for performing common cloud storage tasks. So the common cloud storage physical tasks that we want to do, they could vary depending on what we're doing, but there's like three main ones that I want to discuss right now. The one that I want to first talk about is enabling the cloud storage application programming interface. That's the very first thing we got to do. Why do we have to do this? Well, we need our applications to interact with Google Cloud Storage programmatically, not just through console. So to do that, we need to enable this API. And this is common because APIs are essential for automating our storage operations, and we can integrate them with even other cloud services or third-party tools like a Python script, for example. Another thing that I want to talk about is creating and deleting buckets. Well, obviously, we need to be able to create buckets because they are the basic containers to hold our data. I can't upload any data if there's no container in the cloud for them. So that's what we need to do. So we can do this programmatically, or we can do this through the console. So we want to be able to manage buckets because it's a fundamental task, because it involves things like setting up our storage architecture and removing unnecessary or obsolete containers within them. That's all going to be part of our process. Now, the final thing that we want to do in our Google Cloud Storage, this physical task, is we want to make sure that we're able to obviously upload objects, download objects. We have to store files in the cloud and retrieve them whenever we need. And so we have to add and access data. It's just one of the core functions, and that's why we even use Google Cloud Storage Services, because it's not just about uploading, but we also have to retrieve them with relatively low latency depending on what objects we're trying to use in our use case. But it's not just the physical tasks that I want to discuss. Another thing that's really important here is the common cloud storage meta tasks. So let's think about this, right? So we've got to be able to set an object metadata. Now, metadata, remember, just refers to, it's just data about data. So it's data on the actual object that's being stored. So this could be its size, its name, it could be its format. All of those things are going to be part of its object metadata. The actual data of the object would be us actually opening the file, which could be an image or a video, and that information that's inside of the file is the actual data that we're trying to store. So keep those two things kind of separate in your head, but metadata is just providing the information about the data that's stored, and this could be things like content type, creation date, really any custom attribute. Now, proper metadata is really important because it helps us in organizing our data. So I can have all of my JPEG image files in a certain location in my Google Cloud. I can have all my PNG image files in another storage location. It's how we want to organize it so that we can search it and manage those access to objects within our storage. And that'll make it very easy for us to sort of either retrieve the information or manage who has access to what class of information that we need them to. And another thing that I want to discuss is that we want to be able to create and manage identity access management policies. Because my data is all organized, now I can have this concept of least privileges where I can actually say, okay, this person needs access just to my images, so he just needs not even access to all of my images, but just for the JPEG images, so I can create an IAM policy that allows him just to access the folder in my Google Cloud bucket that deals with JPEG files or JPEG images. And so that's how we can create these identity and access management policies, because my system files and objects are organized properly. So security and proper access control is very critical for protecting our data, and it makes sure that only authorized users can perform certain actions that we deem appropriate. Another one here is that we want to be able to upload and implement version controls. Now, this is important. Not only are we uploading a file, but we want to be able to keep track of and manage different versions of that file or that object in the cloud. Why is this common? Well, version control allows me to make edits to an image, but if I don't like those edits or I need to revert those edits to a previous version of that image, well, I can do that because it allows me to preserve that data integrity and recovery, so I can allow users to restore to previous versions of that image so that nothing is gone wrong. So I'll always have kind of a history of every object that's in the cloud for me, and I can just revert back to an earlier image. So that's a reason why we want to use these things. Another thing that we want to do is maybe use directory synchronization. This allows me to sync local directories on my computer or on my local system with cloud storage, and this allows us to have data consistency between the local and the cloud. So synchronization will just help us in maintaining up-to-date backups, for example, or I can have mirrors of my local data in the cloud, so in case something happens to my local on-premises machine, no problem, I've got a backup in the cloud. I'll just get a new machine and put that information from the cloud back on here and set up the data synchronization all over again. It's a way just for us to be very cautious to make sure that we're not going to be losing any data. But another thing that's actually quite useful is being able to share a bucket across projects using the identity and access management policies, or the IAM roles. This allows our data to be accessed across different cloud projects, and so you'll see that it's common when we're trying to share data between projects within our organization, and it's often necessary for things like collaboration and leveraging data in multiple contexts. So that's a little bit about all the physical tasks and meta tasks that we might take on a Google Cloud Storage object.
In this video, I'm going to show you how we can perform some tasks associated with setup and configuration of Google Cloud Storage buckets. Now, for doing this kind of operations, it's much easier to actually use the gcloud shell inside of our Google Cloud project. So at the very top of our page on our Google Cloud project, we'll have a little button here that looks like a terminal. It's just between our search bar and our notifications icon. And it's this little square thing, and you can see there's some icons there that implies that it's for a terminal. Click that, and then what's going to happen is you'll be met with a page that looks a little bit like this. It might ask you to authorize some APIs. Just go ahead and click authorize. And you should be inside of your project's gcloud shell. And this is where we can actually run some commands and some terminal commands in here so that we can actually create some buckets and some files and all sorts of things. So what I'll do here is first, now it'll take about 10 minutes to get to this step. Just give it a time to spin up. But once you're here, you can actually start writing some commands. And this is very similar to an Ubuntu system. So you can see here, I've got some ls here. I've got some files. I can start doing any type of commands I can normally do on a Linux operating system. I can do so right here. Okay, so what I'll do now is I want to run a couple of things so that we can actually make sure that we can create some objects and buckets inside of the gcloud. So what I'll do is first make sure that I've enabled my Google APIs for storage. So to do this, I can actually use gcloud space services space enable space storage dot Google APIs.com. Okay, now a little window will pop up. This is perfectly normal. Go ahead and click Authorize Cloud Shell so that we have the proper permissions for our gcloud command line interface to run these operations for our Google APIs. So I'm just going to go ahead and actually just spell this properly. So Google APIs.com. Okay, so now that we've hit this, so now this is enabled. We've authorized these things, so we should be good to go. The first thing we're going to need to do is, remember, storage deals in buckets, so we should probably use and create some buckets. So I will do so by creating a bucket with what's known as the Google Storage Utility, or GSUtil command line. So GSUtil contains many different things, many different commands that will allow me to create my buckets. So first thing I want to use is GSUtil MB space -L, MB for make bucket, -L, and we're going to provide some regions. So this is our location. It's not just important that we're creating a bucket, but we have to tell it where this bucket is going to be located. So we're going to put this on the US Central 1 server, which is fine. That this is the closest one to me. You may want to use a different zone or a different region of your choosing, but that's really what we need to provide, is just a region. Next thing I want to do is provide it a name, and we do so with a naming convention like this. It's GS : // and then a bucket name. So this is where I can have my name of my bucket. So I'm going to call this example bucket and a / or \. So now I've got my example bucket created. I'm just going to go ahead and click enter. This will take a couple of minutes just to actually create some buckets for me. Now you can see here, oh, it looks like there's a bucket that's already exists with example bucket. So what I will do is call this example bucket -CLI and click enter. And so now this will create a brand new bucket. And you can see here that there's just a little saying here, creating GSUtil example bucket CLI. Great. So now that that's ready to go, I can just type clear. Now my bucket is created. And what I can do is now upload some objects. So what I'll do here is I'm going to create some files. So next thing I'm going to do is I'm going to use the touch command. I'm going to say hello google.txt, and I'm just going to go ahead and just go into hello Google and just add some text, be like, hello, this file is in my bucket. So this is a small text file. So what I want to do now, if I type ls, you can see my file is right here. I want to go ahead and actually upload this to my bucket. So I can do so by using, again, the GSUtil command line tool. So GSUtil for Google Storage Utility. And I want to copy or CP some information. So the local file path that I want to provide is this, hello google.txt. So I'm going to copy that and just put this here. Okay, so you can see here, hello google.txt is there. That's my local file path. Now I want to place this at the root of my bucket. So I'm going to use my bucket name that I created just a moment ago. So this is going to be example bucket -CLI, and I'm going to put a / here. Now, what I'm going to do when I hit enter is it's going to actually copy the files. And so you can see here that it's copying a file, tells me exactly what file that it's copying, and it's copying a 32-byte file. So that tells me the progress of how it's copied. And it should tell me that an operation has been completed over one object of 32 bytes. So that's great. So that's exactly what I want to do. Now, let's see if this bucket actually exists. So if I go to GSUtil space ls, and this allows me to list the contents of my bucket. So I can go GSUtil : / and my bucket name. So this is going to be example -bucket -CLI, like so. And if I hit enter, I should see one thing. So there you go. You can see that there's my file that I just uploaded. It's inside of my bucket. So watch this. If I just clear my screen and I just remove hello google.txt from my system, now that's fine, because I know that if I hit up arrow a couple of times and I try and list the file, I can still see that this bucket is This file is actually stored inside of my bucket that I've created. So it's actually backed up for me. Now, how do I get it from the bucket back into my directory? So you can see hello google.txt is no longer in my directory. Well, I can do this with a simple download command, and it's actually straightforward to our original command that we copied a local file path to a bucket. Now we're going to do it backwards. We're just going to go gsutil, and we're going to copy, but this time we're not going to copy a local file, we're going to copy a remote file. So this is what we're copying. We're copying our bucket name, so this is our example-bucket-CLI, and our bucket name, our file name is given to hello google.txt. So I can go ahead and paste that right there. And so that is the name of the file that I want to put. And now if I hit // here to let it know that this is my current directory, this is where I want it to exist, I can go ahead and click enter. Now it'll take a couple of seconds. You can see here that it's copying this file. So that's right in my bucket. And if I hit ls, you can see, hey, I just downloaded it again, and I can actually go inside it and see what's inside of my hello.txt. You can see there's this file's in my bucket. So there you go. So that is a little bit on how we can actually download an object, upload an object, and really it comes with these operations that allows us to actually change things on our own. In this video, I'm going to show you how we can actually manage our object lifecycles and how to actually use object lifecycle management on a bucket, and really how we can actually view a bucket's current lifecycle configuration. Let's first understand what it is. What is object lifecycle management, or OLM? So this is just a way for us to automate data management, and it gives us a way to optimize storage costs and maintain just bucket hygiene. So it's really useful for when I'm working with large data sets, and manual management is just it's too much, right? Imagine if I'm taking so much ingestion from an outside source like an API or something, and it's creating flat files in my bucket. If it's creating too many, it's too much for me to actually manage on my own. So what I need to do is use some type of automation tool with object lifecycle management in Google Cloud Storage so that I can manage the lifecycle of my objects automatically within my buckets. Now this involves understanding how the lifecycle configuration actually works, right? So I can define a lifecycle configuration for my bucket. And this is just what this is just a set of rules that'll apply to current and future objects, okay? So I'll give you an example. Each rule could specify an action to be taken when conditions are met. So let's say that I want to move any files, any objects in my bucket that are greater than 2 years old, okay? So that means when the object's age is just about 2 years or older, we're going to move that bucket or delete that bucket or delete that object inside of the bucket, and that's how the lifecycle configuration will be, right? So the action to be taken is deletion, and the conditions that are met is when the file's age is 2 years. That's an example of a lifecycle configuration. So we understand that there's going to be lifecycle actions, right? So the action in my case would be things such as deleting an object, like I was mentioning, or we could change its storage class, or I could relocate it, or there's a few different modifications that I can make on the object itself. I could rename it. I could do whatever I need to do. But I can set a rule to downgrade the storage class of objects that are older than a certain period. And so that'll allow me to save costs on storage without having to delete the files. But there's also lifecycle conditions, right? So conditions can be based on an object's age, creation date, or other attributes. So I was using the object age in my example. That's one way that we can actually have. And then there's lifecycle execution. So automatic execution just makes sure that my lifecycle of an object moving without manual observation and action, it just happens in the background on its own. So when it meets a criteria of a rule, an action is taken on that object. And that action could be deletion or moving it or downgrading its storage class. It could be anything like that. But you set that on the bucket level, and any object inside of that bucket is going to have this object lifecycle management process. Now, let's talk about some of the actions. So the first one I talked about in my example was deletion. This permanently deletes objects that are no longer deleted. That's self-explanatory. Another one that we can use is set storage class. So I can transition some infrequently accessed data to a colder storage class. So what this means is in a regular storage class, the objects are instantaneously available. I can download them pretty quickly. Everything's fine. The colder storage class here, we move an object into this special storage class. Now, it's still available. I haven't deleted it, I can request that information. The difference is that it takes a little bit of time to get it from the Google Cloud. So this is great if I don't need this data frequently. And if I do need it, I'm okay with waiting like 10, 15 minutes to get the information somewhere. Totally fine. Another thing is abort incomplete multi-part upload. This allows me just to clean up incomplete multi-part uploads. So if I'm uploading a large file, usually what happens is that it's split up into pieces and each piece has to be uploaded individually. But if something were to happen and there's like some error, those pieces that are already there, they're going to stay there and take up space. So I can actually have an action that says, okay, in the event that I've just tried to upload a file and you're uploading it in pieces and there's, my internet connection died or whatever it is, it'll identify that, hey, this is an incomplete multi-part upload. I'll abort them and I'll clean up any incomplete multi-part uploads by deleting them. And this just allows me to free up storage resources and save some cost. So setting up the Object Lifecycle Management Tool, or OLM. So this is the first thing we want to do is be able to navigate to our cloud storage. We want to log into our Google Cloud account, and then we want to select our bucket. Find the bucket that you want to enable for this Object Lifecycle Management. And then what we're going to do here is then select the Lifecycle tab underneath this. Once I click on the Lifecycle tab within the bucket details, that's where all the information I'm going to need to add a rule. This is our next step. It's important that we create a new rule and we have to specify the configuration of the rule. And there's two pieces. First piece is the action. We choose what action to take an object meets, such as transition of storage class or deletion or whatever it might be. So I choose the action. Second thing is the condition for when the action is going to take place, such as my age of my file is going to be 2 years old. Then I can delete it or move it to a different storage class or whatever it might be, something like that. Okay, so now that I've defined the rule, it's important that I save the rule. So click Create to save the new rule, and then I can add multiple rules with different conditions and actions, and then I can just click Save. Then what I recommend you do is you test the rules on deployment data first. So test your rules on development data before applying them to production. That's really important. And so keep in mind that these changes to the bucket's lifecycle configuration is not instantaneous. It could potentially take up to 24 hours. So keep that in mind. Okay, so another few different OLM tasks that I want to discuss is that we want to make sure that we verify the lifecycle status. So there's a way that I can actually look at the log of the lifecycle and see how it's doing and sort of make sure that it's doing what I expect it to do. Another thing that I want to do is also manage any existing rules. It's really important that you go back and you may need to edit or delete or maybe add new ones. You can go back into that same page that you were just on and go ahead and manage those existing rules and different criteria or change the conditions. Whatever you'd like to do, it's all available to do. It's not set in stone, so you can actually go back and modify those things. But keep in mind that it takes about 24 hours for changes to cascade. Okay, and that is the basics of OLM in Google Cloud Storage buckets. In this video, we're going to discuss how we can secure our objects with access control in the Google Cloud. So let's talk about securing objects with access control. Remember, when we're uploading objects, it's not just enough what we're uploading or where we're uploading it, but it's important that we have some way, some mechanism to limit who has access to certain objects. And this is the idea of enabling and restricting access to storage objects, but also their whole buckets as well. And we can use either the identity and access management or what's known as an access control list. Those are the two primary ways to handle these things. Now, we need these things in certain scenarios. So, example, if I'm storing sensitive data, like personally identifiable information, financial records, medical records, that kind of thing, in a bucket, I need to be able to collaborate with multiple teams or external partners, and I need to be able to share this common bucket. So I need to serve a static website content, such as images or HTML files from a bucket, and then users will upload those files to a bucket, and we need to be able to see exactly who can upload and view this information that's being uploaded. Okay, so, well, how do we actually handle this? Well, we can actually do this at the uniform bucket level access. Now, this is recommended for most of our scenarios, especially if you're trying to work with managing permissions across multiple objects. And the way I would start this is that this will only use IAM for our permissions. So it allows us access allows you to use IAM alone to manage permissions for our buckets and objects. So somebody with a certain role or permissions attached to their role, whatever it might be, they can access this information. So the permissions are the same for all buckets contained objects. So if I apply this on the bucket level, that applies to every object inside of that bucket. So it provides features not available with ACLs, such as managed folders and IAM conditions, domain restricted sharing, and even workforce identity federation. So those additional features are very useful for this kind of granularity that you have on the bucket level itself. So to enable uniform bucket level access, what we end up having to do is just create a bucket and choose the uniform option. And once I have that enabled, I have 90 days to switch back to this fine-grained access before it becomes permanent completely. So there's a bit of a 90-day return policy for these settings that you want to have. Now the fine-grained access, this allows us to use both IAM and ACLs, access control lists. This allows me to take a little more granular approach on who has access to what, not just at the bucket level. So it gives me fine-grained access. We'll combine the legacy access control lists, which support Amazon S3 as well. And this is great for interoperability with other cloud providers such as Amazon AWS services. And you can see that ACLs will secure our individual objects rather than the whole system. And while IAM permissions apply at the bucket level or higher, so that's useful for that. And I can also have an IAM secure buckets or higher levels, so I have the best of both worlds. I have the identity access management, will secure my whole bucket, and my access control list will secure individual objects inside of that bucket. So it gives me this kind of granularity that is useful for this kind of stuff. Now, IAM permissions with ACLs are actually quite useful to handle. So IAM and ACLs work in parallel, and either system can grant access to a resource. Now, IAM is usually recommended for its unified view and consistent inheritance, but you'll also see that ACLs grant object level unique permissions and interoperability with Amazon S3. So I can use the ACLs here if I'm trying to work interop from an inter-cloud perspective between Amazon and Google. This is the way to handle it. Now they work in parallel. IAM permissions do not appear in ACLs, and ACLs do not appear in IAM permissions. So it's important that you know that the ACLs are set on individual objects, but the IAM permission is actually set on the bucket level itself. So those are the main things. Now, you can simplify your management by disabling ACLs and using IAM exclusively for controlling accesses to your resources. That's perfectly fine. But if you have sensitive data, you should store it in a bucket with uniform bucket level access enabled. That's really the best way to handle it. It's the best practices I suggest you make. So that's a little bit on IAM permissions with ACLs and other things as well. In this video, I'm going to discuss the Google Persistent Disk, compare the cloud storage with this Persistent Disk service, and identify when you might use each one. Let's first get started with cloud storage and persistent disk explanations. So there's object storage and there's block storage. Cloud storage, like we've seen before, is very good at handling objects. And this is great for unstructured data. Now, persistent disk uses what's called block storage. Now, persistent disks, and they're called local solid-state drives, SSDs, that are attached to virtual machines, uses this kind of storage, and it's great for things like consistent, low latency access, and it's integrated in our VMs. So when I create a VM, I'm really creating like a boot disk. I'm having something that has some certain level of gigabytes, a certain amount of gigabytes attached to it. That's like our hard drive. And this is what we really use this for. And it's great for this high performance and redundant network storage. And data is striped across many physical disks for us by a hypervisor. It can be zonal or regional for added redundancy as well, so that if one region goes down or one zone goes down, well, guess what? There's another one to back it up. And so persistent disk, again, is just using this kind of block storage. Now, because we're splitting our data across many physical disks for consistent input-output operations per second and throughput, this thing is quite fast and it's redundant. So data is automatically replicated within a storage infrastructure for us, and this is very advantageous from when we're trying to deal with this kind of low latency system. And I can have this in a zone or regional availability everywhere. And so this is great for when we have this kind of durability. So it's replicated within the storage infrastructure to ensure high durability. And I'll have this kind of flexibility where a region goes down, it can replace across two different zones later down the line. So in every region, there's two zones. I'll have this data replicated in both zones. So if one zone goes down, the other one's right there. And so the use cases here are primarily used with virtual machines and Kubernetes databases. And those are really the system. That's really what we're looking for. Now, a local solid state drive is chosen for workloads that require the highest possible IOPS, and their lowest latency do not need long-term data persistence. Now, this is physically attached to the server hosting the VM for performance. Now, local SSDs are great for temporary data, and it can be recreated, or it's not critical if it's lost. So I would use persistent disk to make my data persistent. Here, however, I'm trading that persistence feature for a faster throughput of information. So this is great for very low latency use cases, but it's not durable like it is with the persistent disk. And this is going to give us really good I/O operations compared to persistent disk. Now, it has fixed size for each local SSD, so you can't attach multiple local SSDs to a single VM. You choose the SSD, it sticks on the virtual machine. That's the SSD for that virtual machine. Now, again, this is great for high demand temporary storage needs use cases. Things like caches or scratch space for high performance computing or data analytics. This is what I'd use this device for. So that's the difference between object storage and block storage, as well as the difference between persistent disk and local disk in Google Cloud. In this video, we're going to compare some cloud storage with file store and identify when each type of storage would be used. Let's go ahead and look at the difference between cloud storage and file store. So cloud storage is just the object storage service, and it's great for binary and object data, blob, really just any type of unstructured data. File store, on the other hand, is the managed file storage service optimized for high performance file-based workloads. What this is, it's suitable for applications that need a traditional file system, much like the one that you have on your computer already, and it has the same file system semantics. So it's often used for things like enterprise applications, databases, user home directories, anything that require a file system structure. Now, Google File Store features multiple features here that is quite useful for our applications. One of the ones that I like is the network attached storage, or NAS. It provides petabyte scale online network storage, and it's great for high performance computing. It has persistent file storage. It supports multiple concurrent application instances, and it accesses the same file system simultaneously. You'll have a multi-reader and a multi-writer. If you're working with a Google Kubernetes engine, File Store allows you to mount your GKE persistent volumes as read-write by many nodes. So now you'll have multiple ways to read and write to the same system. You'll have something known as what's called POSIX compliance. So File Store is POSIX compliant, which means it behaves just like a traditional file system, so that we can mount our hard links and file locking that we'd normally see in traditional features like this. And here's another one on service tiers. This is where it gets interesting. It offers multiple service tiers tailored for specific use cases, so I can have basic file sharing and web hosting to even high availability for mission critical workloads. It doesn't really matter what your use case here, there's going to be a service tier that's available for you, even if it's something very mission critical or something small for temporary storage. Anything like that, it's available. Now it supports NFS v3 and NFS v4.1 protocols, which facilitate communication with data transfers between clients and the server, and it's very scalable. And once you provision this, I can scale the capacity of my file store instances according to need without any downtime. So I can go up or down in storage space, it doesn't really matter. Now there's connectivity as well. File store instances can connect to any clients that are on the same VPC network, and I can even use this on a shared VPC network. Now let's talk a bit about the tiers that are available here for our file store. The first one is this basic HDD or solid state drive tier. This tier is suitable for file sharing, software development, and use cases with the Google Kubernetes engines. And it's great for a cost-effective solution with HDD storage. Now, zonal is another one. This is a little bit of a lower capacity or a higher capacity range. So you'll offer scalability up or down in 256 gigabyte units and performance that scales with capacity. Now, what will happen here is this is designed for our high performance computing, things like batch computing, electronic design automation, media rendering and transcoding, even some advanced AI and handling very large data sets is great for these zonal tiers. Regional is another one. So regional tier provides high availability across 2 zones within the same region, and it makes it suitable for mission critical workloads. And this is ideal for enterprise applications and databases that require high availability and resilience to zonal outages. Enterprise tier is the highest performance and availability that is possible with this service. It's designed for the most demanding workloads. Now, this allows us to use things like scale-out architecture. You'll see that data is stored twice per zone for durability, and it's 99.9% available. You'll have synchronous replication between zones, and it ensures changes are immediately replicated. Now let's talk about enabling our file store. Select or creating a project is our very first step. Now, these are the steps that we should follow. Make sure that we've selected the project for our file store, and you don't plan on keeping the resources. It's recommended to create a brand new project for this. Now, you want to ensure billing is enabled for the project. So confirm that billing is active for this service on your project, and you can enable the file store API for our project, and you can do this through the Google Cloud Console or by using the Google Cloud SDK. Another thing that we can do is we have to make sure that our virtual private cloud or our VPC network is properly configured, and we need to verify that the network has the necessary firewall rules to allow traffic between things like our GKE clusters, if that's what you're using, and our file store instances. Or if you're using a shared VPC, make sure that the necessary permissions and routes are set up correctly for that as well. The next step that we want to follow is we want to secure our file store with some identity access management, and that's important that we have some type of security on who can access this information. Another thing that we want to do is we want to connect via supported protocols and drivers. So we'll explore the supported file system protocols, and remember that the file store API provides fully managed NFS storage, and through Kubernetes APIs, and you can dynamically provision these persistent volumes on ourselves. And this is a driver that's a primary way for us to use our file store instances with our Google Kubernetes engine, and this driver is called the File Store CSI, and it provides a fully managed experience that's great for our Google Cloud File Store and our Google Kubernetes engine. And that is a little bit on enabling File Store and what File Store is, as well as some of the features that go along with it compared to the cloud storage. In this video, I'm going to identify which use cases would lead to an implementation of Memory Store, and what's the difference between Memory Store and Google Cloud Storage. So let's take a look here. Memory Store and Google Cloud Storage, they both serve distinct purposes in the Google Cloud ecosystem. What Memory Store really is just a fully managed in-memory data store allowing for sub-millisecond latency for Memcache or Redis support. What it is also just using Google Cloud Storage so that we have an object storage solution designed for storing and retrieving large amounts of unstructured data. The difference between this Memory Store and the Google Cloud Storage comes down to what use case you're trying to support. For example, if I'm looking for this sub-millisecond latency, such as something I'd use for Memcache or Redis, I'd use something like the Memory Store. But if I'm using the Google Cloud Storage, I'd want some type of object that I don't need this sub-millisecond latency for, and more of a long-term storage. I'd use Google Cloud Storage for this. Now, these use cases for Memory Store really just comes down to whether if you're caching some information, so you don't have to go and retrieve it from a database or a data warehouse, or you could have some real-time analytics. So as information is coming in, you're storing it in this Memcache or some type of Redis system. And so this is great for applications that need rapid access to data for analytics and processing, so they don't have to go and fetch it from the disk on a database or a data warehouse. Another thing that's actually useful is leaderboards. Gaming platforms will often use it to manage their leaderboards efficiently. So if you've used some type of video game before, you could see a global leaderboard. This is what it's actually doing. And then you'll notice that there's a queue. Now, queues for Memory Store can handle tasks such as messaging queues, This is where we would hold the messages inside of this fast sub-millisecond latency retrieval period. Now, Google Memcached is part of the Google Cloud's memory store. Now, it's a fully managed Memcache service, and it provides a high-performance, scalable, and secure in-memory key value store. Now, the key here is that it is a key value store with low latency. So you provided a key, and it returns the value in that information. So that's how you're able to retrieve things very quickly. Now, this is open source compliant, and it's very scalable and reliable. In fact, the service is so scalable, it can enable you to adjust resources as your applications need to grow. So you can configure the number of nodes, the memory per node, and even the number of CPUs that you have per node based on your workload requirements that you're trying to use. Now let's talk about Redis. If that was Memcache, what's Redis? Redis is similar. It's an in-memory storage. It actually stands for Remote Dictionary Server. This is an open source in-memory data structure store, and it's used basically as a database. In fact, since it's all in memory, it holds all data and RAM, and it allows for low latency reads and writes. It makes it particularly suitable for these kind of use cases that require fast data access, and it's great for things like caching. In fact, there's different data structures. It supports various data structures such as strings, lists, maps, sets, pretty much anything really. It's very good with spatial indices or bitmaps. So these structures allow for very complicated data manipulation and storage. It's not just a single value that you're retrieving. It's very performance in mind. Because it's all an in-memory database, we're using RAM, and that's much faster to retrieve information from than the disk. So this is a high performance with sub-millisecond response times, making it the fastest database of pretty much anything. It's much faster than a regular database that you'd see on a Postgres. It also offers things like persistence and replication, as well as high availability. So this is where it can provide this durability with persistence mechanisms. And so you can configure it to periodically dump the dataset to disk or append each command to a disk-based log for recovery purposes. It also has atomic operations that allow it to perform like an ACID kind of thing on its data types. So I can append it to a string, I can increment the value in a hash, all sorts of things I could do. Another thing it supports is scripting pub/sub support. Now, this pub/sub support, it has a publish and subscribe messaging paradigm, which allows for message broadcasting to many different multiple subscribers. Now, the memory store features is, again, another useful tool offered by Google Cloud. It has very high availability with both their basic tier and their standard tier. Standard providing a high availability using replication and automatic failover. Now, the security is another useful feature that's offered. Of course, we need to, since we're storing data in the cloud, security is paramount. So we have to protect it from the internet using our VPC networks. We can have a private IP address, some IAM integration, and in-transit encryption. There's also scalability issues that we can have. We can start small and grow as needed with automated scaling. And we'll have things like migration with no code changes. And so there's open source compliant, making it easy to switch applications, and backups, which offers basically our import or export features. So we can migrate them using basically an RDS snapshot. And that is all the differences between Redis, Memcache, and Memory Store inside of Google Cloud Project. In this video, we're going to discover some of our key concepts that are associated with our data transfer services. And this is a tool that's successful for migrations of data and why we want to use it in the Google Cloud. So Google Data Transfer Services, also known as DTS, is a powerful tool for just migrating our data to our Google Cloud. So this is great for if you have an on-premises database, if you've got some type of information on your local machines and you want to move them up into the cloud, we can leverage DTS so the organization can reduce operational overhead and minimize some downtime. So it's just a managed service for moving data. That's all this is. So it handles all the underlying infrastructure, our software updates and maintenance, and allows users just to focus on the migration itself without having to worry about the underlying infrastructure and software. It supports varied sources. So this is where we can have an on-premises database. I can even source it from other cloud providers. I can have an online source where I can transfer data publicly that's publicly accessible from HTTP or HTTPS locations. And there's also things like our secure service. Security is a top priority for DTS, especially since we're moving data. So it includes features like encryption and compliance, so that there's make sure that our organizations can meet the regulatory requirements, especially with the type of data that we might be moving. And it's quite scalable. It's built to handle migrations of any size, and so we'll have things from gigabytes to petabytes of data. And the great thing is, it'll automatically scale for you to accommodate whatever volume of data you're transferring. And all of this is very user-friendly. It's designed to be intuitive. It's a very low-code approach to moving information, so you can set up and manage your data transfer jobs with very little code. And it's all done through the Google Cloud Console if you'd like. Now, the Google Data Transfer Services has a few different use cases. So we've already talked a couple of them, but let's talk about a couple more here. If we have Google buckets, if we have buckets from in the cloud, and there's a lot of data in one bucket, and we want to transfer it over to the next one, we can transfer this data between our buckets using our DTS. In fact, we can also migrate data to our Google Cloud this way, and we can back up and archive all of our data. So it can be used to back up data to Google Cloud Storage for disaster recovery, or to archive data that is not frequently accessed. Those kind of things are what's really good with DTS, but it's also shows its use case with data processing. So data that needs to be processed or transformed, DTS can move it to the appropriate Google Cloud service where these operations can take place. So I can actually use DTS as a middleman in my ETL if I'd like grab some information and send it over to a pipeline that does the actual transformation. And so now I will then also use it for large data transfers. The service is beneficial for these very large scale data transfers. Again, it's up to moving petabytes of data at a time, very big data. This is essential for significant cloud migrations or data processing tasks. Now, Google has its consistency. The DTS data consistency is important, where we'll have things like during migration, you'll go through several mechanisms. And what will happen is these mechanisms are strategies to help maintain the integrity and consistency of our data. And so a couple of them that I want to talk about here is that it checks for validation. Before and after our migration, we have to validate the data to ensure that it's been transferred accurately and completely. Now, Google Cloud offers tools, things like Dataflow and BigQuery data transfer services that are meant for this kind of validation purpose that we want to use. Another thing that I like to use is make sure that we have cyclic redundancy check, or CRC checksums. Now, for certain types of data transfers, especially if you're working with a distributed file system like Hadoop or HDFS, what we notice is that composite CRC checksums are great to guarantee that the data is valid and it has good data integrity, especially when we're transferring very large files. Now, there is some limitations to Google DTS. It is a great tool, but it's not the perfect tool. So the object size that we're looking at is maximum single object size limit of 5 tebibytes. And this is if you have objects larger than this, the transfer is going to fail for those objects. So keep in mind that that's the largest object that you can handle. And there's an object naming requirements as well. There are for objects in cloud storage that apply to all DTS transfers. You have to make sure that it adheres to this naming convention. And there is a updated object failure. So if an object's data is updated during a transfer, DTS might fail during that transfer for that particular object. So keep in mind that it's going to transfer objects that is not being updated, that's not live. So that's really what you want to use this for. It's not a real-time data transfer either. It's something that can be done in batches. So it does not support real data time transfer, and it's not meant to be used as a synchronization tool. It's just meant as a giant bulk transfer from one place to another. Another thing that's key here is that it's a one-way transfer. It's designed just to send information from a single source to a single destination, and it's not suitable for scenarios where it's requiring a continuous sync with data in other locations. There are other tools for this if you're trying to sync two sources to kind of destinations, like a source and a destination together continuously. There's another service that would be useful for that, but that's not what DTS is for. There's also complex deployments are another issue. They aren't exactly trivial to set up, so you have to make sure that you have your deployments ready to go and they kind of make sense. So you'll have to check the logs for this. Another thing is I'll notice if API limits and quotas are going to be a problem as well if you are looking at continuously sending information. There are usage limits and quotas to protect the Google infrastructure from these excessive API requests, so it's something to keep in mind about. But there is a way, I guess, if you call your Google Cloud representative and sort of explain your situation, they might be able to bypass that information, that limit for you, depending on what's going on. But again, it's not out of the box. There are some limits and quotas that you have to adhere to. And migration service restrictions are also in play. The data migration service won't migrate from multiple source accounts to a single target account. So you have to keep that in mind. You have to have a single source account and a single target account for this kind of thing to work. And so this is the limitations of Google DTS, as well as some of the pros and use cases for using Google DTS. In this video, I'm going to be discussing how we can do our pricing for our cloud storage resources in Google Cloud. So there's a bit of an interaction between storage choices and the effect on our overall cost of storage, and I just want to explore this here. So remember, when we're talking about pricing for cloud storage resources, there's a different tiers that we want to talk about, so we have to choose the right tier for our business use case. And so what it comes down to is you have to analyze your expected needs for things like retrieval and the permissible latency of access times. And this comes down to what your business use case is and how fast you need this information. So it's expected to have multiple storage classes in play and to migrate data between them as data moves from what's called a hot type of storage to something colder, such as nearline or cold line or archive. So the first thing I want to talk about is the standard. So the example of gigabytes per month per cost. So we've got the standard. So this is going to be, if we look at on a per month basis, this is going to cost about 2 cents USD for this kind of thing. So this is important. So for every gigabyte that you store in your standard tier, it's going to cost 2 cents per gigabyte. And so that, and a nearline is a little bit different, where this is where you don't need the information readily available. So it can take you a few minutes to retrieve the information. Well, this costs about 1 cent USD per gigabyte. Again, cold line, even colder. This costs less than a cent. So this is going to take even longer to retrieve the information. This is like your cold storage. And then the one that takes the longest to retrieve, but is the cheapest per gigabyte, is our archive. And basically all of our storage resources will have these four tiers that allows us to choose which one that might be useful for us. So there's a big difference between our archive and our standard. Standard would be like, just a second to retrieve the information, and archive could be a few hours. It depends on what you're doing here. So all your hot data should be stored in a standard, and the infrequently accessed data should be stored in nearline, cold line, or archive, depending on how often you might need it. Now, there's a way for us to manage our pricing in Google Cloud Storage, and you can actually look this up in Google Cloud underneath the pricing tab. And so it'll tell you exactly what's going on. So operation charges apply when you perform operations within our Google Cloud Storage. So an operation is just an action that takes changes or retrieves information about resources. That's considered an operation. So you pay for those things. So a retrieval fee applies when you read, copy, move, or rewrite object data or metadata that is stored using nearline, cold line storage, or archive storage. So there is a retrieval fee, and it's in addition to any network charges that are associated with reading data. And that happens when you are trying to retrieve a file, and that changes. So that's the idea of a retrieval fee. When you're using this cold storage, yes, you're paying money for the storage. Yes, you are. But you also can pay money to retrieve the information from that cold storage, because it has to go and fetch it. And that is going to be about 1 cent or 2 cents per gigabyte, and the archive storage would be about 5 cents per gigabyte to retrieve that information. Now, the buckets that you're going to be using, this affects us in certain ways. So there's going to be operations that are free, and there's going to be operations that are going to cost us a little bit of money, and so we have to keep track of them. And you can look at this underneath the pricing tab inside of Google Cloud, and you can actually see exactly for what class I'm working with and what region I'm working with will all affect the price, and you can see the breakdown of what you're doing. Okay, so pricing from our Google Storage network, there are network access charges related to the amount of data that's read from or move between our buckets. So data transfer within Google Cloud, that's when data transfer is to other cloud storage buckets or to other Google Cloud services. There are network usage charges that apply for this data. And it depends on the class that you're using, whether that's standard or cold storage or archive. Something like that is going to affect your price. But there are specialty network services when data transfers uses certain Google Cloud network products. For example, if you're familiar with Cloud CDN or cloud storage, data transfer charges are waived, but cache fill charges may apply. You'll also see media CDN, cloud storage, data transfer charges, and that's another one you can use. So a CDN or cloud CDN or CDN interconnect, those services will allow you to bypass the network charge, but you do have to pay for the cache fill charges to actually fill the CDN. So it's a little bit different. Now, a general data transfer, when data transfer is out of Google Cloud or between continents, such as from a bucket to the internet, that kind of thing, there are some costs associated with it. So the general data transfer to worldwide destinations, this can go, if you're going from 0 to 1 terabyte, it's about 12 cents. 1 to 10 terabytes, it's about 11 cents. And this is per gigabyte of usage. So every gigabyte that you transfer between a certain number here, it's going to cost you a certain amount. But what you'll notice is the more data that you're transferring, the cheaper it is per gigabyte. So that's kind of how their pricing models work. But keep in mind that you are not just paying for the storage, you could be paying for the retrieval and the network cost to actually move the data from one location to the other. So it can add up, but the great thing is that Google Cloud has these tools built into the console that allows you to see how your products, how your code is kind of either upping the money or bringing down the money. That's really how this stuff will work. So that's a little bit on Google Cloud pricing models for both network, storage, and retrieval. In this video, we're going to talk about cost of Google Persistent Disk and local SSDs in Google Cloud. And we're going to talk about some of the factors that affect these price costs. Okay, so controlling the price of these persistent disks and our local solid state drives. So with Google Persistent Disk to start, what affects our cost is the disk type. This only applies to persistent disk options of standard hard disk drive, standard SSD, and premium SSD. They all have different pricing. So you're billed for not just the disk type, but also the capacity. The more space you have, regardless of its usage, whether or not you're using it, that's how much you're paying for it. So larger capacities can offer a lower price per gigabyte, but you're paying for more because there's just more space. So you got to make sure that you're paying for that provision space, make sure that you're using it all, don't over provision, and keep track of those things, right? So another thing you want to think about is your local SSD has a fixed size per gigabyte per month. So that's important. And that's going to affect what's going to happen. Now, the reason why is because they can only be purchased in fixed sizes. So you can't actually have something in between. So you can either have 10 gigs, 100 gigs, 200 gigs, like that kind of thing. That's what these local SSDs are for. So just a little bit of difference between persistent disk and local SSD. Now the performance with persistent, what you'll notice is that the performance is going to scale with size, and this is going to affect cost. Okay, the larger the disk, the more performant it's going to be, and that's also going to affect your cost for this. Now with local SSD, cost scales with the number of disks, interface types. That's kind of how this will work. Now the number of attached local SSD disks and the selected disk interface, whether you're using an NVMe or an SCSI, it can impact your performance and your cost. And another thing that you want to also think about for both places is that costs will vary by region. More high in demand regions are going to cost more, less in demand regions are going to cost less. So it's important to check what's going on the Google Cloud website. It'll tell you exactly what your prices are per region that you're trying to deploy to. That's definitely helps out in this case. Now you want to make sure to optimize your costs. You want to make sure that you right size your storage. Allocate only as much as you need. No more, no less. Try and determine what that value is and then stick to it. Select the appropriate disk type based on your performance needs. Do you really need an SSD? Do you really need an NVMe? What is the, can you get away with getting a little more latency, or do you need the fastest latency, the lowest latency possible. Those are the kind of questions you want to answer when you're designing your system. And then the location is you have to choose the regions with better pricing, but also choose the regions where your customers are going to be using the product. Plain and simple. That's kind of how it works. And so you want to use those detailed calculations on the Google Cloud Pricing Calculator and sort of mess around with these parameters to see, okay, what is my cost window going to look like for the product I'm working with? Now, controlling the price of Google File Store, that's really important as well. Let's think about this. So we've got our service tier. This is the type of service tier you choose that affects the price. So you'll have like an options that includes basic HDD. That's a standard. Basic SSD, that's your premium. You'll have things like enterprise or zonal, which offer these high scale solid state drives, which again, you pay more. They're very performant, but you're paying more for it. Another thing that you'll notice in file store is that you're paying for instance capacity. So you're billed for the allocated storage capacity, even if you're not using it. So if you pay for 2 terabytes, but you're only using 1 terabyte, guess what? You're still billed for the 2 terabytes. So you keep that in mind. And another thing as well, just like with the other services, pretty much all services across the entire Google Cloud ecosystem, the location where your instance is provisioned will affect the cost. Different regions have different pricing. It's not uniform across the globe. And this kind of makes sense. So we want to choose to optimize our costs. You want, again, right size your capacity. Choose the appropriate service tier that you're trying to work with and pick the location. Provision your instance in a region that offers the best rates for your needs. For backups, you are also charged based on the number of stored bytes within a minimum charge of 1 hour of usage. So make sure that you're backing up either more or less depending on your use case. Again, you can work with the Google Cloud Console and work with its pricing calculator to see exactly what will happen with Google File Store with the parameters that you're looking to achieve for your product. Now, when we're talking about controlling the price of Google Memory Store for Redis, we're talking about our service tier again. If this decides if Redis instances is standalone, which is our basic tier, or you have something known as highly available, which has a little more fault tolerance to it, and this is called the standard tier. Now, the standard tier includes things like cross-zone replication and automatic failover. So if one zone fails, no problem, we've got the other zones to back it up. Another thing that you're paying for is your provision capacity. Again, you're billed based on the storage and throughput capacity you allocate, not what you use. So that's important. Higher capacity tiers will offer better performance, especially with Redis version 6. And the region that you allocate your Redis instance, that's going to provision affects your costs. So choose the region that affects you. Remember, different regions are going to have different rates, and you'll have replicas as well. For standard tier instances, the number of read replicas will affect the pricing. You can add up to 5 replicas to scale read queries, but again, you're paying for more. So you have to select the service tier for your needs, right size your provision capacity, and choose the region for this place. That's how you control those costs. Another thing that we can actually look at is controlling the price of our Google Data Transfer Service. This has a few different metrics. It's a little different from the rest that we've talked about. First one here is data volume. The amount of data you transfer will affect the cost. You're billed for the bytes that are successfully transferred to our destination. That's one of these things. Another thing is we have things like network usage. This cost can vary depending on whether the data is transferred within the same network, between different networks. That will also affect your cost. Now, it's not just transferring, but the transfer type that you're using. So the price may differ based on whether you're using an online or offline transfer services. Online transfers, for example, involve data movement over the internet. You're going to have to pay for network usage, while offline transfers use physical storage devices, so it's a little bit different from that. So you'll pay a little less. Choosing the type of transfer, the network usage, the data volume, this will all affect it, but it also has several service features, some advanced features like scheduling, for recurring transfers or using custom scripts. All of those might incur additional costs. Now, what you can do is you can, again, look at the detailed breakdown to estimate costs in the pricing calculator on Google Cloud, depending on how often you want to run this data transfer service and what network and what region. All of those things will affect your cost. So to optimize, minimize your data transfer. Only transfer the data and delete any redundant or obsolete files before you do any transfer. You'll have things like efficient scheduling. Schedule transfers during our off-peak hours if possible, as this can sometimes reduce the cost. Less, if you're doing it while traffic is low, your network cost might go down. And then you monitor your usage. Regularly monitor the transfer activities and see if you can identify any inefficiencies or unnecessary transfers so that you can actually kind of trim the fat, so to speak, and keep the volume of data low and make sure that you're not overscheduling or running this service too much for your use case. And so those are just some of the kind of optimizations for costs and what affects costs for these services in Google Cloud. They're a little different. Some of them are just meant for storage. Some of them are meant for just moving information, but you can check the cost breakdown on the Google Cloud pricing calculator for more information to actually work with the services that you're looking to work with. And that is a little bit about costs in Google Cloud. In this video, we're going to talk a bit about troubleshooting when it comes to Google Cloud Storage. So there are some common issues that can arise when you're using Google Cloud Storage buckets, and I'm going to talk a little bit about them. As one of the most common ones when it comes to troubleshooting Google Cloud Storage is security, and you'll see things like authorization errors. The specific codes you're going to see is 401 unauthorized and 403 forbidden. 401 unauthorized just means you have to verify if the credentials are correct and you have the necessary permissions, so you'll have to speak to the administrator. 403 forbidden is check if the account is disabled or if the access of the resource is forbidden due to those permissions. So one is unauthorized, meaning that your credentials are wrong. Forbidden means your credentials are right, but you don't have the necessary permissions to access that information. So both cases, check with the administrator. And if you're the administrator, you'll have to go into your IAM and make sure that you have the necessary permissions or if your credentials have changed. Now, you've got the bucket access with cross-origin resource sharing, CORS configuration. CORS it can be a little bit messy when it comes to buckets, but it doesn't have to be. Ensure that CORS configuration on the bucket matches the request values and that you're not using an endpoint that doesn't allow CORS requests. Now, CORS is essential for things like our web security, and it helps mitigate the risks of what's called a cross-origin HTTP requests, which are restricted by the same origin policy. So it's going to be checking to see if it can actually make a call from this service. Now, that is the two most common ones, and we'll talk about a little bit more about the rest. There's a couple more that I want to talk about, and one of them is the error codes 400 and 409, and this is where you'll have things like a bad request and where you've maybe improperly formatted your request, so confirm that your request that you're creating is properly formatted. You'll have a 409 conflict, which allows you to resolve any conflicts. And what I mean by that is that those could occur when trying to create an already existing bucket. So if you're trying to create a bucket that already is up in the cloud, you could get a 409 from the command line interface, for example, telling you that, hey, this already exists. So you might have to change some stuff. You'll also have networking issues. So if you troubleshoot drop network traffic, ensure that the project's firewalls explicitly permit the network traffic to reach your instance. So that's another thing. I've seen a lot of people have extra security there and some ports aren't open, and then that causes some failures to actually retrieve information from the bucket. So that's usually just a human error on when you've configured your firewall. So you might have to open a few ports there, but just open the necessary ports to make the request. Don't open any extra ones and sort of open yourself up to an attack. Another thing I want to talk about is troubleshooting Google Cloud Storage performance and health. When we're talking about performance issues, we're talking about latency issues, and this is often tied to our bucket location. So when you're talking about for upload or download latency, where the bucket is stored is obviously going to affect how long it takes to upload or download this information and the users accessing them. So you want to use the nearest region to reduce your latency. You also want to check the Google Cloud Service Health dashboard for storage insight errors. This is going to check for incidents affecting cloud storage services, and it's actually right into the Google Cloud Console, and it gives you this user interface that you can actually look through and see if there's any errors that you're seeing, any logs that might affect you. That's all going to be there. So that's a little bit about troubleshooting when it comes to Google Cloud Storage buckets, as well as what we can do to sort of make sure that we have the correct ports open on our firewall so that we can retrieve the information from these buckets. In this video, I'm going to identify some common issues that can arise with Google File Store and how to troubleshoot them. So Google File Store is just a managed NFS file server, and it's all offered on Google Cloud, and it provides storage for applications that usually are running with the virtual machine instance on Compute Engine. Okay, so there's a couple things that I want to talk about when it comes to file store access. you want to use the recommended virtual machine type. Every file store has a recommended VM, and you want to make sure that you're using that for your client VM. If your client VM is running Linux, confirm that you're using the default mount options, and note that using the sync client mount option significantly reduces the performance, so make sure that you're mounting the disk properly. And you want to place the VM in the same file store region. That also affects it. If you have your VM in one region and your file store in another, there's going to be some latency issues. Make sure that they're in the same region to sort of reduce that. And mounting across regions not only reduces performance, but you'll also be incurring network costs because now you're sending information between regions. And that's where your network costs are going to come into play. It can be quite expensive. So pick your VM and your file store machine to be in the same spot. And so you want to watch for maxing file store capacity. If your file store instance isn't at or near full capacity, when capacity is nearly full, remaining space becomes highly fragmented, and that becomes, it can slow things down. So you can cause read and write operations to slow down. So what I like to do is set up a low disk space alert to avoid this scenario, so that when my disk space is starting to get a little bit low, it's fine. I'll just provision a little bit more. These things can scale efficiently, so I'll get a little alert. And this makes sure that the file store access is actually doing what we expect. Another thing I'd like to do is schedule regular performance testing. I'll test the performance of my file store instance using a tool, and this is the file input-output tool. So if the results show abnormally slow performance, I can contact my account representative and ask them to sort of see what's going on there. It might be something wrong with the machine. It might be something wrong with my configuration. I'll be able to sort of see how what to do when I run these tests with my file input-output tools. Another thing I'd like to discuss here is just some additional file store troubleshooting issues. We could be managing many small files. Now, in addition, when we're looking with the standard configuration issues, high volumes of small files, file store files will share using the sync export option for data safety and NFS protocol compliance. And so if I have many files are involved, the cumulative latency are going to add up. So if I'm extracting tar files or copying many small files can lead to reduced performance. So to improve performance, what I like to do is consider parallelizing file creation with things like the Google Cloud Storage util or GS-util in the command line interface. This allows me to copy data between cloud storage and file store, and this will also help. So copying data from cloud storage to file store instance using GS-util is known to be slow, but I can ensure the cloud storage bucket with client virtual machine and file store instance all reside in the same region, and then this will reduce my costs for networks. So dual regions will provide a maximally performant option for data stored in cloud storage. So if using this option, I like to make sure that my resources will reside in one of the single regions, and I'll have them contained in a dual region. And so if my cloud storage data resides in US Central 1, US West 1, ensure that my client virtual machine and file store instances will also reside in US Central 1, and that also makes things a little bit quicker, a little bit faster. But if I have them all in one single region, like everything's in US Central 1, it's going to actually save me some time. And, being able to interface between the file store and the Google Cloud bucket can actually reduce some latency, but it's not something I would do recurrently. I would try and sort of think about using this GS-util as some type of archive mechanism for long-term data storage, and something I want to offload from my file store for more, hot data. That's where I would use this. Okay, so that's a little bit about troubleshooting when it comes to file store and some of the mitigation methods we can use to sort of keep the machine running properly. So in this course, we've examined data storage selection, configuration, and pricing to confidently tackle data challenges. We did this by exploring unstructured data storage options, Google Cloud Storage, choosing storage classes, and bucket locations, managing and configuring cloud storage, managing object lifecycles, and securing objects with access control. Google Persistent Disk and File Store, pricing Google Cloud Storage and unstructured data services, data transfer services, Google Memory Store, and troubleshooting Google Cloud Storage and File Store. In our next course, we'll move on to explore how to design and manage resilient structured relational databases using Cloud SQL and Spanner, with a focus on cost control, migration, and availability. Just as a painter selects the perfect canvas and palette to bring their vision to life, this course guides you in choosing and utilizing Google Cloud SQL and Spanner to create robust, scalable database solutions. In this course, I'll give you an understanding of the architecture and uses of Google Cloud SQL as an OLTP database platform. Discover how businesses' goals such as scalability, recovery point objective, and recovery time objective influence the selection of Cloud SQL editions. I'll then cover the core tasks involved in managing a Google Cloud SQL database instance, including deploying a Cloud SQL instance and conducting high-level instance management, create a database on a Cloud SQL instance, and execute database-level management tasks, such as data verification through queries, and explore strategies to ensure data availability and access, even during outages, and implement failback procedures to restore initial deployments on Cloud SQL. Understand how to utilize Google Database Migration Service for migrating existing database to GCP. Finally, I'll delve into the functionality and use cases for Google Cloud Spanner as a relational database, set up a Spanner instance, and manage it at a high level. Establish a database on a Spanner instance, and carry out database-level management tasks, including data verification through queries. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, I'm going to describe the Google Cloud SQL and its use in OLTP database platforms. So the Cloud SQL, I'll start with a very big overview here, just a very broad one. So what is this exactly? Well, it's a fully managed database service. This means that the business will pay for fees to the provider, and it gains access to the underlying infrastructure for the database. The provider then, in this case would be Google, will be able to manage the databases for us. So this fully managed database service, it allows us just to focus on the business rules and the business logic for our products. Now, we're going to be working with a Google Cloud platform hosting system. So all of this database is going to be managed by the cloud. And you're going to have features such as auto-encrypted data for security. And the idea here is that we're going to have a SQL database, a relational database that's in there. And the database is going to be in rows and tables. And each row and table is going to have encrypted information. And it's going to be automatically encrypted for that kind of security that would be important when we're dealing with sensitive information, such as personal information, credit cards, names, addresses, that kind of thing. And the Cloud SQL features provide lower maintenance costs because it's fully managed by the cloud. You don't have to worry about the maintenance of the application data itself. So there's flexibility in focusing on the business rules. You'll have things like business continuity. So you'll have proper data backup and recovery. So in case something were to happen, you can just easily retrieve the latest application data and continue operations without any interruptions. So there's proper business continuity in that service. There's also security and regulatory compliance as well. So this provides data encryption and firewall protection. And so Cloud SQL will give us this kind of system so that we're protected against any nefarious attackers. And so this RDBMS service is going to focus on providing private connectivity with authentication and user network controlled access. And there's simple initial setup here. It's actually, you can get started with just a couple clicks or a couple commands on the command line with G-Cloud interface, and you can have a database application within minutes ready to go. So some of the other features that I want to talk about are the things such as automated tasking. So with automated tasks, you'll see that it's simple for me to set up a recurring task and have it run on a schedule, such as vacuuming my data, adding a row, or doing some type of analytics. This is all there for us. So you'll have task management to ensure that you can focus on scaling those businesses while we're going. And so you'll have proper storage management, things like backup or redundancy management, undergoing updates, capacity management, or even just providing any data access. This Google service will offer all of that, and it does that for you underneath the hood automatically without you having to do anything. And so this simple integration, this easy integration is important. because it allows us to offer Cloud SQL instances and ensures easy integration with things like App Engine or Kubernetes Engine and even Compute Engine. And there's easy migration as well. So database migration services make it easier to migrate the production databases to our cloud. And so that's very easy for us to handle this. So I can take things from on-premises and put them into the cloud quite with a database migration service. And then I can replicate these capabilities from MySQL and PostgreSQL. And then I can have some reliability of the migration data, and it's available at no additional charge. So you can get this set up even if you have data sitting on premises. So the Cloud SQL insights that it provides is quickly understanding and resolving database performance issues on the Cloud SQL is completely possible in the cloud. So I can actually see what's taking very long and why it's taking long to do an operation such as a query. And we can identify what we need to do, whether that's adding an index or changing the schema or doing some operation. But highly scalable is really important when it comes to Cloud SQL. It needs to scale with traffic. So you can scale up to 96 processor cores and more than 600 gigs of RAM. So you can scale out with read replicas as well. So you'll have one write instance and multiple read clusters. So you can sort of load balance between those two. And so then what you're having here is the standard application programming interface or the API libraries that are available. I can build and deploy for these clouds faster using things like Cloud SQL. And it offers things like MySQL and PostgreSQL databases. It's very simple for me to use. And you can actually use this in the terminal, or you can use this in your SDK libraries for a programming language such as Python. So another thing I want to talk about here is the automated backups. Cloud SQL or MySQL will automatically perform these regular backups of our database. And I can also manually initiate backups at any time. It'll actually automatically make backups of my data for redundancy. And it has CPU and memory scaling, just like we were talking about. We can scale our database by increasing or decreasing the number of CPUs or RAM allocated to the database instance. And it has high availability. So it's built-in high availability with automatic failover to a standby instance in the event of a primary instance failure. So you'll have a backup ready to go in case your primary one goes down. No problem. The site's not going to go down or anything. The traffic's just going to get rerouted to our standby instance while we get the primary one back up. And so that is very useful for these things. Security as well is paramount. You'll notice that when we use Cloud SQL for MySQL or PostgreSQL, it's going to encrypt all of our data at rest and in transit. And it's going to be using the Google system, but it's going to have fine-grained access control through things like IAM roles and SSL connections. And you'll have things like logging and monitoring that's important. So Cloud SQL or MySQL provides detailed monitoring and logging capabilities through things like Stackdriver. So you can actually go through it yourself. You can monitor key metrics such as CPU utilization, network traffic, and storage usage. And the great thing is not just monitoring, but you can actually set up alerting through the service as well. So when thresholds are exceeded, you get an alert to let you know something's going wrong. And you'll have Google Cloud Platform integration with other GCP services. So Cloud SQL or MySQL will integrate with other GCP services, such as our Compute Engine, our Kubernetes Engine, and the App Engine. And this allows us to easily incorporate it into existing infrastructure. And you'll have compatible with PostgreSQL and SQL Server tool sets. So this is compatible with things like Microsoft SQL Server, which means you can use familiar tools and libraries to manage and interact with those databases. So that's the great tool for these kind of things. So if you're using a Cloud SQL for SQL Server, I can actually use a Microsoft SQL Server. Or if I'm using a PostgreSQL server in Cloud SQL, I can use pgadmin to manage it. So whatever tool that you would normally use to connect to an on-premises database or a local database, you can actually use to connect to the same system in the cloud. It's no different. You would provide the address and everything will be there. So that's a little bit about Cloud SQL and its services and advantages. In this video, I'm going to describe how business goals of scalability, RPO and RTO, fit into choosing a Cloud SQL edition. So now you want to try and choose your best SQL edition. What exactly are we going to be using? There's many different Cloud SQL variations on Google Cloud, so how do we choose? Well, the idea is that there's different plans, right? So if you have a Cloud SQL Enterprise, these are great for things like general purpose workloads, and it'll offer between 1 to 96 CPUs, a certain amount of RAM ratio. There's a service level agreement of 99.95%, and it has less than 60 seconds of planned downtime. So depending on the plan that you're using, you're going to have different metrics. So for example, if you need more CPUs, you would have to go into the Cloud SQL Enterprise Plus. Because if the Cloud SQL Enterprise offers up to 96 virtual CPUs, the Enterprise Plus will offer up to 128 CPUs, and you'll have 10 seconds of planned downtime with twice the read and write performance. Now, the thing is that our MySQL, PostgreSQL, and SQL Server support is all very important for these things. So when you're trying to choose these things, you have to be able to pick the right flavor of your relational database management system. Exactly what are you trying to do? Now, PostgreSQL is a great all-around choice, and so is MySQL, but there's caveats to each of them, and it depends on the business rules that you're trying to employ. But for all of these things, we all have a easy migration, a migrate to a fully managed database solution, such as MySQL, PostgreSQL, or SQL Server. It can be inefficient and expensive with significant effort around patching. But the great thing about these things is that migrating to this fully managed solution is really simple with a simple service. All you have to do is just take the information from your current database, and these services will just lift and shift these database entries that you have on your local system and put them into the cloud. And it's done through the database migration service with very minimal downtime. So let's take a look at these individually for Cloud SQL Enterprise and Cloud SQL Enterprise Plus, so we have an idea of the comparison between these two. So you'll have, like I said, about 60 seconds of planned downtime and 96 virtual CPUs, and you'll have up to 128 virtual CPUs with 10 seconds of planned downtime. The SQL Enterprise will offer up to 624 gigs of RAM, and the Cloud SQL Enterprise will offer up to 824 gigs of RAM. You'll have an SSD for storage, and they both offer SSDs. Storage for local SSDs is in something that is attached directly to the box that's going to be running your database is not available, but you can get a storage local SSD exclusive to the Enterprise Plus, so that's important. With the Enterprise Plus, you'll have an SSD, but it's going to be attached directly to the box, so it's going to have faster read-write times from there. You'll have the logs on Google Cloud Storage for a maximum of 7 days, and the logs on Google Cloud Storage will be saved for a maximum of 35 days. So that's the difference between the Enterprise and the Enterprise Plus. But it also has a few different performance enhancements that I also want to bring up, is that the increased read performance is via data cache is there. So the data cache will leverage a fast, what's called a local solid-state drive, a drive that's connected to the machine directly. So it stores data pages that are read frequently. So you can get up to 3 times improvement in things like read performance. And it's very useful for in-demand application. But it also has increased write performance. So Cloud SQL Enterprise Plus delivers up to 2 times the improvement in write latency, and it makes it suitable for write-intensive applications requiring low latency and high throughput. There's also a compute engine auto-tuning. So this is the auto-tuning of engine configurations to match capabilities of the underlying instance platform as well. So there's a few different types of scaling that are offered by this service. One type of scaling is called vertical scaling. And so when we're talking about vertical scaling, what we're trying to talk about here is adding more CPU, adding more RAM. We call that vertical scaling, as in we're not adding any new machines, we're just making the machine a little more powerful. Now, it's adding more resources. So it's not only easy, but it's also cheaper than horizontal scaling to do. And it also requires less time to fix things. So if your system is going down, you've got no choice but to vertically scale. It's probably the first thing you want to try. But horizontal scaling is really the long-term solution, because what happens here is that when you start adding new instances of your servers and you add them to the existing system, what you're doing here is now you've got these 3, let's say there are 3 servers, they're going to be splitting the workload between the 3 of them. So that's called horizontal scaling, in the sense that you're not adding more things to you're not adding more resources to one machine. You're now adding more copies of the machine, so it takes up more space in the horizontal direction. That's why that's the way you can remember between horizontal and vertical scaling, is more machines will be side by side, and so you're scaling them out horizontally. So there's disaster recovery variants that are important. So a database will fail over to a secondary region. After the database is ready and used by an application, it becomes the new primary database and remains the primary database. You'll have things like temporary secondary region failover. This will be put back into its failure. So if a region goes down, you've got a temporary secondary region that will start taking over the workload. And so this is really worried about fault tolerance here, or some type of redundancy. Having this temporary secondary region is going to be important for this. But also having a permanent secondary region is important for these kind of things. So if after the database is ready, it becomes a new primary database and remains the primary database, it doesn't shift back. With the temporary secondary region, what happens is it goes down, it temporarily goes to the second region until the first one comes back on and switches over. So we've got a little bit of disaster recovery metrics. So one of the things that I want to talk about is the recovery time objective. This specifies the amount of time from the occurrence of a disruptive event to when the affected resource must be fully operational. And we'll also have a recovery point objective. Now, the recovery point objective is a little bit different. It's especially important when it comes to data backup and recovery activities. What we look at here is that means that the data must not age much from when it was last backed up. Does that make sense? So as a result, the data will be as up to the moment as possible. So you want to consistently have that recovery point objective. Your backups need to be not old. They can't be old at all. They have to be pretty recent. The more recent they are, the easier these things become to kind of go back to those backups without data loss that you're going to be incurring. So that is in the RTO. But the thing is that there's an inverse relationship exists that between the time for recovery and the cost needed to support the recovery. So the shorter your RTO is in terms of time, the more cost for recovery increases, and vice versa. And with RPO, you'll kind of see that, right? Your RTO and RPO values have been identified and quantified by an IT administrator, and it all comes down to cost. How important is this data to back up? Do you want to pay a lot of money for these things? So based on the results of your risk analysis from your leadership, it's a good idea to have what these recovery time objectives or recovery point objectives are supposed to be, because it comes down to how much the organization is willing to spend. So that's a little bit about the disaster recovery metrics with RTO and RPO, as well as the different types of scaling in Cloud SQL Enterprise and Cloud SQL Enterprise Plus. In this video, we're going to discuss the core tasks that are associated with managing a database instance on Google Cloud SQL. So there are core management tasks in the Cloud SQL that we need to be able to handle. So Cloud SQL is a service that allows us to create database instances. It even allows us to edit the created database instances by changing the size or the password or certain settings on the system. But it also allows us to delete our data instances that we create. Now, these operations are typically what we're going to be doing when it comes to Cloud SQL. When it comes to things like vertically scaling, we need to be able to edit our database instances, or if we're trying to change some settings or add some logging, that'll be in the settings as well. We also want to be able to delete our database instances or create brand new ones. And so this is part of the idea of being able to clone our database instances. So imagine now I want to be able to horizontally scale. I have maybe one instance with all my information. And what I'd like to do is then create copies of those instances and then attach them to something like a load balancer so that I can actually route traffic to each of those instances. This involves actually cloning them. Then I'll be able to start, stop, and restart my database instances. And I'll also be able to label the database instances. Now, labeling is important when it comes to things like cost tracking, which is important for the organization that we're going to be working with, because, as we have these tags and labels attached to these instances, we'll be able to figure out exactly what project they belong to, how much cost they're actually incurring as time goes on.
And it also just kind of gives us some more tasks that we can actually do. So creating a database instance in a Cloud SQL instance is important, but we want to be able to list the available instances in the console as well as the command line interface. And so you can actually do this in the CLI and the console itself. And deleting the database instance as well is the possibility for these kind of things. And again, that can all be done either in the console or in the CLI. Now, in terms of authentication, when we're talking about security, we're obviously going to be able to segment our data based on the user that's accessing it. So they're not able to access everything or a portion of it or based on role. So this is where we'll have things like identity access management and data user authentication. So here's the database authenticated user. That's the first thing that we're going to be setting up. And so there will be some built-in authentication uses a username and password, and it'll authenticate our local database users. This is no different than actually authenticating on a local database on premises or on your local machine. And so there's ways that we can actually set this up, but we can also authenticate directly with the IAM roles that are set up for us inside of the Google Cloud Console. And so this offers a built-in password enforcement, but it also allows us to use the IAM service that's offered by Google Cloud to be able to connect directly. So if I am accessing the Cloud SQL from a role that I have attached to my account for my organization, then I should be able just to have passwordless entry into the system. And so that can all be set up there as well. Now, when it comes to database user management, again, it's the simple CRUD operations that we're going to be using, right? So creating a user is going to be important, and we can set up a default user account. We can do this in the Google Cloud Console, or we can use the CLI to do this. And we can also manage the user password policy. And so this is another important aspect. So we want to be able to make sure that the password policy doesn't apply to encrypted passwords, but you're going to set your password and exactly what rules you're going to have on that password policy. And so having extra rules on the password, exactly what's allowed to be in your password, how many tries are you allowed to enter that password before it kicks you out, that is all going to have to be set up by the administrator to do this. And another useful thing is to audit or list the number of users that you have so you have an idea of who has access to your Cloud SQL database instance. Another common thing is we sometimes want to be able to change our user password, and I recommend that this is done frequently to make sure that we're not causing some security issues. So frequently changing the user passwords is encouraged. So maybe having a policy attached to say, okay, every quarter, everybody has to change their password for this database. We want to be able to remove user password policies if need be. So this way, a user that has a built-in authentication type, we can remove that. So to remove the user password policy, you can use simply the console or the G-Cloud command line interface. And another thing that we should be able to do is sort of offboard some users that are no longer needed. And so this should be done at least once a quarter to make sure that you are keeping the people who have access to the data to a minimum. So when it comes to maintenance, there's a couple things I want to bring up. So this is a managed service. So Cloud SQL has some features and updates that happen automatically for us. And so this makes sure that the underlying hardware, the operating system, and the database engine are reliable, they're performant, and they're secure, and they're up to date. Now, this is a fully managed service, so it's not something that we have to set up. Google Cloud just has this product there for us to use. And they'll also manage things like database version upgrades for us. And so, for example, the database software provider that develops PostgreSQL will release new minor versions several times a year. And then each version will come with certain bug fixes or security patches or performance enhancements, that kind of thing. And so you can find those minor versions in the Cloud SQL for PostgreSQL or MySQL or whatever service that you're using, whatever flavor of relational database management system you're using. And this is where we're going to upgrade our version for us. Now, these are upgraded to the latest database version shortly after release.
And so this is happening under the hood for us without us having to do anything. So you're benefiting from running the latest database software. So another advantage of having a fully managed service. And then there's patches for the operating system. So they'll continuously monitor for newly identified security vulnerabilities in the OS. And upon discovery, they're going to patch the operating system to protect the system from new risks. Another thing that I want to bring up here in terms of Cloud SQL is data replication. So replication is just the ability to create copies of our Cloud SQL instances or an on-premise database and offload the work to the copies. So what we do is sometimes we want to be able to migrate data between our regions, and this is useful to be able to use cloud data replication for this. And we want to usually use data replication as just to scale the use of our data in a database without degrading performance. So one thing I like to do is be able to migrate some data between our regions so that it's easier for my clients or my user base to be able to access the information closest to them, rather than me having all my data in one region. Having it between two or more regions allows me to have some type of fault tolerance. So I'm not putting my eggs in one basket, so to speak. So in case a region goes down, I've got other regions to support the user base. Another thing that is useful is be able to migrate data between platforms. And I'd like to migrate from the on-premises to the cloud. And so having data replication in place for these things are going to be very useful when it comes to taking on-premises data and putting it in Google Cloud. Now, replica could be promoted if the original instances become corrupted, and that's perfectly fine. That's exactly what they're for. So when we're talking about a Cloud SQL instance, the instance that is replicated is called the primary instance, and the copies are called read replicas. Specifically, what this means is that primary instance can handle write and read operations, whereas the read replicas are just that. They're meant for reading. Now, in the instance where the primary instance goes down, one read replica is going to be promoted to the primary instance, and we're going to bring up a new instance to replace that read replica. And that's how this kind of works. So having this kind of fault tolerance is really important when it comes to large-scale distributed systems. And managing our SQL Cloud instances is going to be important. So database and user instance backup is going to be very important for no matter what relational database management system you're using. So how we back up our users and back up the data that's stored in their database is going to be important. And this can actually be scheduled. In fact, you can do this with a simple command on the G-Cloud to set up this for your Cloud SQL instance. So I like to have things on a schedule. Depending on the instance, I'll have daily backups or weekly backups, and I can have it set to back up the latest data every Saturday at this certain time when traffic is the lowest. And that's something that's useful for this. And then in case of disaster, I have a backup that I can just take that information and restore everything to a brand new instance. So I'm not going to be kind of dealing with any disaster at all. And so that is the fault tolerance capabilities of managing our SQL Cloud instances. And it's also very useful when it comes to having a distributed system across multiple regions so that we can actually have read replicas and write replicas, as well as some of the operations that we do with users and data replication. In this video, I'm going to show you how we can set up a Cloud SQL instance and perform some high-level instance management. So let's go ahead and get started by setting up a Cloud SQL instance. So to start, we're just going to go into our Google Cloud Console, and we're going to come up here and we're going to search for SQL in our search space. And you're going to see underneath the search results an icon that looks like this, and it'll say SQL, Managed MySQL, PostgreSQL, and SQL Server. Go ahead and click this, and you are going to be met with the page that will look empty to you. It might ask you to enable some APIs. So go ahead and click Enable. Right now I've got a SQL instance that's already up and running for an SQL Server of 2019. It's stopped right now, but it's attached to my project. So what I will do is actually create a brand new instance for this. So let's go ahead and click Create Instance. Now, at the top of our page, we'll be met with the page that looks something like this. Now, the first thing that Google's going to ask us to do is figure out exactly
what our database engine is going to be. So whether I'm going to be using MySQL, PostgreSQL, SQL Server, these are all tools that they have their pros and cons for using them, and we're not going to go into too much of the details between the difference here in this video. For now, I'm just going to choose PostgreSQL, and you can see here that each database engine has a supported set of versions. So as new versions come out, we're going to be adding more versions here and into Google Cloud. And so what I'll do right now is I will go ahead and click Choose PostgreSQL, and I'll be met with a page that will kind of be split down the middle. The first on the page is going to tell me a bit of the instance info and the password that I'm going to use for the actual system. And then I can set things like a password policy, so I can impose requirements on passwords, and I can enable a password policies, and I can have things like all passwords should be a certain minimum length, they require complexity, all sorts of things that allow me to enable these things. But if you notice on the right side of the page, it'll also give me a pricing estimate, which is really important. So if I, $2.04 per hour, that's about $49 per day. And so that's kind of what's going on. So you can make sure that you're meeting the cost based on the configuration that you're spinning up. So let's get started by creating this instance, and let's go ahead and type basic instance name. So this is a unique identifier for our instance. So I'm just going to call it example-instance, like so. And I'm going to provide a password. Now I'm just going to ask it to generate a password for me, and I can actually take this password and use it to connect to the system later. So that's fine. If I want to enable a password policy, I'll checkbox this, and then I can set the minimum length, the required complexity, set password change interval, all sorts of things like that. For now, I'm just going to leave that unchecked. And this is where I can actually start playing around with the database versions. So I want to use either 15 or 16. 16 is the latest one, and that's just what's supported right now. So what I will do now is just leave it as PostgreSQL 15. And now there's like a different Cloud SQL edition. So again, there's going to be Enterprise and Enterprise Plus. And so they have a different level of service level agreement. For example, with Enterprise Plus, you get 99.9% availability, whereas with Enterprise, you get 99.95%. There's less than 60 seconds planned maintenance downtime, and this is a sub-second planned maintenance downtime. For now, I'm just going to click Enterprise for my purposes, and you can see here as I click Enterprise, my cost per hour has just dipped significantly. So here it's $2.04 per hour. Here it is $1.23 per hour. Depending on the region that I'm working in, I can also get a lower cost per hour as well. Now I can choose a preset for this edition. Presets can be customized later as needed. So here, for example, if I'm looking for a sandbox environment, something just for me to create some proof of concepts, I'd use a sandbox. And now the presets here are going to change things like the RAM, the storage, all sorts of things. So now with my sandbox environment, you're seeing a 14 cents per hour, about $3.38 per day. But in production scales, we're looking at $29.41 per day. And so you can work out what that works out to in a month. For now, I'm just going to leave it as sandbox for the purpose of this video, just to reduce the cost. And then we can choose region and zonal availability. Now, just to show you what will happen here, different regions will have different costs. So for example, in San Diego, it's 20 cents per hour. In Iowa, it's 14 cents per hour. In South Carolina, still 14 cents. If I wanted things like on the West Coast, still about 14 cents. So depending on what I'm looking for, so something like Montreal, it's about 15 cents. So it's just to show you that depending on the region that you choose, your cost is going to change. And you can actually see a cost breakdown of what's happening and why. So let's scroll down here just a little bit more to see what I'm looking for. So if I'm looking for a multi-zone or highly available, something with automatic failover for this sandbox environment, I can do that. And now it'll actually double my price from 14 cents per hour to 28 cents per hour, because now we have them in different zones. So for now, I'm just going to leave it as single zone. Come down here to customize the instance as well. I can actually show configuration options and see things like, some granularity. For example, maybe I actually, for my sandbox environment, I don't need 2 CPUs and 8 gigs. I need 4 CPUs and 16 gigs. Well, that's going to change my cost, and it's going to double the cost because we're doubling the CPU and doubling the RAM. And that's really what we're doing here as we're
kind of working with this page is that I get to actually change all sorts of things that allows me to connect to the database or how the database is going to be configured in Cloud SQL. Now, all of these things can be changed as after we've spun up the system. So if I need to vertically or horizontally scale this system, there is a methodology in Cloud SQL here that allows me to vertically scale the machine and then transfer over any data to the new instance. So that's what we're going to do. Now we're just going to scroll all the way down to the bottom, click Create Instance, since I'm happy with the configuration the way it is, and it'll give me a little message saying that the instance is being created. I'll be going back to the initial page. You can see here that it's telling me a bit about the example instance. It's telling me that it's being updated. And if I click all instances on the page over here, you'll see exactly that there's a little green icon, and this means that the instance is going to be updated. Everything that I've done here can also be done in a command line interface as well. Google will give you a way to connect to the machine if you scroll all the way to the right, and you should be able to see things like high availability. Click over here. You can create a clone or connect to a VM when it's ready to go. And then that's pretty much it. That's all you got to do. You're pretty much set up to use PostgreSQL. And the same process is repeated for MySQL or any other database engine that's supported by Cloud SQL. In this video, what I'm going to be doing is I'm going to be showing our created database on an instance of Cloud SQL. And I'm going to perform some database level management tasks, such as creating a database on that instance and verifying some data with a query and actually showing you how we can interact with the system. So let's go ahead and let's go and look into how to get started into this system. So I have an instance already created. So I'm going to access it by going to my search bar at the very top of the page, and I'm going to look for SQL. I'm going to meet a search result that says SQL, and then it has Managed MySQL, PostgreSQL, and SQL Server. And you'll see the icon looks a little bit like a stack, like a little square. And that usually represents the database in kind of a diagram. So we're just going to click this one here, and we're going to be met with our pages of instances that we have created. Now, if you don't have one that's already created, it was done before, but now you've got one that's created. What we're going to do here is we're just going to click Example Instance, which is the one that I'm going to be working with. That's the instance that we're going to be using as our example. You might have it created in a different way. Let's go ahead and click this one, and we'll be met with the instance page. Now, what's happening here is that there's a bunch of different operations that we can do, including things like monitoring, restarting, exporting the information, stopping it, or even cloning our data. And what we want to do is we want to go to the left side of our bar and come down here to where it says users. That's the very first step. Now we're going to come over here and we're going to see that should be a user account that's already created. And the default is Postgres. Since I'm using a PostgreSQL server, I'm going to go ahead and click this button, the little three dots there, and I'm going to click Change Password to something that is useful. So this is in case you forget your password that you used, or you want to be able to add a brand new user account. You can do all this underneath the Users tab on the left side of our screen here. So if you're happy with the settings here, you know the user that you're going to be connecting with, you know that you're going to be using a certain action with this password, we're going to go ahead and come back to our left side of our sidebar here, and I'm going to click Cloud SQL Studio underneath Overview. So I'll be met with a page that looks like this. Now, I'm going to have a database that's already created, but in case you don't, this is how we can actually select it. So there should be at least one database that's created by default. There's Postgres, and I've created one called example-database. And so I'm going to select the database that I'm going to be creating with, and I'm going to give my user and my password from my last step in here, and then I'm going to click Authenticate, and I should be able to access the database. Now, in case you don't have a database that's already created, let's go ahead and go to the left side and come down to where it says Databases. Now, on this left side is where I can create a brand new database. Now, if I click Create Database, all I have to do is provide a name. So I will give it example-database-2, for example, and then I will click Create.
And that will actually create a brand new database. It'll take about a few minutes just for everything to actually show up here. But by the time you're done, you should have two databases, one Postgres, the default that's already created, and the one that we just created. In this case, for mine, it's called example-database. Let's go back to the left sidebar and go to Cloud SQL Studio and connect to example-database. So the first thing I'm going to do is click the little drop-down menu, click example-database, provide a user, in this case it's Postgres, and my password that I set for my user. Now I'm going to click Authenticate, and now I'll be met with our SQL editor. Now in our SQL editor, this is where we can actually use SQL Studio to actually create some data, inserting it into the database, and then doing some operations on it. Now I've already inserted some data into this database, and I'll show you exactly what it looks like here. So I have created a table called employees with 4 columns, and we can verify this data by just running a simple query. So all we do here is just type select space star from employees, and you can see here that it's helping me autocomplete my query. I'm going to click tab here to autocomplete, give it a semicolon to let it know that this is what I want. Now, a couple things that are happening here in this window. One, there's an SQL validator. So it's letting me know if there's any syntax error. So the little green check mark lets me know that I've made everything make sense. And if I make a syntax error, something like select to, for example, it says, syntax error at or near select to. So it's guiding me here with its IntelliSense. I can click format here to format my query so that it's a little more readable. And I can actually have my results display after I click run. Now you'll see when I click run, you can see the information that I've inserted into this database table. It says John Doe, manager, and this is their salary. And these are all the columns and entries that are inside of my system. Now, I can actually run any query, not just select. I can actually do any type of CRUD operations. So if I want to insert more data into my database, I can just come down over here, write another query. So here's where I can create my table, my employees. There's a serial. I don't need to actually create the table again. All I would need to do here is just do a simple insert, and I can insert some information. So here I can put in Jack, and he is a custodian, and they make about whatever number, and then we can come down over here. We can say something like Jill, and we can make them into a CEO, and they make a certain number of money. So just adding information. So if I click run now, what'll happen here is I'm only going to be running the query that I'm on here. So because my cursor is on this query, if I click run, I should insert more data. And that's exactly what you're seeing here. Now, if I come over here and select this, you'll see that I've actually just inserted some more data. So there you go. This is the information that I expect. You can see here we've got all of our stuff. And, it works just like any other SQL information, right? Like any other SQL editor. Not only can I access this through the SQL Studio, which is very useful from the web perspective to be able to get, just to access this information at all times directly in the Cloud Console. It's more secure. But I can actually use any terminal or any server and connect to this database directly, so long that it's publicly available if you have it set up in a public subnet. Security is paramount, so I recommend for any production level data that you keep it in a private subnet, something that's not publicly accessible to another user, and that all users have IAM credentials to be able to use SQL Studio to be able to run their queries in here. And this is how we can interact with all of our data, and it makes things just a little bit straightforward. And besides that, you can do just about anything under here, including manage our users, manage our databases, and even create new backups. In this video, I'm going to describe the process that's used to ensure data is readily available in case that there's a failure in one of our servers. So when it comes to creating high availability on Cloud SQL, what we're really trying to do here is just make sure that we reduce system downtime. So something happens in a zone, power outage, a failure, network failure, anything like that. We want to be able to quickly respond to that event
and have our data accessible even in that failure event. So this is where we have things like automatic database instance failover to another zone. And we'll talk a little bit more about this, but ideally what we do here is we don't just put one region with our database and then have everybody in the world connect to that region's database. That's setting up, it's a recipe for disaster. What you want to do is you want to have failover. So in an event that something happens to this system, you now rely on another system. So the way I think about it is I'll have a database in Ohio. I'll have a database on the West Coast somewhere, say in Oregon. Now, users will be able to connect to whichever one is closest to them. But let's say the one in Ohio fails. What'll happen is that now all traffic is going to get routed to Oregon, and that may take a little bit longer than it normally would for users that are closer to Ohio, but at least they're able to access their data. And that's fine in that situation, but having that automatic database instance failover to another zone is crucial. And what we do to make sure that this is allowed is that we have what's called cross-regional replicas within Cloud SQL. This is where it gets interesting, is that Google Cloud now, because this is a fully managed service by them, all I have to do is just in a few clicks or a couple commands on the command line interface, I can just do this system, have this set up. So I'll have a primary instance somewhere in the world. I'll have a bunch of read instances everywhere else. And then if in the event that something happens to the primary instance, the read instance takes over as a primary instance, and we bring up another server. And so this allows us to have this kind of failover. Now, we have this high availability. So yeah, one of them is downtime, is the time during which the application or system is unavailable or not operational. We want to minimize that. And we'll also have things like regional persistent disk support. Now, this is a high availability configuration, and it just consists of what's called a service level agreement coverage that's offered by Google Cloud. And we'll have something like a service level agreement. Now, this is just an agreement between the service provider, in this case our Google Cloud, our customer, which is us, and it addresses all the required services and the expected level of service that they're looking to provide us. And so they'll say something like 99.95% uptime, no matter what. So that means 99.95% of the time, this database is going to be available. I can pay for it 99.99% if I choose to. If it's something very critical, I may want to pay the extra amount of money to get that higher level of service that I'm looking for. Now, read replicas are a copy of the primary instance, and it changes to primary in normal circumstances. So that's what the read replicas are for. Okay, so Google Cloud has some SQL availability, high availability techniques that we want to use. So one of them is right. It's called a cluster and a failover. Now, this architecture pattern is exactly what you might expect, right? So we've got a cluster of computers. One of them is our primary instance. This handles read and it handles write operations. And we can connect to that instance and make changes. And if I write some new data, if I insert some new data into that database, it now cascades to its neighbors in the cluster. Now, what happens is that if the primary instance goes down, one of the other instances, which is just acting as just a straight read instance, will take over as the primary instance. So now it can handle the read operations as well as the write operations, and then cascade those changes down to its neighbors in the cluster. Now, what happens is while that original primary instance is down, we're bringing it back up. When it comes back up, it's now the read instance and the process continues. So this is how we have this kind of failback procedure. And it's quite important for this kind of system. And so then we'll know that the read replicas and the failover overview is really how this will work, in the sense that, yes, we've got a bunch of read replicas as well as the primary instance, and the read replicas are exactly the same as the primary instance's data, but they're just meant for reading. Now, when something happens, we now have like a zonal outage. The traffic to those read replicas stop as soon as the zone becomes available, and read replicas resume from the primary instance. And this just cascades. We just do this over and over again. No matter how many failovers there are, we'll just use this kind of pattern over and over again. Now, the technology that we're talking about here is called failover clustering. This provides protections from both planned and unplanned downtime. So if a node fails, we'll have another node take over, and the cluster switches to the backup node. Now, this is a very useful tool, and we'll have things like database mirroring. This will provide database level protection from the unplanned downtime. So it protects against database failure by providing what's known as database failover. So when a primary database fails, the mirror enables a standby to be available in about 2 to 3 seconds. So there's just a little bit of downtime for those 2 seconds, but it provides zero data loss. And that's what's really useful here about the database mirroring. Now, log shipping is a high availability and disaster recovery solution that's offered by Cloud SQL. And how this works is it's just trying to protect against unplanned downtime. It's similar to database mirroring. It also works by restoring what's known as a full backup of our primary database to a backup server. Now, the backups are treated equally in what's known as the transaction log. So anytime we've changed something in the primary database to the applied database is going to be done on the backup server as well. So they're going to be always up to date and in sync with each other. There's more technology that's available from Cloud SQL for this kind of thing. So there's peer-to-peer replication, and this is where we'll have data replication techniques that are used to protect applications against the unplanned downtime. This is more of a bidirectional replication, and it's high availability scenarios. We'll have things like our database snapshots. These are essentially a backup of our database at a specific point in time. So I usually have them set on a schedule. Every Saturday, when the traffic is low, I'll take a snapshot. And this feature allows the user to quickly restore the database to any point. And so if I have almost like a timeline, last 6 months of every Saturday's snapshots, I can go back in time and kind of revert back before the system broke. Now I'll have what's called a backup and restoration. And the backup and recovery plan is an essential component of what's known as high availability. This SQL database backup is performed to disk because a disk-based backup is the fastest mechanism for backing up and restoring our data. And this is just built right in. We can use the SQL backup and restore process. That's the same on any relational database management system to do this operation. Now, there's a couple things that I want to bring up here in terms of our Google Cloud SQL locations. Now, you can create a highly available SQL instance in 2 types of locations. First one is known as a regional location. What this means is that it's a specific geographical location. So I give it something like New York or Montreal or Ohio, that kind of thing. Another one that I have is called a multi-regional location. Well, if a regional location is just a single geographical location, a multi-regional location is an extended geographic area that'll include 2 or more geographical locations. So I can just give it a country such as the United States or Canada, and then I can have these multi-regional clusters across the country. So if something were to happen in New York, no problem, Ohio's there to pick up the slack. And that's the idea of these multi-regional systems. Now, Google Cloud has some more multi-regional locations that are offered. For example, there's North America, and this is where it'll include things like Los Angeles, Salt Lake City, Oregon, Las Vegas, North Virginia, South Carolina, Iowa, and Montreal. These are a whole multi-regional location. So if I select North America as that, what will happen is I can have clusters across all of those regions in the world. Europe is another one. Multi-regional location will include things like London, Frankfurt, the Netherlands, Zurich, Belgium, and Finland. Asia, as well as a multi-regional one. So this is where I can have Tokyo, Osaka, Seoul, Taiwan, Hong Kong, Mumbai, Singapore, and Jakarta. And I'll have things like non-multi-regional locations, such as Sao Paulo and Sydney. And those are just made for the Southern Hemisphere there. So that's kind of what those are for. But that's pretty much it. So now I've got a regional and a multi-regional fallback plan, and the technology is then going to be done automatically for me so that I will always have this high availability, even in the event of some catastrophic event such as a power outage. In this video, I'm going to show you how we can actually implement a failback to recover an initial deployment on Cloud SQL. So What you're seeing right now is the SQL instance page, where you'll see I have an example instance that's running on PostgreSQL. And you can get to this page by simply going to the very top of the search bar, looking for the SQL service, which is the Manage MySQL PostgreSQL SQL Server service. And you're going to click that page. It's going to take you right to this. And this is going to list all of your instances that you have. And I'm going to implement a failback to recover a deployment, and it's going to be on the example instance that I have open here. Now, the example instance is just going to make sure that when I click on this, it'll take me to the actual instance page. Now, on the left side, you're going to see a whole bunch of options that are available. The one that we're going to actually hover over and click is the backups, which is underneath the databases. Now, in here, this is where all this failback stuff will live for our Cloud SQL instances. Now, what I want to do is I want to click the Edit System. So you can see here, these are some of the settings that are already enabled by default. So you can see that I have automated backups, and they're enabled. My backup window is going to be from 10 p.m. to 2 a.m. Atlantic Daylight Time. There's automated backups that are retained, about 7 of them, and there's 7 days logged. Now, as you can see here, if I scroll down, you can see that I already have some backups that are already created. And they're created automatically for me. So if I want to go to July 1st, for example, I can click Restore, and I can restore my database back to that state. Or I can create a backup currently with a snapshot. So it's quite simple on how to handle this. So let's say, for example, I would like to create a backup right now, currently for this date. Well, now I can go ahead and create a backup, but I'll be billed 8 cents per gigabyte for the data storage. So it's something to keep in mind, depending on the size of our system, that it might affect cost. Now, what I do is I can describe the backup optional. So this is going to be an example backup. And there's different location options that I can actually enable. For example, I can have this in a multi-region location so that there's some type of dependency. That way, if one region goes, I have my backup in another region. Now, usually I keep everything in a multi-region default, and I keep it in a US data centers so long as they're in the United States. Now, what I can do is when I click Create, I'll actually create a backup that I've created on demand, not automatically. Now, when this is finished, all I have to do to restore is go to the backup that I'm interested in, click Restore, and then I can overwrite an existing instance. And it's simple as that. So I can overwrite the source instance, which is the example instance right here, which is what I've called. And then once I click Restore, there's no going back. I will then go back to my data set of July 4th, 2024 at this time. And that's pretty much it. That's how you can restore your system and keep everything backed up automatically with the backup steps in the SQL managed instance. In this video, I'm going to discuss how we can use the database migration service to bring existing databases into the Google Cloud Platform. First, understand how we can actually migrate to Google Cloud SQL. There is a service called the Google Database Migration Service, and it's meant to take on-premises databases and send them into the cloud. And this is actually just a cloud-based data migration tool. It's something that's offered to Google, and it's a fully managed service that supports users who just want to move our data into the cloud. And it has things like its pricing and its models is all based on the size of our data set and how long the data migration is going to be. So the database migration comes from numerous sources. It could be multiple on-premises sites, and you want to move them all to the cloud. It can all be handled directly by the Google Database Migration Service. Now, there's database replication concepts that I want to discuss, and one of them is the migration concept. So database migration is just a process where data and metadata is moved from our source to a destination database. Destination is typically going to be in the cloud. When the migration is completed, the destination database becomes the primary database, and all dependent applications should read from that primary database. Then we just have to take apart the one that is on premises. Now, we also have something known as continuous migration. So the database migration is kind of like you push a button and it moves everything you have. It's like an on-demand migration. Continuous migration is sometimes referred to as ongoing or online migration. It's just a continuous flow of changes from our source database to a destination that follows an initial full dump and load. So if we have, in the case of a migration, when we want to switch to use the destination for reads and writes, we have to finalize the migration. So what will happen is that replication is finalized between the source and the destination Cloud SQL instance cluster is ready to be used as a standalone primary instance. This is kind of like almost a hot swap. Doing the switch when the source and destination are in sync gives us the most minimal downtime. So there's a few different types of migration that I want to discuss. One of them is known as homogeneous migration. So for homogeneous, for what we're talking about here is like-to-like migrations. So MySQL to Cloud SQL for MySQL. Or if I'm using a PostgreSQL server, I can use PostgreSQL to Cloud SQL for PostgreSQL. This is what means totally homogeneous. The same relational database management system on my local on-premises is going to be used in the same relational database management system on-premises. So Postgres, MySQL. Now, the migration will leverage the primary replica relationships, and this is where we can actually use a MySQL tooling, a PostgreSQL tooling, so that I can set up a migration. A replica instance will appear in the Cloud SQL instance, and then we'll attach the source that was set up. And that's really the idea. So that's homogeneous. Heterogeneous migration is a little bit different, where the source and destinations are different. For example, I could have an Oracle system on my local machine, and I can also want to migrate this Oracle system on my on-premises. I want to migrate it to use PostgreSQL in the cloud. And this is where we're going to use this change data capture based replication that's offered by the database migration service. So there's a few different types of use cases that I want to discuss when it comes to database migration. One use case here is the migration capabilities of database migration service. We'll have this concept known as lift and shift migration to a managed service. So this is when an organization wants to move to Google Cloud. We're going to go from virtual machine-based self-hosted databases to managed database cloud services. So this allows our team to get out of the business of managing the infrastructure and literally just move the data into a fully managed infrastructure solution in the cloud. So that's a lift and shift migration to a managed service. We also have something known as multi-cloud continuous replication. This is similar to the read replicas across multiple regions. So if our data exists in another cloud provider, say AWS, a migration job can be set up so that we continuously replicate the database into Google Cloud for this multi-cloud read availability. What happens then is that I'll have my data in another cloud provider, such as AWS, and I'll have my data in Google Cloud at the same time. Now, the database migration service doesn't support a dual write scenario, but it does support a dual read scenario. So that is, writing to and reading from both the source and the destination in this situation is not allowed, but we can read from both if needs be. Now, the database migration service has a few key features. It's very easy to use. In fact, it's just designed to get new business customers into Google Cloud. And so the tool has to be really simple, very low code for you just to be able to lift and shift your data from your on-premises solution into a fully managed service in the cloud. There's also AI-powered assistance with Gemini. So make database migration will be simpler and faster with this AI-powered assistance. It'll be able to figure out exactly what you're trying to use. So you can review and convert database resident code like stored procedures, triggers, and functions to something that's compatible to a dialect in the Cloud SQL, and it'll handle all that for you. Now there's single-step conversion and migration. So you can modernize your, let's say, legacy Oracle workloads. You can migrate them all to PostgreSQL. There's a built-in conversion workspace that reduces the manual effort of these kind of heterogeneous migrations. And with the tools that's offered by Gemini, it'll help you with the conversion process to guide you through the schema and code conversions so that you can have these heterogeneous migrations all completed. Now, there's also serverless migration experience. You can eliminate the operational burdens of database migration, and there's no migration service to provision, manage, or monitor, and it has auto-scaling, and it'll ensure high performance and uninterrupted data. Security of data migration is paramount. So this is what we want to do here. So I want to be able to make sure that all of my data
with this information that I have. It could be sensitive information such as healthcare or financial information. Because I'm migrating it through the cloud, there's going to be encryption in transit for all of our data that's offered by Google Cloud. And once it's stored, it'll be encrypted by default, and all Google Cloud databases will provide multiple layers of security to meet the requirements that we have for our security and make sure that we're not violating any constraints or HIPAA or GDPR kind of requests, that kind of thing. Okay, so there's also just some Google database migration service elements that I want to discuss. So we have connection profiles, and these are represented by the connectivity information of the specific source that will be used in a migration job. So you can actually set those connection profiles up. So that's how you are able to connect to the source system. There's also a conversion workspace, which helps us convert your schema and code objects from the source database to a format that's really compatible with our destination instance. So that's also available. And we also have data migration jobs, and these represent a source connection profile and a destination cloud SQL instance. And that job is what's going to actually connect to our on-premises, connect to the destination system, and then use any type of translation between, if it's a heterogeneous system, so if we're trying to migrate some Oracle triggers or Oracle procedures into PostgreSQL, it will handle all that for us. And so we have to set up that migration job. This is the actual job that's going to be using our migration specific settings to transfer information from our on-premises to the cloud. And that's really the concept of the Google Database Migration Service. In this video, we're going to be discussing the Google Cloud Spanner and what is it actually used for in a relational database. So Cloud Spanner is a fully managed native cloud database solution that's built by Google, and it's offered here on the GCP platform. This is our first scalable enterprise grade, and it's globally distributed and strongly consistent database service that's built specifically for the cloud. And it combines the benefits of relational database structure with even non-relational horizontal scale. So what happens here is when we have a non-relational horizontal scale, it means that it's very good at multiple writes at the same time. And it's very, very good for this kind of thing. So it actually supports an SQL semantics, similar to really any relational database management system, but it's using almost no SQL principles underneath the hood. And so, but for us as the user querying our information, we can actually just make the proper queries directly in the console. And it has global and horizontal scalability, which is very useful for these kind of things. So it will scale with the demand on the system. So if there's more requests coming in, we'll have more clusters or more systems to be able to handle those kind of requests without any downtime, without any type of latency. And there's automatic data replication and server redundancy built in for us in case of an error that shows up. So we're never actually going to be using data. So Google will actually use the Spanner database internally to manage the workloads for its various products and services. And it uses it for AdWords and Gmail. Google Cloud Spanner is the actual tool that's being used to retrieve data for those services. So there's a few different functionality pieces that I want to talk about. So we'll have transactions that can be applied across rows, columns, tables, and databases within Spanner. And it has multi-site replication and failover reports. So it's synchronous and strongly consistent. So you can control the replication and placement of our data using automatic multi-site replication and failover. So in case one zone goes away or something happens, no problem. We've got it backed up in multiple zones or multiple regions. You'll also notice that synchronous and strongly consistent replication is important. So it's consistent. So if I change one zone or I change one node in the cluster, it transitions all of my changes across many different many different nodes in the cluster as well. So that's very strongly consistent read and writes. So reads are as well consistent, and data is versioned to allow for stale reads. So clients can read previous versions of data and subject to garbage collection windows and all sorts of things inside of the system, but you can have those kind of things for stale reads. And what you'll notice supports a native SQL interface for reading and writing data. So although it's using all sorts of fancy NoSQL tools underneath the hood, from our perspective, we write in a SQL system and a SQL interface, similar to what we would do with any other relational database management system, and Spanner will translate all of those things for us to make sure that we're getting the best optimization. Now, there's some features I want to talk about when it comes to Spanner. So it's globally distributed, horizontally and scalable, and strongly consistent relational database. That's really important for this kind of thing. So not only do we have this kind of scalability, it will actually offer vertical scalability, meaning you can increase the computing resources such as the CPU and RAM allocated to our instance. But it doesn't natively support horizontal scaling across multiple regions. But it has a very strong consistency. So horizontal scalability across multiple regions, continents, and regions are available, but you have to actually enable those tools. And so you'll also have what's known as strong consistency. Now, the thing that I want to discuss is with our consistency, Cloud Spanner will provide strong consistency, meaning that when a write operation is committed, it is immediately visible to all subsequent read operations, no matter where they are in the globe. So Cloud SQL will offer transactional consistency within a single database instance, but it doesn't provide the same global consistency across as Cloud Spanner will. And so that's the idea. The difference is here is that Cloud SQL doesn't have this horizontal scalability across multiple regions, but Cloud Spanner does. You'll notice that Cloud Spanner is a globally distributed, horizontally scalable, strongly consistent relational database, whereas with Cloud SQL, you'll have the same kind of behavior, but horizontally scaling when it comes to those systems is actually quite difficult for us. Okay, so let's move on now to some features that are offered. So yes, we have globally replicated data. So we have something that's fault tolerant, which is really important. And this is going to provide low latency as well to our data from anywhere in the world, no matter where the user base is. And this is going to also enable things like disaster recovery, data locality, and ability to serve users in different geographic regions. And you'll see that relational data model and its secondary indexes and foreign keys are all supported. So both services, such as Cloud SQL and Cloud Spanner, provide additional features such as secondary indexes, foreign keys, and SQL support for complex querying. You'll notice that Cloud SQL will support these features and functionalities provided by the underlying relational database engines. And here, Cloud Spanner is kind of using these tools and optimizing them for us underneath the hood. Now, this is a fully managed service. This means that Google is going to take care of the infrastructure management, things like our backups, our security patches, and our software updates. So that way, all we have to do is just focus on developing the applications without worrying about server maintenance. And this is something that, from a business standpoint, makes a lot of sense. Having an on-premises solution is not just about building the application, but now supporting the underlying infrastructure. Whereas if you're just using this in the cloud, Google is now taking care of these things for us. And so you'll notice that Cloud Spanner's underlying infrastructure is more complex because of its distributed nature. And so building that kind of same thing with an on-premises solution is very challenging. And it's quite the engineering effort for a small company. Now, Google Cloud Spanner also has a few different instance features. So there's at least 3 read-write replicas of the database each in a different zone. You'll have separate isolation for fault domains. So each zone is a separate isolation. And you'll also see that there's a Paxos distributed consensus protocol, and this is used for writes and transactions commits that's available. You'll have synchronous replication of writes to all zones across multiple regions. And there's a 99.999% availability for service level agreement and multi-region. And this is really important. So the database is going to be available even if one zone fails, you'll still have it available in multiple zones. Here's some use cases where people are using Google Cloud Spanner. It's used a lot in the financial services. The industry presents a perfect storm for regulatory requirements and customer expectations, especially for sensitive information. So communications among banks and financial tech companies and regulatory bodies have to run flawlessly around the clock, and this is what financial services offer. You'll see that gaming is used, so it'll test the scalability of a database like gaming. This is what this is for. So imagine now you've got a brand new game, and it attracts millions of players on the day of launch, and all of them represent significant potential revenue from real-time gameplay. so you can't have any type of downtime. Having Cloud Spanner here is really important for this. And you'll see that it's used a lot in retail transactions as well. So e-commerce sites will use this, especially during the COVID-19 pandemic. It's really accelerated how users are using retail sites. So it has to be able to scale vertically and horizontally. And Google Cloud Spanner will work for all three of these industries. And that's just some ideas of why a institution would need to pay the extra money to be able to use Google Cloud Spanner. In this video, I'm going to show you how we can actually start up a Spanner instance and just kind of get it set up so that we can start creating some databases on it. So to start a Spanner, Google Cloud Spanner instance, what we want to do is actually go to the Spanner service. So up at the very top on our search bar, go ahead and type Spanner, and you're going to look for the search results that says Spanner with the 3 wrenches connected to each other, and it's horizontally scalable relational database. Go ahead and click that. And my project has no Spanner instance, so this is exactly what it looks like. It'll look something like this. And what we want to do is we just want to create a provisioned instance. So to get Spanner up and running, there's actually 3 steps that we have to do. First one we're going to be working on is just creating an instance, and then creating 1 or more databases will be covered in a later topic. So let's go ahead and create a provisioned instance to get started, and we're going to be met with filling out some forms. Here is we're actually just going to fill out a name. And so this is really important. When we create this instance, we have to make sure that we name our instance appropriately, and we want to provide a unique identifier for our instance known as the instance ID. Let's first give it an example, -spanner -instance, and let's just leave the instance ID to be the same as the instance name, just to make our life a little bit easier. We'll go ahead and click continue, and now we're actually asked to choose a configuration. Now, the configuration is going to be based on what region we're trying to do. So if I'm trying to have a regional or a multi-regional system, so if I want the regional system, this is the 99.99% available service level agreement that's available, and there's lower write latencies within our region. But if I'm trying to scale this out globally to everyone, people all over the world, I need to have my system in multiple geographic regions, and so I would have to pay for the multi-region. For now, for our purposes, for our example, I would choose regional, but if I was going to work with a production level environment, I would actually make sure that I have multi-region. And I can actually now choose the region that I want to work with. I'm just going to choose US-East 1 for South Carolina. Okay, and that's what I'm going to choose here. So you can almost see here that I've got 3 read-write replicas in 3 separate zones within this region, US East 1. There's a maximum storage capacity of 10 terabytes. The compute cost is 90 cents per hour, and the storage cost is 30 cents per gigs. And so this allows us just to see the estimated cost of our configuration that we've selected. So let's go ahead and click continue. Now we can allocate some compute capacities. Now this is where it's really important, right? So your compute capacity is going to determine the amount of data throughput, queries per second, and storage limits in our instance, and it all affects billings. So for now, what I'm going to do is I'm just going to leave it as nodes selected for large instances, and I'm going to have 1 node. Now, if I had auto scaling as a result, I can enable auto scaling and say that I want 1 node to a maximum of 10 nodes. Now, what this means is that Spanner, as fully managed service, is going to adjust my compute capacity between these minimum number of nodes and maximum number of nodes. And it's going to be based on the traffic and the number of queries that we're trying to submit into the system. Now, because this is such an example, I can get away with using it as 1 node, but I can also keep it as auto scaling if I'm trying to scale this out to a global audience. If I had an application in a production environment, this is what I would be using. And, we'd be doing some testing and changing some configurations for this. So now I'll just leave it as manual allocation for now. And I'm just going to go ahead and click create. That's it. That's pretty much all we have to do. We've got everything ready to go. It's going to take a few minutes for the system to get back up and running. When it's up and running, we'll move on to the next step, which is going to be creating a database. Okay, so in this video, I'm going to create a database on an instance of a spanner, and I'm going to perform some type of query and data definition languages on this instance that I've created. So now that the instance is ready, it's now ready to accept a database. So to do so, I'm just going to go ahead and click the example spanner instance. I'm going to be met with the page that you see in front of you. I'm going to go ahead and click Create Database down here, and I'm going to then give an example database name, and I'm going to choose the Google Standard SQL, as well as provide some data definition language. I can do so at this step if I choose to, and then when I'm finished, I can scroll all the way down and click Create. It's a very simple process to actually create one. It takes a few minutes for the actual database to be created and attached to the instance. Since I've already created one, I'm not going to fill this in, but it's essentially the same thing. The only thing I'd caution you is that you can choose a database dialect. There's two ones that are supported, the Google Standard SQL dialect and the PostgreSQL dialect. Both of them have their pros and cons. I've chosen to create one with the Google Standard SQL, and it has its own data definition language that's associated with it, and so we can actually use that. It's quite similar to PostgreSQL as well. So I'm going to click Cancel here and just go back to my instance page. If I scroll down over here, you'll see that here's my Google database instance that's already been created. And you can tell that it's using the Google Standard SQL. And I'm just going to go ahead and click this database, and I can start writing some queries. And one of those queries that I can do is the queries to actually create a table. So if I come over here and click Create Table, you'll see that I've already have what's called a Spanner Studio, which is where I will write all of my queries for the system. Now I've already written these queries and inserted data into the system, so I don't actually need this tab over here. But if you come over here and look into my editor too, you'll see exactly the same steps that I've used using the Google Standard SQL syntax. I've created my table, which is just a basic users table with a few different columns, such as user ID, that's not null, a username with a string of max, a user email with a string with the maximum character length allowed, and I've told it that the primary key is my user ID. And you can actually see on the left-hand side, in the Explorer section, you can see that the users here are all listed with these three columns, as well as what primary keys that we're using, which is the user ID. And that makes sense. That's exactly what we're looking for. Now, if I insert some data into my users, I can do this. And so this becomes much easier for me to handle. And now I can insert some values into the system. So I can go ahead and insert, just like any other SQL syntax, I can insert some data. And that's exactly what you're seeing here. I have 4 different queries. One will insert John Doe and johndoe@example.com. Then there's Jane Smith and Alice Johnson. All of these are showing up into the table, and we can see so if we go into my editor one, I can actually just run a simple select statement, which is selecting star from my users, and there's all my data that's associated with this table. If I run this again, you can see that this is actually fetching across all of my instances that I have open, all of my databases that I have open. Now this is in a single region instance, but it's able to retrieve this information very quickly. And you can see over here, it'll tell me that the statement is completed in 6.73 milliseconds, and I can actually see an explanation of my data to actually show me how I got the exact output, as well as some query summary information so that I can have some type of analysis to actually see how is this actually performing, if my system needs to be vertically scaled or horizontally scaled in any way. So that's a little bit on how we can use the database creation inside of a Google Spanner instance, as well as just writing some basic queries inside of Spanner Studio.
In this video, we're going to describe the pricing options for unstructured data and select the most appropriate model for our business use case. So exactly when we're working with Spanner or any type of unstructured Google data service, what we're trying to do here is understand the key levers, the parameters that actually contribute to the cost. And so there's a few different variables that we want to look into. One of them is the compute capacity amount. So we want to keep track of the compute capacity, and it's measured in terms of processing units or nodes for Spanner. And it's trying to look at an instance over time to see exactly, okay, as we look at the number of nodes that we're using and over a certain month, what is the cost for it? So you're charged for the number of nodes multiplied by the hourly rate that those nodes are being used. you'll see that there's a database storage amount. Obviously, the more data that we're using, not just the more nodes that we're using to process that data, that's also going to be a key contributor. And we're not also storing our data for consumption, but we also want to create copies of that data for storage. And this is in case for fault tolerance. So we have something like a backup in case something were to happen. Now, all of this data has to be moved from one location to the other. So another key component to the cost is network bandwidth used. Anytime we're sending out data or receiving data, consuming a piece of the network, and so we're going to be charged appropriately for that movement of data. So that's really the four main components for our pricing out structured. But we also have compute capacity that's going to be used and how that actually affects price. For example, we want to look at the regional configuration. It's provisioned as provisioning units or nodes. So one node is about 1,000 processing units, and regional instance pricing includes 3 read-write replicas in a single region. Now, if I wanted to, across this, have some type of multi-regional configuration, I'll have a different price. Obviously, with a multi-regional configuration, there's more infrastructure that's involved there, there's more data that's being used, so it's going to be more expensive than the single regional configuration. Now, this compute capacity is provisioned as processing units or nodes, just like our single units are, our single region is, but the pricing is going to include all default replicas and across region application network usage. So one region may communicate with another region to retrieve data, and that also affects costs. So if we look at the database storage used price, so now we're looking at exactly how much data are we storing. Well, again, this comes down to regional or multi-regional configurations. A regional configuration for one region, pricing is based on the amount of data that's stored in the database, and it includes the cost of storage in replicas, but for one region. If we look at a multi-regional configuration, we're going to be paying more as well, because pricing is going to be based on the amount of data that's stored in all of those regions, because they each have their own replicas for that data. And so you're going to be paying more for that. So for example, for a single region, you'd be paying 30 cents per gigabyte per month. But for a multi-region, you could be paying up to 50 cents per gigabytes per month. So it depends on what your costs and your objectives are in your system that you're trying to design for your business use case. You'll see this same pattern is used across backup storage as well. So it's all going to be based off of regional or multi-regional configurations. Again, pricing is based on the amount of backup storage, and it includes the cost of storage in our replicas for a single region. And then if you have to have that same process, but for multi-region, you're going to be paying more as well. So it's 10 cents per gigabytes per month on a single regional capacity, but 30 cents per gigabytes per month on a multi-regional capacity. And finally, there's the network use price. So it's actually pretty easy to handle things. So there's, in our network, when we're talking about ingress, we're talking about data that's being transferred into the database, and that is going to be free. That's the good news. So if I'm trying to import data or send data, or there's an application sending a insert command to a database table, no problem. That's free for us to use. In fact, you'll see that egress within the same region, so if I'm sending data to the same region, to a service that's in the same region, that egress is going to be free as well. When do we actually pay for network usage then? Well, we pay for network usage specifically when we're dealing with egress that's sending between regions within the same continent. So for example, if I have US East 1, US East 2, and there are different regions, or I'll have US East 1 and US West 1, some on opposite coasts, those are two different regions, but they're both in the United States, they're in North America. So that means we'd have to be paying 10 cents per gigabyte per month for the information that we're transferring between those two regions. And that is really the main purpose of our network use price. It's the only one that's a little different from anything that we've seen before when it comes to backup storage and database storage use price. Now, when we're talking about boosting our pricing, specifically what are we deciphering here is that the spanner data boosts our pricing. We're talking about automatically providing on-demand compute resources. This is the idea of what's offered with Spanner. It can create isolated compute resources, and we can attach them to any existing Spanner instance. And then I can use it to process workloads like federated queries from Google BigQuery. I can even export data using Dataflow or even batch queries from any line of business applications that I have. I can do this all in one spot. Now, this works with, like I said, Google BigQuery, data exports, and even batch queries. And you can also use it to measure usage in serverless processing units. So Scanner will automatically connect to things like data boost resources in the same region as our active Spanner instance by default, so we don't even have to worry about that. And you can enable this by granting required IAM permissions and configuring connections to things like data boost, and then after that, it should work on its own. Now, we're working in serverless processing units, or SPUs, and we're charged on a per second basis with a 1 minute minimum charge. So that's something to keep in mind. Now, these are what's going to represent the compute resources that are required to service a query. Now, there's the database import and export pricing that is a little different from the previous models that we've been discussing. So they're cost-based on standard rates for Dataflow batch workers, so there's no additional charges from Spanner for use of the export or import tools. But what you're paying for is for the data storage and Dataflow workers to actually do the job. And you may have to pay outbound data transfer rates for cloud storage, and that's a part of the problem here. I guess that's part of the downfall for this. So if you're trying to send information to cloud storage in a separate region, it does not overlap with your cloud storage bucket configuration. You have to pay the Google Storage's standard rates for outbound data transfer, which is fine. You may have to minimize your charges, so you could ensure that you choose a region for your import job that overlaps with your bucket configuration. And so there's ways that you can import your regions for this kind of data transfer. And so you may have to pay outbound rates for outbound data transfer as well. So if you can run an export job in a region that does not overlap with the Spanner instance configuration, you can pay the standard rates there for that. And that is what we want to talk about when we're talking about pricing, specifically for moving data within multi-regions, and exactly how much it costs to store data for backup and applications in Google Cloud. In this video, I'm going to identify some common issues and problems that can arise when we're working with Cloud SQL and how we can actually troubleshoot them. So troubleshooting Cloud SQL connection issues is really the main purpose of this kind of slide here. One of the major problems that I've seen is where we're unable to connect to the actual Cloud SQL server, and this is actually coming because we're working with a private internet protocol or some type of private IP address. And so sometimes what you'll notice is that if we're hosting this Cloud SQL on a private subnet, there's no outside connection that can be made. And so you might want to make sure that your public IP address is listed as an authorized network, and make sure that your SSL and TLS certificates are up to date. And those are really going to fix the issues that you're going to be having when it comes to be able to connect to these Cloud SQL connections. Now, it also comes down, now, let's say that you're able to connect, you're able to get to the actual server, you're not being blocked by some type of IP address configuration or some firewall or anything like that. That's great, but now you may have authorization issues. And so this is where we'll end up using like our Cloud SQL auth proxy. So if we're using this auth proxy, we want to check to see if it's up to date. Is it even running? Those are kind of the things that I check first. Check to see if the instance connection name is formed correctly. And that's really those things that you want to check to make sure that the proxy is running, it's up to date, and you have your connection name configured properly. And really, it gets down to Cloud SQL connectors as well, and language-specific code. So, I've had issues where I've not formatted the connection string properly to the database. That happens. And so I can compare the code with my sample code for a programming language and see exactly how those connections are formed, and then just mimic those things. But sometimes I'll even use a self-managed secure sockets layer, or SSL, or transport layer security, or TLS certificates. So then this is where I have to make sure that the client certificate is installed on the source machine, and is the client certificate spelled correctly in the connection arguments, and then I can see if the client certificate is still valid, that kind of stuff. And that really just comes down to troubleshooting where I got the certificates from, more than it actually comes down to the machine that's actually being running on. But I've seen this block connections and prevent authorizations. Authorized networks is important. I want to make sure that the source IP address is authorized to be on the network, and I can try to see if there's an unsupported IP address somewhere, and then this is what's going to also prevent my connections. Any further connection failures, you might want to check with your administrator. So are you even authorized to connect? Do you have the permissions for this? Are you seeing what's called a connection limit errors? Maybe that there's too many people able to connect to the system at the same time. Is your application even closing connections properly? Sometimes we just are taking up too many connections in the pool, and then we're just unable to connect because all the connections are being used already. So those are just kind of the troubleshooting steps I go when it comes to authorization issues. But now that we've got authorizations properly managed, the next thing I check is authentication. So authorization and authentication is a little bit different. Authorization is checking to see if we are who we are. Authenticating is seeing, or I guess I should say authenticating is checking to see who we are. So we're checking things like our username and password, whereas authorization is we're trying to see if we're even authorized to perform a certain action. So in this case, what we're trying to do here is we're saying this is a native database authentication. So we'll have things like our username or password. Am I seeing some type of access denied errors? Am I even typing the correct username and password? Those kind of things. And if I'm using IAM database authentication, I have to make sure that I'm enabling the cloud SQL.IAM authentication flag on the instance so that it knows that I'm not going to be providing a username and password. Instead, I'm going to be providing my Google account so that I'm able to connect to it. I can add a policy binding for this account. So there's a few different things that I can do, but really with IAM database authentication, all you have to do is just enable the cloud SQL.IAM authentication flag on the instance, and you'll be able to connect to the system. There's some more common connectivity issues that I want to discuss. So we've got things like connections closing properly. So this is really important. So I get to verify that the application is closing connections properly. I see that there might be expired certificates. So sometimes these SSL certificates do expire, and so you have to rotate them. And you'll also see that there's connection authorization issues. So again, you have to make sure that you're authorized to connect. And so if you're having trouble connecting using an IP address, for example, make sure you're connecting from an on-premises environment with a MySQL client. That'll make sure that your IP address matches something that you're supposed to be. Otherwise, they usually don't. Typically, these cloud SQL engines, if depending on the administrator and what's actually being stored in them, they're not going to be open to people outside a certain network. So you have to make sure that you're connected to a VPN to have the correct IP address, and then send that over into cloud and use that IP address to connect to Cloud SQL. So that's really the important thing. Another thing is that check your connection methods. Not all connection methods will be enabled depending on the administrator and how they're set up. So you want to verify how you're connecting. So if you're getting an error saying like access denied for a user, when you connect, you have to make sure that you're verifying a password, all these things. So this is really how we check these things properly, is that there's going to be a connection method that's going to be preferred and secure, and you should be in accordance with that. Connection initiation method is important. You can see information about your current connections by connecting to your database and running like a few different commands like this. You can actually see a process list in your database to see, okay, exactly how am I connecting? What is the initiation method? And I can see an IP address as well to see exactly what's being done. So if they're originating from something like a Cloud SQL auth proxy, or if they originate from an app engine, all these things will affect, you get to check the connection initiation method. Now, there are connection limits. So, for Cloud SQL instances, there are connection size and app engine specific limits in place. And so you can check those things out on the Google Cloud quotas and limits page, and they'll explain to you how those connection limits are set up. You can raise them, but you would have to speak to an account manager to sort of get those temporarily raised if need be for your specific use case. A couple more steps that I would use to troubleshoot Cloud SQL instances. So make sure that you're having the correct backups in place. Keep the number of tables to a reasonable number, and that's really important. And then you'll also have proper import and export procedures. So you can use things like the MySQL dump utility. If you're using MySQL, Postgres has its own one as well called PG dump. And so you can use this import export feature to transfer data using a cloud storage bucket. I like to manage the disk space properly. So if my instance is reaching the maximum storage amount allowed, what you'll notice is that write to the databases will fail. So if you delete data, for example, by dropping a table, the space freed is not reflected in the reported storage used of the instance. So what I recommend you do in this case is vertically scale and add more size. So reaching the maximum storage limit can also cause the instance to get stuck and restart. So you really want to manage those things and have proper alerts in place. So as your disk is turning to full, you should have some procedure to start removing data or archiving data or vertically scaling the machine. Data corruption is important. So this is something that we have to manage properly. So in MySQL, using generated columns might result in data corruption, so I avoid those if I'm using MySQL. I also make sure that I have things in a proper clean shutdown, so no new connections are sent to the instance and existing connections are ended. The amount of time a database has to shut down is usually capped to a certain minute, so you have to make sure it either shuts down gracefully or it's going to be forcefully stopped. And this can result in disk writes being aborted midway through, and that could lead to data corruption. So make sure that you have proper clean shutdowns in place. There's also something known as a suspend state. So what you'll notice is that there are various reasons why Cloud SQL may suspend an instance. So if you have billing issues, guess what they're going to do? They're not going to turn off the database completely, but they're just going to suspend it. They're just going to keep it in this state where nothing can connect to it. So if your credit card for the project's billing account has expired, the instance may be suspended, and you can check the billing information to figure that out. And so in that time, your database is basically kind of in this locked zone where you can't really do anything with it. So you have to resolve the billing issue. The instance will return to a runnable state within a few hours, and it's something I'd avoid if I can, because that is there's really a bit of an issue there. You're essentially without a database for a few hours, and that, especially for something like Cloud SQL, where you could be serving millions of users, it's not something you want to have. So again, troubleshooting some Cloud SQL performance issues, I always enable query logs. So this allows me to tune the performance of my queries. It also just allows me to see how the queries are performing, and then I can maybe add some more indexes in certain places or change the structure of certain things. So basically, as I see what's being done with the database, I can identify the pain points and how the database is designed and maybe add a few things to enable things properly. And then there's the enable lock monitoring. And this is really important so that I'm checking to see in performance tuning, when we refer to a lock, is if there's two queries that are trying to update the same record in a table, they could potentially lock each other, as in each query is waiting for the other query to finish, but no one is doing anything. And so that when they're in that kind of lock state, nothing can be done to that record, and it can start to create some latency in our data sets. You'll also see that MySQL uses what's known as the performance schema, and this is a feature for monitoring MySQL server execution at a really low level. It's really accessible to consume stats generated in our performance schema, and there's ways that we can actually just query this performance schema and see how our queries are performing in the database. And I always recommend that we keep a small number of database tables. Database tables consume system resources, so the more that you have, the bigger the CPU you're going to need, the more memory you're going to need, and the more money it's going to cost. So I would keep the databases to be very small for this. Again, some more performance tips. If you're having slow inserts, updates, and deletes, make sure that you're checking your locations properly. And so what I mean for this is check the locations of the writer and database. Sending data a long distance introduces latency. So make sure that you're not doing any type of cross-regional insertion. If I live in the States and I try to do this insert or update or delete in a database that's in Tokyo, that's a long ways away. It's going to take a while for that data to show up inside the database. For slow queries, I recommend that you also check your RAM and CPU usage. So this is important for this. If your workload consists of CPU-intensive queries, such as sorting and regular expressions and really just complicated functions, you might be throttled, so you might have to increase the CPUs and the RAM as well. I would also check the database and reader locations in general. Make sure that your reader and locations they make sense, so that if I'm going to be connecting to a database, that's going to be close by geographically to reduce that latency. And of course, this is just in general, no matter what database we use, we want to make sure that we're using indexes, reducing our scanned data, and just avoiding round trips in our data. So we have to make sure that I'm properly designing the database with those principles in mind that we've always used to design local database or on-premise database. So that's just a little bit about Cloud SQL performance tips and some troubleshooting when it comes to authentication and authorization. In this video, I'm going to identify some common issues that can arise with Cloud Spanner and how we can troubleshoot them. So Cloud Spanner or performance regression really just comes down to identifying the query speed changes. We want to be able to detect them as soon as possible. So if we're working with PostgreSQL, when our SQL queries look up data, Spanner is going to automatically use the secondary indexes that are likely to help retrieve the data more efficiently. And in those cases, the indexes will cause the queries to be slower, but not all cases. So you might notice that some queries run more slowly than they ran in the past. So what we want to do in this case is just identify when those queries are starting to change, those speeds are starting to dip. And when this happens, I recommend that we review the schema, and this is going to make things a little bit easier. So this involves how my data is actually laid out in the database and, significantly changing a large amount of existing data that has a secondary index by adding, changing, or dropping a secondary index. I can use several different tools to identify a specific query that's executing more slowly than the usual, such as query insights and query statistics. But then once I find what those things are, I can review the schema and I can see that, hey, this query is slowing things down. It was fast to start, now it's slowed down. I can look at the SQL statement for the query and identify the tables and the statement uses and the columns that it retrieves from those tables. And then I can find those secondary indexes that exist for those tables, determine whether any of those indexes include the columns I'm even querying, which means that Spanner might use one of those indexes to process the query. But if they are applicable indexes, the next step is to find the index that Spanner used for the query, and this is where I have to use the explain, can actually dig a little bit inside of the query that's being done, and I can identify, once I figure out from my SQL statements, my investigations, I can see, hey, this query used this index. Now all I need to do is go ahead and remove the index or change how the index is structured by reviewing its schema. And that's really the kind of the main piece that you do for those kind of performance regressions. Again, they don't always happen, but I'd always have some tool in place to start to identify when those query speeds are changing. Okay, so Cloud Spanner request and transaction tags are important. So we'll have things like query statistics. So I'll have built-in tables that keep many statistics for queries, such as the data manipulation language statements. Those are the ones that are going to use the most CPU and all queries in aggregate. So that's going to be there for me. I'll also have things like read statistics, which are important. Read statistics just tells me I can retrieve statistics from any type of read operations I've done using these SQL statements. And then there's also transaction statistics. So if I have something to query, read, and identify how these transactions are being done, Spanner will provide built-in tables that store statistics specifically about a transaction, and I can query a table called spanner_sys.txn_stats. And those are going to retrieve all of the transactions that I've done. And then I can also look at something really important when it comes to troubleshooting, and that's lock statistics. So it can enable to identify the row and table columns that were the main sources of transaction log conflicts in our database during a particular time period. And I can retrieve these statistics from the log stats table that's all built into Spanner. So each of them have their own statistics tables that I can query. And so one of them is called read stats, TXN stats for transaction stats, and there's lock stats for lock statistics, and there's even query stats for query statistics in general. So that is really the main piece here for all of our Cloud Spanner logging. Now I'm starting to see that there's a latency issue. How do I even begin to diagnose it? Well, to diagnose a latency issue, you want to look at an instance's latency metrics. So I can use the Google Cloud Console there, and I can examine the metrics more closely and find correlations between latency and other metrics using the cloud monitoring tools. And so I can have high total latency with low spanner latency, and this means that it has higher than expected, but the latency is higher than expected, but the latency metrics for Spanner are significantly lower than the total end-to-end latency. So there might be an issue in the application code in that situation. But we can also have it high total latency and high Spanner latency in this case. And this means that the instance needs more compute capacity. So if my instance does not have a high enough CPU resources and its CPU utilization exceeds the recommended maximum, then Spanner might not be able to process our request quickly and efficiently. You also see that Cloud Spanner query index operators. And so this is where we'll have things like our table scans or our index scans, and we'll even have things like cross-apply scans. So a table scan operator indicates that Spanner did not use a secondary index, and an index scan operator indicates that Spanner uses a secondary index when it processes the query. And then you'll see that there's a cross-apply operator where in some cases Spanner uses an index that contains only some of the columns that the query selects, but as a result, Spanner must join the index with the base table, and so we call this a cross-apply index. And this is really important when it comes to understanding the query plans, because if I'm using an index scan or a table scan or a cross-apply scan, I can figure out exactly how to create proper indexes so that I can speed up the queries. Now, Cloud Spanner deadline exceeded error investigations. Again, this is a data access API issue. So that's one of these problems I could have is that I just don't have access for this kind of deadline exceeded error. Now, when I refer to a deadline exceeded error, just so everyone's on the same page here, when I'm using a Spanner client library, I'm using things like deadline enforcement. So deadlines allow our application to specify how long it is willing to wait for a request to complete before the request is terminated with the deadline exceeded error. So if I'm having a deadline exceeded error, it means that the system took way too long to retrieve an information. It's basically a timeout. And so one cause for this is, we've seen this before, is that we have data access API issues where the API itself is not performant properly. I'll even have data API issues where I'm able to access the API, but the data API is taking too long to retrieve the information. You'll also have administrator API issues as well, where you may not have access to certain endpoints, and that causes some delay. And then you'll also see that there's some Google Cloud Console issues as well. And you'll also possibly see some data flow issues if you're trying to use data flow for this kind of retrieval of information from Cloud Spanner. So what I recommend we do here is we look at the error codes. So Cloud Spanner error codes and error handling is crucial for these kind of things. What we're talking about here is we're talking about either aborted operations, and this is typically due to concurrency issues such as a sequencer check failure or transaction abort. So this is, that sometimes happens. So you'll see that the request could be conflicted with another request, and that could be an issue for that. I recommend for a non-transactional commit, I retry the request or structure the entities to reduce contention. And there's sometimes if I'm trying to insert something or something already exists, so if I'm trying to create a table and it already exists, the entity that a client attempted to create already exists. So if I'm creating a table with the same name, I shouldn't do that. If I'm trying to create another column with
the same name. I should not be allowed to do that. Canceled means that the operation was canceled, typically by the caller. It's perfectly fine. It just means that we could retry the operation. Deadline exceeded is basically a timeout. It means that the deadline expired before the operation could complete. And so sometimes you want to check to see if the deadline is sufficient. So using a deadline corresponding to the actual time in which a response is useful is really important. And that comes from understanding our statistics pages from earlier. There are some more error codes and error handlings that I want to discuss here. So we've got things like failed precondition, and we'll have things like the internal error as well. So failed precondition, the operation was rejected because a precondition for the request was not met. So either the message field in the error response provides information about the precondition that failed. So it's not always happen. It depends on how the table is set up. But one possible cause is running a query that requires an index, but the index isn't defined. That could happen. An internal one means that the server returned an error. So this is like our server 500 errors from our APIs. So some invariants expected by the underlying system have been broken. I wouldn't retry unless you understand the specific circumstances and cause of the error, because you could be breaking something. An invalid argument. So the client specified an invalid value. So for example, the message field in the error response provides information as to why it was invalid. I would not retry without fixing the problem first. Could be wasting some time or breaking something. And then not found indicates that some requested entity, such as updating an entity or querying a table or column, but doesn't exist. So either some data is missing or you've misspelled something. So I would check that as well. This is known as an out of range error. This operation was attempted past the valid range of our data. So this means that if I'm trying to request data over a certain period and I can't do an operation outside of that range, I'll get an out of range error. Permission denied error is pretty self-explanatory. It just means that the user is not authorized to make the request. You'll also have something known as resource exhausted. So some resource has been exhausted, and this can sometimes happen as well. As this could mean that the file system is completely out of space. So if I'm trying to insert data, I want to make sure that I didn't exceed my spanner or project quota. So I would not retry this query if you have a resource exhausted error code. Unauthenticated just means that the request does not have valid authentication credentials for the operation. So I would mean that you would have to re-log in or re-authenticate with the proper keys to make sure that you're able to connect to the instance. A couple last few error codes that I want to discuss. One of them is known as unavailable. This means that the server is currently unavailable, and this could be for a wide variety of reasons. Either it's still being brought up, it's there, but it's not ready for connections, so it'll return an unavailable. You'll see unauthenticated as well. This request does not have a valid authentication credentials, and you'll also see an unknown server. And this sometimes means that we just returned an unknown error. Errors raised by APIs that do not return enough error information may be converted to this error, and I would check that your request is safe and then retry with what's known as exponential backoff if you got this. It's really scary to see an unknown error here because it could be anything. So I would make sure that you know exactly what's causing this error before running the query again. So those are just some of the error codes that you'll see in Cloud Spanner, and as well as what to do when we are working with indexes in Cloud Spanner. So in this course, we've examined how to design and manage resilient structured relational databases using Cloud SQL and Spanner with a focus on cost control, migration, and availability. We did this by exploring Cloud SQL additions, core management tasks, provisioning instances, and creating databases in high availability, recovering from failure, migrating to Google Cloud SQL and Google Cloud Spanner, provisioning a Spanner instance database schema, defining Cloud Spanner schema and adding data, pricing out structured data services, and troubleshooting Cloud SQL and Cloud Spanner. In our next course, we'll move on to explore how to design and manage resilient NoSQL databases using Firebase services or Google Cloud Bigtable,
with a focus on cost control, migration, and availability. When is a car not a car? When it turns into a driveway. When is a database not a database? When it's a NoSQL database. In this course, I'll explore the practical applications of Firebase within the Google Cloud ecosystem, starting with the identification of use cases for Firebase and its integration with Google Cloud services. I'll then delve into the Firebase real-time database, learning to establish, configure, and populate it with data. After that, I'll shift focus to Firestore, guiding learners through the creation of a data model for storing document-centric data and setting up a Firestore database. I'll finish up by uncovering the NoSQL Google Cloud Bigtable, including schema design best practices, instance setup, and the intricacies of creating new tables, equipping students with the knowledge to effectively implement and manage NoSQL databases in real-world scenarios. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, we're going to identify the use case for using Firebase and describe its relationship to Google Cloud services. Let's first understand that the Firebase development platform consists of three main pieces. We want to be able to build our information, build our applications, and we want to be able to release and monitor the system that's being built and deployed. And finally, we want to be able to engage, meaning that we take our monitoring and releases and we identify things that can be changing and then iterate on the build process over and over again so that we can actually have some type of life cycle management of our data sets and our applications. But basically, this is what the Firebase development platform consists of. There's these three things that we want to do is in terms of build, release and monitor, and engage to identify some changes that could be made to the application. There are some Firebase build products that I want to discuss. Some of them include things called the Cloud Firestore. This is great if you're trying to build serverless or secure apps for a global scale. You can store app data in the cloud, and you can even sync data across online and offline devices and retrieve it with some queries. And there's also a real-time database as well. So I can build serverless apps by storing and syncing things like JSON data between the users in near real time. And this all can be done online or offline, and it has very good user-based security. You'll also see that there's a remote configuration available, where I can set up feature flags during prototyping and development, so I can dynamically control and optimize the user experience in the production. Firebase extensions are also available, so I can add functionality to my apps, and these come prepackaged open source bundles of code that I can just immediately import and start using with my applications. Now, the Firebase build projects include a couple different steps. So there's the app check. This is used to help protect our app from things like abuse by testing it from incoming traffic so that our app is able to block traffic without valid credentials. This is just so we have an extra layer of security around our application. Cloud functions are very useful here. We can run and write the app logic server side without needing to set up our own servers. So they're actually just our serverless cloud functions that behave to actually do the heavy lifting for the application. So this is where all of our app logic will live in these separate serverless functions that we call. And authentication is actually done for us as well. I can add an end-to-end identity solution to my applications for easy user authentication. I can even have things like sign-in and onboarding in just a few lines of code. And then there's things like cloud messaging, where I can get infrastructure to reliably send and receive push messages between the server and the devices across platforms at really no cost. So it's actually great to build a front-end application with very little back-end knowledge, and using some of these services that are available, we can just end up taking something off the shelf and have our cloud functions and authentication and cloud messaging all done for us. Now, when we build our projects, what we're doing here is we're actually hosting. So it's going to deploy some fast-loading, secure websites, and they have things like a global content delivery network or CDN, and we don't have to worry about setting up this CDN. It's all set up for us. Handles things like cloud storage as well for file storage, so you can store and serve user-generated content
with ease as our app grows. And you can go directly from prototype to production-ready cloud storage very quickly. It's very easy to do. And not only this include hosting and cloud storage, but it has something known as Firebase machine learning. And this is in its beta stage. So not only can we store information inside of these servers, but we can actually add some machine learning features to our applications with their ready-to-use APIs and support for custom model deployment. And these are just machine learning models that have been pre-configured and trained to do certain things and actions. So there's one for a few different use cases. You can actually have this sit on top of your data store, and you can actually make some predictions off of it depending on what the data is and what you're trying to do with it. Interesting enough is that when we have a release and monitor our products, we have a whole suite of tools to help us monitor the products in Firebase. So Crashlytics allows us to track, prioritize, and fix what's known as stability issues that erode our app quality in real time. So as soon as one crash happens somewhere, we get the logs for it, and we can actually visualize the logs and see what's going on. Google Analytics is used to monitor user acquisition and feature adoption metrics. So as we launch our app with free and unlimited app analytics, we can actually try and predict what's the next thing we should be building for our application based on how the users are using the application. And performance monitoring, it allows us to get insight into the app's performance, and we can address issues quickly, such as a spike in CPU or memory usage. Then we might need to vertically scale some machines. Test Lab. So this is so we can spot errors before release by testing and validating the app on physical and virtual devices, and it simulates actual environments as well. And you'll notice that app distribution allows developers to send what's known as a pre-release version of their applications to trusted testers from the console or using command line tools. And we can manage all of our testers in one place before we actually deploy this thing to products. Let's take a look here at our Firebase engagement. So there's also engagement products that are available. So this is known as remote configuration. This allows us to control and change our app to optimize the things like our user experience. And we don't even have to release a new version of our application. We can actually just have some type of configuration file and change them on the fly to see how the application will change. There's also an A/B testing. Now this is in beta. You can run experiments to test ideas and learn how they impact key metrics. So, if I change the color of a button from green to red, how does this impact a certain metric, such as the user engagement score that you come up with, something like that, some KPI that you're tracking. So you can have half your users see a green, half your users see a red, and see exactly, okay, well, what happens here? Is there a statistical difference between these two things that we're doing? And then there's the in-app messaging beta. So you can actually encourage your users to complete key in-app actions with targeted and contextual messages. And that's all done through Firebase. Again, this is in beta, but they're always adding new features to the engagement step for Firebase. Now, Firebase security is important as well. We have things just as you might expect, a role-based access control system, Firebase user role-based access control, or RBAC. It gives granular control over who can access the application data. We also have data encryption for at-rest and in-transit data. So all of our data is going to be encrypted with Google's encryption policies. And we have what's known as audit logging. So I can see who's accessing my data and when. So I can track who has accessed application data and then be sure to make sure that I'm not violating any type of compliance measures. So that's a little bit about the Firebase ecosystem that's involved in Google Cloud. In this video, we're going to identify the key use cases for implementing the Firebase real-time database. So real-time database is just a classic Firebase JSON database. So this is great for applications when you have very simple data models and they just require simple lookups and low latency synchronization. And so you don't really need to scale anything. So this is where we'd use a real-time database. So real-time syncing is great for JSON data. So this is all cloud-hosted NoSQL database that's allowed for us. And it has a multi-device collaboration suite for this. So I can use this on multiple devices, whether that's mobile, laptop, or whatever. I can use anything I want. And what I noticed is that there's serverless app development that's available. This is where we'd use the Firebase real-time database for this. And this is great for
real-time database that will ship with mobile and web software development kits, so I can build apps without the need of any type of server. And so I can execute backend code that responds to events triggered by the database using things like cloud functions for Firebase. And I'll have offline use optimization. So when my users go offline, the real-time database SDKs are actually going to use what's known as a local cache on the actual device to serve and store those changes. And then when the device comes back online, this is the interesting thing, the local data is then going to be automatically synchronized from the device that they were using it on to the serverless system. And then the Firebase authentication is all built in. So, you're going to have strong real-time user-based security. And so this is going to provide us some intuitive authentication for our developers. It's actually very simple to use. Just a few commands in the SDK will get you authenticated, and it's very easy to get set up. So the few different capabilities that I want to discuss, one of them is the fact that this is a real-time data synchronization. So we're going to be using data synchronization instead of standard HTTP requests. This way, any connected device will receive the updates within milliseconds. So it doesn't even think about network code or network calls or anything like that. It provides collaborative and immersive experiences between the real-time database and the server, hence making it real-time. So then there's the offline data persistence that's important. These persist our data to the disk. And for this reason, these Firebase applications will remain responsive even when they're offline. So the client device will receive the missed changes once connectivity is reestablished. And then you'll see that client device database access is very useful. So you don't even need to have an application server to access the Firebase real-time database. I can access it directly from a mobile device or even a web browser. In fact, some validation and security are available through the whole Firebase real-time database security system. And these expressions are executed when the data is even read or written. And this can actually scale very well. It has multi-database scaling. So if you're on the Blaze pricing plan, they can support some type of data needs for the application that we're working in. So this allows us to split our data across multiple database instances in a single Firebase project. This allows us to streamline things like authentication with Firebase authentication. And it controls access to data in each database with some custom real-time database rules for each database instance that we're working with. It has a very large JSON tree as well. So this will store data as one large JSON tree. It's actually very simple data, and it's very easy to store. It's not very high dimensional in any way, so this is what we'd use. And it's not suited for things like hierarchical data. So complex hierarchical data is harder to organize at scale. And these hierarchies where some data points would be related to one another is not something that I would recommend using this system for. So Firebase real-time database support, you'll have the Apple and Android offline support. So you can actually have a mobile first real-time SDKs that both support local data storage for offline ready apps. And you can have a presence functionality that's available. So it can be useful when a client is online or offline. You'll have real-time databases that can record client connection status and provide updates every time the client's connection state changes. There's also things like deep queries. So I can sort or filter on a property and queries can do this kind of sorting or filtering on any properties, but they can't sort and filter. They have to either filter or sort. It's a little strange, but you can create some default deep queries and they will always return the entire subtree that we're working with in our data set. So this is known as granular data access that's available. So you can access data at granularity down to the individual leaf node values in the JSON tree, but you just have to be able to be specific on what you're looking for. And so these things, the indexes are not required, but the performance of certain queries degrades as our data set grows without them. So it's something to think about when we're creating our real-time database for this. So Firebase real-time database reliability and uptime. So again, we have a regional solution, so available in regional configurations. This is when we're actually going to be using this real-time database. They're limited to zonal availability within a region. You'll have the extremely low latency, though, with typical response times no greater than 10 milliseconds. So this is great for frequent state syncing that you're working with in your application. You can even read more about these reads on their Google Cloud webpage there explaining this, but you'll notice that their high uptime performance. In fact, like the typical uptime is 99.95%. That's their service level agreement. Again, you can read this on the Google Cloud. The Firebase documentation there explaining what their SLA is for this, but it's 99.95%, which is pretty good for a real-time database like this. Now, the interesting thing is that there's scalability options that we can use. So scaling is obviously going to require, performance, right? So one thing that we do is we use sharding, and this is required for our scaling process. So sharding just involves splitting up our database into multiple pieces and having, instead of one database, we'd have 4 databases with sections of our data in each piece. And there's no local rate limits for each of these to individual piece of data. So you can write as many times as you want. Again, great for the real-time syncing portion. And again, security is paramount with any of these data stores. And so Firebase real-time database security will separate the authorization and the validation steps. You'll see that it will have read-write rules cascading. And so this will separate this kind of authorization and validation because we're using these kind of read-write rules cascade. And you can even have some type of data validated that's separately. So you can validate data separately using the validation rule. So that's a little bit about the Firebase real-time database security. In this video, I'm going to show you how we can actually set up a real-time database. So what we want to do is go to the left side of our page. When we get to the console.firebase.google.com website, we're going to select our Google Cloud project that we already have signed up. And what we want to do is go to the left side and click All Products. Now in here, in the All Products page, you'll see that there's different ones, such as for building our application. There's all these products that helps us build, including things like hosting and machine learning. There's things like running, so I can optimize my application. So we'll have things like A/B testing, cloud messaging, app distribution, all sorts of things are there with the running and analytics step. Now what we want to do is actually just get to the build step, and there will be a section that should say for our database. So right here, you'll see that there's a real-time database option. If we scroll down and click this one, this is allowing us to store and sync data in real time. That's exactly what we're looking to do. So we're going to click this real-time database page, and we're going to be met with this page. Now, what I want to do is go ahead and click Create Database. Now, in the Create Database window, we are going to choose a database location. In this case, I'm going to keep it as US Central 1, but there are a few different locations that are available, such as Asia Southeast 1, Europe West 1, and US Central 1. For now, I'll just leave it at US Central 1, and we're going to go ahead and click Next. Now, there's a few different ways that we can actually get this to start. So I can start it in test mode or locked mode. Test mode just allows anyone with our database URL to read and write data, which is useful for development, but I wouldn't recommend this for production. For now, let's go ahead and do it in test mode just to get started, just to sort of get this to work. And so then I'll go ahead and click Enable. And now we're met with this page. Okay, so now that's pretty much it. Our real-time database is ready to go. We can even add data manually. So in our Firebase console, I can manually add data to our real-time database. We're going to click our Data tab. And what I want to do in this case is use the plus add child button that we're going to be seeing here. So the plus add child button is going to be right there. So see this little plus icon. So this is our root for our data. If I click this little plus button, this is where we're going to add our child, and our child is going to be our key value store. And this is where we're going to add new nodes, and I can enter the data directly in the Firebase console. So now I can have, my name, for example. I can have a key value of name. Let's have Elias as this, and so you can see it's already thinking of a string. We'll go ahead and add that. We can also add another child here. Let's go age, and let's enter, 29. And so we click add here. So there you go. So you see here, this is the age and the name that's associated with this name. And so this is data. This is how we can manually add our data, and we can remove our data by clicking the little trash icon, and this will actually delete our data this way. We can also do the same thing for our name, and you can see, so doing so will permanently delete the data at this location, including all nested data. And we can just go ahead and click delete, and it'll just take a second for it to actually disappear, as you saw. And this is just a way for us to actually manually add information and remove information. And that's pretty much all we have to do. And that's how we can add data. And if you want, you can actually go into our rules sections. You can see here that this is just testing. For example, a basic rule allowing read and write access to all authenticated users. So you could maybe change this now that you're happy with the testing. I would actually recommend that you change this to say things like auth does not equal null, to make sure that you have to be authenticated. So I like to put this in a JSON. So I'll put double quotes, auth does not equal null, like so. And then I will just take the same string and make sure that this is done so here for the write. So this makes sure that you have to be authenticated to be able to read and write from this information. And so once you're happy with that, let's just get rid of some of these comments in this JSON field. We can go ahead and click publish up at the top left. And then you could say your security rules are not secure. Any authenticated user can steal, modify, or delete data in your database. No problem. Just click dismiss for now. And that's good for our testing purposes. And that's pretty much how we can handle our data. And that is the real-time database. So we got set up with a database in just a few minutes. In this video, I'm going to identify the key use cases for implementing the Firestore service. So let's go ahead and talk a little bit about indexed or NoSQL with Firestore. So Firestore is just a powerful, fully managed NoSQL document database. This means that it's just designed specifically for mobile and web app development, and it doesn't use any SQL syntax, or such as joins, to retrieve the information. Now, a document database is just, think of them as JSONs, some type of key value pairs with fields and values inside of them so that we can actually retrieve them on the entity that we're working with. This allows us to have some flexibility and scalability for diverse unstructured data types. And the integrated with other Firebase and Google Cloud Platform products so that I can actually use this NoSQL with Firestore just about any Google Cloud product I have. And so NoSQL databases will handle these unstructured data effectively across all of our platforms. Here are some capabilities that I want to discuss. Like I said, it has a flexible data model. So the flexibility that the Cloud Firestore data model supports, hierarchical data structures, so I can store data in documents, which are organized into collections. So documents can contain things like nested objects in addition to sub-collections. You'll have things that are powerful query features. So I can use queries to retrieve individual specific documents or to retrieve all the documents in a collection that match the query parameters. There's even things such as with real-time data synchronization. So I'll have real-time updates when the system is online or offline. This comes with the offline data support. So like real-time databases, you'll see that Cloud Firestore will use data synchronizations to update any connected device, but it's also designed to make simple one-time fetch queries very efficiently. And the offline support comes when we're trying to cache data that our app is actively using, so the app can write, read, listen, and query any data, even if the device is offline. Now, when the device gets back online, what happens is that sync from the changes that was happening while it was offline is now going to be sent to the data store. And so this is where the real-time data synchronization comes into play. Another thing you'll see is that this is actually designed to scale, and it's using multi-region scalability. So Cloud Firestore will bring you the best of the Google Cloud's powerful infrastructure. So we'll have something like automatic multi-region data replication. You'll have strong consistency guarantees. You'll have ACID and atomic batch operations. And so we've designed these Cloud Firestore solutions that you're going to see in Google Cloud so that they can actually scale across the world in multiple regions all at the same time. Okay, so Cloud Firestore is actually very easy to use. It's really intuitive. It follows a logical data model. This is going to organize things in collections and documents for us. We'll have a multi-platform client-side software development kits, or SDKs. This allows me to actually use them in Python programming languages or JavaScript, for example, so I can actually import the libraries and start using those kind of SDKs. We'll have automatic authentication management for complex authentication and networking code that's actually all done. Another thing that the Cloud Firestore global scale and availability offers, such as multi-region data replication for durability and high availability. It offers automatic scaling. So as my traffic starts to increase, you know what that means? It means that we're going to actually scale our workloads according to the traffic. So if things, my CPU or something is getting hit too many times, so I need to start to vertically scale or horizontally scale something, the automatic scaling will come into play. And so the strong consistency for our data is important. So even if we have distributed environments, you're going to start seeing that the data changes are going to cascade to the nearest neighbors. And so this will give us consistency even in these distributed environments. Now there's a serverless development procedure that's here. So client-side authentication, such as our SDKs, will handle our authentication in our networking code. You'll have security rules and data access control for our validation. This is really important to make sure who can access the information that's stored in Firestore, so that's also available. And you'll see that there's direct mobile app connection. And this is without the need for additional server infrastructure. Now, the Cloud Firestore integration follows with other GCP products. So integration with Firebase authentication for user identification and management. That's what it also integrates with. You'll see that it integrates with Cloud Functions as well for running custom code in response to data changes that's happening within Firestore, such as an addition to a key value pair. And so then there's an additional GCP products that are available for comprehensive app development experience. So this is great if you're trying to use things like, for example, Google Storage to store some flat files in there. You can actually integrate with those products as well. Now there's offline support, and the way this actually is done is with local data caching for read, write, and query operations. So it'll actually take some data from the server and put it into our cell phone, or our device that we're using, and it actually will store the data locally, and then the device is then going to start modifying the data inside of the application, inside of the device. And so that's useful for that. And then this is where we'll have real-time data synchronization. So when the device comes back online, if it was offline, it has a local data copy on the device. And so it'll be making edits to that local copy. And then when the system's back online, we're actually going to synchronize all of our changes that we've made while the device was offline to the server so that the changes are synced with each other. And what's interesting here is that this is actually available on web, iOS, and Android platforms. And so this was going to give us this flexibility, scalability, and ease of use for all of these powerful features that are used on Google Firestore. And this is what's going to make it a very useful product for when we're trying to scale out our devices or our user base. Having Firestore will be great for those kind of scalability options. In this video, we're going to describe the process of building a data model to store the document-centric data of Firestore. So Cloud Firestore data model is just a NoSQL document-oriented database. So this is unlike an SQL database. In an SQL database, there are tables and rows, but here there's none of that. Instead, here we're storing in what's called documents. Now, documents are just organized into collections. So what is a document? Each document contains a set of key value pairs. So think of them almost like a JSON object if you think about them. They're very similar. So Cloud Firestore is optimized for storing these large collections of these documents. So if a document is like a JSON object, so maybe we'll have a person's name. A name would be a key. So my name would be Elias, so that would be a key value pair. Then it'll be maybe their age, their gender, and each of those would be their keys and then values for those parameters. And so all of that would be into one
document that's available, okay? So now if I take a bunch of those documents and store them together, I've got this thing called collections. And I can actually have documents that contain sub-collections and have nested objects. So I can even have a JSON within a JSON, and both of which can include things like primitive fields like strings or even complex objects like lists. And so the collections here are created implicitly inside of Cloud Firestore, and they assign data to a document within that collection. And again, we can also have sub-collections. So I can have a collection of data, and then inside of those, I'd have a sub-collection within that collection. And it's just a way for me to sort of separate and organize my data without using tables or rows. So the Firestore data model is the document, right? So documents consist of key value pairs, like we were saying before, and they support different data types. For example, we could have strings, we could have some type of blob. So like normally Firestore will support a variety of data types. So one of them is string. You'll have booleans, numbers. You can even have geopoints, which are lat long points, and even a binary blob and a timestamp that you can actually use. And this is all very lightweight JSON records. So that's kind of what this whole purpose of this document is. So for example, I could have somebody's first name as Mac, his last name Anthony. They're born in 1992. So first, last, born are the keys. The values are Mac, Anthony, and 1992. And that can have all sorts of things, right? So what if I wanted to have a complex nested document, right? I could have their first name, their last name, their year that they were born, and then an address. And that address is going to be its own JSON object. So that address will contain another key, which is house number, street number, zip code, all sorts of things. So you can almost see how these become nested. And so if we look at the model collections, right, we'll see that they contain documents. They're attached documents that can require unique names, and the documents should not contain other documents, which is important there. And you'll notice that collections are created before our documents are created. And then finally, collections only exist while they have documents. So you can't have an empty collection. They have to have some type of document in there. Okay, so that's how collections work. So let's go ahead and look at what exactly is a sub-collection. So a sub-collection is a way to store hierarchical data. So let's say there's a requirement to store data from a chat app. So you'll see that a chat app can contain chat messages and chat rooms, and you need to store them in some type of collection and rooms. So the correct way to store a message in this scenario is to use a sub-collection. So we'll start with an outer collection that's associated with specific documents, such as rooms. So inside of that one, I'll have document 1, which could be room A, and it'll have a name. And then inside of that document, there will be messages. And so messages is now nested inside of that room A with that name. So these would contain their own sub-collection that discusses messages. And this is where hierarchical data is stored in that sub-collection. Now, documents can contain sub-collections. There's nothing restricting you from that. But you'll notice that sub-collection is just a collection associated with specific documents. But there are certain rules you need to keep in mind while creating this sub-collection. So I can't reference the collection and documents in the collection. You can store hierarchical data in the sub-collection, making it easier to access our data. And you can have a sub-collection in documents in sub-collections, allowing us to nest the data even further. So it gets a little tricky to sort of talk about in words. So I think maybe a better thing we can do is actually try and visualize what's going on. So here's some hierarchical data. So we've got some room bookmark, which is rooms. And, and this is our bookmark rooms. So this is a collection called rooms to store different chat rooms. And inside of here, we'll see that there's a class, which is known as team room. And inside of that, it'll give us a name, which is the team chat room. And we do that again, and we know that, okay, this is going to be a hangout room. And so this is a name for a hangout chat room. And we continue doing this, and you can have a list of all of the rooms themselves. And so you'll see that we're getting a lot of different rooms here. And this is where we'll get our hierarchy of data. So once you have chat rooms, you have to decide how to store the messages. And so each room would have its own
key values pair, so it'll be messages, and then that will have its own hierarchy of data, where it's another object. So you can see how they can become nested. So let's go ahead and take a look at some lightweight object that points to a location in our database. That's the whole concept of our reference. So every document in Firestore is just this. It's a location within the database. And you can see that documents are uniquely identified by their reference in memory. So we can refer to our location. You can create a reference to it. And then references can be specified as a path. So I can go into chat room A, go into the team room, and then grab the messages and maybe go to the fourth message, and then that'll have a path. And so it looks like a file path almost to retrieve the information. And that's really how we're kind of retrieving information here with a NoSQL store. It's no longer using different tables and key value relations between them. We're actually just kind of nesting them into some type of tree structure, and then just kind of walking through the tree to get to the information that we need. And then that's how we can have a quick access with Firestore and the data model reference. So that's how Firestore works with collections and subcollections.
In this video, I'm going to show you how we can actually stand up a Firestore database, perform its initial configuration, and add some data to the system. So Firestore database is offered by the Firebase console that you can access by going to console.firebase.google.com. And this is where we're actually going to do all of our work with these Firebase projects. And what I want to do, you'll be met with the page when you reach here where you can either add a project or select a current project. I already have a project available, so I'm going to select the project here, and I'll be met with the page that looks like this. Now, this is all normal. It might show you if you have some information in your project already. As you can see, I've got some storage already accessed in my project. But on the left-hand side, if you scroll down, you should see a section that says Product Categories in the navigation menu. What we want to do is we want to click Build. And in this drop-down menu, we want to scroll down until we see Firestore Database. Go ahead and select Firestore Database, and you'll be met with a page that looks like this. Now, I already have some collections and data in its own database, so what I will do is create a brand new one, just for example. So I'll click and Add Database up at the top next to where it says Cloud File Store, and I'm going to just give it a database ID. Now, the database ID I'm going to say is going to call it example-database like this, and I'm going to select a single region location for this database. Now, the reason why I'm selecting a single region is because this is not going to be used in production, and in the interest of saving cost, I'm just going to use just US Central 1 for Iowa. And, if I was promoting this to production in any way, I choose something like one of the multi-regions that's available, so I have some fault tolerance and reduce latency to my end users. So we're going to go ahead and click Next on the bottom right of this little window. And then what you're going to see here is it's going to ask you for a starting mode for our database. Now, because we're in development and for an example mode, I will use test mode. This just allows us to keep the database open, and you must update your security rules within 30 days to enable long-term client read access. So this is fine for our purposes. I'd use production mode so that it has more security enabled. But in this case, since we're still in development, we can actually just keep it in test mode. So we're going to click Create on the bottom right, and it's going to provision our Cloud File Store database. Now, this could take a few minutes, but it's depending on how much traffic there is to the system. So now we're actually here on the example database, and you can switch between all of your databases if you have more than one by clicking the little drop down next to the name, and you can actually see default or example database. So I've just created it. Now remember, this is a collection. So what this means is I want to go ahead and create collections of data. So a collection just means that it's going to hold entities of data. So the parent path would be, root here, and I can give it a collection ID. So I can go ahead and give it employee, and I can click next here. And this is where I can have some document ID here. So what I'd like to do is enter a collection ID. So I've decided to call it employees, something like this. And this is what we're actually going to, I'll leave it singular for now. And I will go ahead and click my field name. I'm going to give it a string, or give it a field of name, keep it a string, and just keep the value to be John Doe. And then I'm going to add another field. Let's say I want to add position. So maybe I'll leave it all lowercase here. And this would be a string, and I could say manager, something like this. And this is all a document. So this would be someone's employee ID. So what I'll do here is I can say a collection must contain at least one document. This is document ID, so I'll call this employee 1, for example. So a document is contained inside of a collection. So this is the first employee. I'll give it this name, this position, all of the stuff. I'll go ahead and click Save here on the bottom right. And you can see right here, I've got in my collection, I have a whole bunch of documents called employees, where I can maybe add another employee. So maybe I'll add another one. I'll say employee 2, something like this. And I'll do the same kind of thing. I'll provide their field, which is their name. And let's call it Jane Doe. And let's also make her a manager. Like so. And so, as you can see here, this becomes a little bit easy to see. I have a collection of employees. Each one of them has a document ID. So we've got employee 1 with values of name and manager, and I can add different fields if I so choose to. And I can add another collection if I wanted to. For example, I can add a different collection ID. Let's call this department. Okay, here we go. And I'll give it a department ID of department 1. And we'll leave this one here as their name of the department. And we'll call this sales. And we'll leave that there. Okay, so that's one department. Maybe I want to add another department. And so I'll add a document here saying, call this department 2. And we'll give it another name. And we'll call this engineering. And we'll go ahead and click Save. And so now you can see what's happening here. I've got different departments, different collections with different documents. So every collection contains many documents. Every document can contain many fields. And I can edit each document's fields by adding as many fields as I want. And then I can even add its own sub-collection. So that's really important. So I can add another collection here underneath the employee 1, so it can have its own collection, and I'll give this collection ID something different. So I can have maybe direct reports, something like this. So let's go direct. I'll keep it snake case here, or camel case. So call this direct report. Go ahead, click next. Let's give this document ID. Let's call this port 1, and we'll give them a name. And we'll provide a string value, and we'll say, okay, their value is going to be, I don't know, Max. So that's their first name of the direct report. So now you can almost see that, okay, we've got a collection underneath employee 1 called the direct report. And this means that, okay, we can see, all right, these are all of the direct reports for employee 1. So you can almost see how this becomes nested inside of the Firestore. Now, employee 2 doesn't have any direct reports, so they don't have that collection. So employee 1 would have some direct reports, and I can have and maybe they keep hiring people for this employee 1 to manage, and then we can add different documents. So if I look into report 1, this is their name. There's all this information here, and this just helps us kind of keep this information nested. And you can almost see how this can be a tree-like system where I can actually have this cascade and change in many different ways. So when I need to retrieve all the information on employee 1, I'm not only retrieving their first name and their position, but I'm retrieving all of the direct report collection that's attached to employee 1. So this one-to-many relationship will also be retrieved when I query employee 1 from the employee collections. And so this makes it very useful because we don't actually have to write any SQL code to actually do any joins. can just attach the information in this tree-like system so that we can retrieve the information that we're looking for. And that's really it. That's really useful. So NoSQL is required to actually write this code, hence this NoSQL database. In this video, I'm going to show you how we can use the NoSQL Google Cloud Bigtable. So this service is a NoSQL fully managed database that's great for large analytical and operational workloads. This is great for applications that need high throughput and scalability with low latency, such as IoT, financial data analysis, and user analytics. The benefits of this is the fact that it's scalable, it has high performance with low latency and high throughput, and it integrates easily with other Google Cloud services like Dataflow, BigQuery, and it's really just a great thing, but it's meant for very large workloads. This is kind of the, I guess, almost the bigger brother of the Firestore, which is also a NoSQL database offered by Firebase, but this is actually used for very large workloads, much larger than what Firestore supports. And typically with Firestore, you can use the GUI, the actual console in Firebase, to actually add data, edit data, see what the information that's actually being stored in that system, what it looks like. But with this, you can't do that. There's no user-friendly way to actually use the console in any way to create some data or edit data. So it actually has to be done through, specifically on the SDKs, through a library such as Python or JavaScript, something that you can actually download. So you'll have to install like the Bigtable SDK through Google Cloud, either with a package manager with either Node or pip for Python. And just you'll be able to write your code there to actually insert our data, which is a bit of a process to do. But in this case, what I'll show you is actually how to create one of these instances and what the steps are to make one. So let's go ahead and go to our console.cloud.google.com, bring up our console here, and we're just going to search for Bigtable. Now you'll see that there's a icon that looks exactly like this, Bigtable here. I'm just going to click this and I'm going to be met with the page that looks like this. Now it might ask you to enable a Bigtable API. Go ahead and click enable to get started. That's just so that we have it enabled for our account and our project. But for right now, if you're met with this page after you've enabled it, go ahead and click create instance up at the top next to the word instances, and you are going to be met with a form. Now we're going to walk you through what you have to fill into the form. So the first thing I'll do is offer an instance name, and I'm just going to call it example-instance, like so. And I'm just going to leave it like that here. I'm going to click continue. I'm going to choose SSD for this, or HDD. Now I will choose HDD actually. There's a difference here between what we want to do. So if for SSD, this is great for lower latency and doing a lot of reads per second. This is used for real-time serving for production or use cases such as ad serving and mobile app recommendations, things where we really need the recommendations to be fast. Here, the high HDD is great for higher latency for random reads. They're good performance on scans, and they're typically used for batch analytics such as machine learning or data mining in itself. So go ahead and click continue here. And what we're going to do now is select a cluster. And this is where the ID is totally permanent. So we'll have example-instance-c1 for cluster 1. And this is where I can say that a cluster is supposed to just handle the application requests for all of our instances. And a cluster is going to contain one or more nodes, which are compute environments that's attached to this. Now, what's really important here is that I have to select a location for where this cluster will be. And typically, I can add more clusters later. And so for the first cluster I'm going to choose is I get to choose the location. Now, if I had a global application that I'm trying to serve all over the world, so you can imagine if I had something like Netflix or something like that, I would want to have these things spread across multiple regions. Multiple clusters will have their own regions that they can access. So this is important for that. But for now, I'm just going to select a region that's closest to me. I'm going to say, let's see here, there's a bunch of them here. I'm going to select US Central 1, Iowa, or US East 1, South Carolina. I'll just choose this one. and I'll select any zone for now. Now, what's important is I can choose a node scaling mode. So we've got things like a manual allocation to say, okay, I want one node. I can have an auto scaling node, and I can add or remove nodes at any time. So for now, I'll leave it as manual allocation so I can have one node with this system on this cluster. Let's say if I wanted to select auto scaling. Well, what does that look like? Well, this means that I have a minimum of one node or a maximum of 3 nodes in this example, and I can choose this to be whatever I'd like. So let's say I expect that there's going to be a high demand potentially, so I'll start off with one node, but if that node reaches a CPU utilization of about 60%, then I know that I need to add more so that it can scale to the traffic that I'm getting. Whether there's high traffic times, I'm going to start adding more nodes. And this costs a little bit more depending on the usage, but you can see if I scroll down, I can actually look at the storage utilization per target. So I can have it set to 8 terabytes per node. And really what I want to do is use just the manual allocation for now, just for the interest of an example. And this pretty much is it. This is how we can actually spin up our instance. If I click create here on the bottom left, it'll take a few minutes to actually create this system. And you can see that it's already starting to spin up. And after it's spun up, I can start downloading the tools for Python and start coding a solution to actually start inserting data into this system. In this video, I'm going to discuss a little bit about Bigtable and its schema design. So Bigtable is just a simple key value store for data, and it's not relational at all. So meaning that we're going to be leveraging the NoSQL system here. It does not support things like joins or transactions, are supported only within a single row. And one index per row key. So each table has only one index, the row key. There are no secondary indexes. Each row must be unique, so you can't have duplicate rows in a NoSQL table. And it's sorted lexicographically by row key. And so this means from the lowest to the highest byte string, and row keys are sorted in what's called a big endian byte order, and this is called a network byte order if you're familiar with it. This just means that the binary equivalent of alphabetical order. So then we've got things like column families are stored in no specific orders in any specific, and you have columns are grouped by family, and they're sorted in this order, this alphabetical order within the column family. So in a column family called sysmonitor with column qualifiers of processor name, I could have CPU first, then disk read, then ID, then memory. See how it's almost, it started with the percent sign, then it went with the D, then the I, then the M. It's all alphabetical order at this stage. So that's really how this works. Now what I'll do is look at a little bit further into the schema design. You've got things like your row and column intersections will contain multiple timestamped cells. So each cell will contain a unique version of the data of the row and the column. You'll have aggregate cells that contain in aggregate column families. So you can create column families that contain only aggregate cells, and aggregate lets you merge new data with data already in the cell. And then there's operations that are atomic at the row level, and so an operation affects either an entire row or none of the row. And reads and writes are evenly distributed, and so this is going to be evenly distributed across the row space of an entire table. And you'll have big tables that are sparse, and a column doesn't take up any space in a row, and it doesn't just use that column itself. Now, just to add more to this, so that there's big table schemas. These tables are better to store related data in a single table rather than multiple tables. And you can actually avoid creating a large number of tables with this. And so you have everything in just as low number of tables throughout the system. And this leads to better lifecycle management of our data. And so there's separate tables shouldn't be created for similar data. So if the data is related in any way, just chuck it all into one single entity. That's what these things are designed to do. Have one large table so you can actually read and write from it. Now there are some column families that I want to discuss. So you can add related columns in the same column family. So when a row contains multiple values that are related to one another, it's good practice to group the columns that contain those values. You can limit the column families per table to about 100. This is pretty important. Creating more than 100 column families may cause performance degradation in this system. I use short column names. Names are included in the data that is transferred for each request, so make sure that they're short for better performance. And you can consider data retention needs when adding columns to column families. So you'll have garbage collection policies that are set at the column family level, not at the column level. So you want to make sure that you keep the most recent version of a particular piece of data. Don't store it in a column family that is set to store 1,000 versions of something else. So it's just not really something you want to do. Okay, so big table schema. I just want to discuss a bit about columns. You can create as many as needed per table. Big tables are sparse, and there's no space penalty for a column that is not used in a row. You can have millions of columns in a table as long as no row exceeds the maximum limit of 256 megabytes per row. You're perfectly fine to have that. I like to minimize columns in a single row, and I treat the column qualifiers as data in themselves. So you'll have to store a column qualifier for every column. You can save space by naming the column with a value. So I can take a table that stores data about friendships in a friends column family, and then each row will represent a person and all their friendships. And then each column qualifier can be the ID of a friend, that kind of thing. That's usually how I handle that stuff. When it comes to big table schema rows, I keep the size of all my values in a single row under 100 megabytes as possible. And I add entity information to a single row. That's very useful for this. And then related entities should be stored in adjacent rows. That makes it really useful for this. And what I will say is that there is a bit of an exception. If you keep an entity in a single row, results in rows that are hundreds of megabytes, just split the data across multiple rows. Just make sure that they're next to each other. It's better for that. Now let's talk a little bit about, we've talked about the tables, we talked about the rows, we talked about the columns. What about the cells? Well, cells should store less than 10 megabytes of data, and the cell is just the data stored for a given row and column with a unique timestamp. And aggregate cells can store aggregate data. So if you only care about the aggregated values of events for an entity, such as, I don't know, the monthly sums of sales for every employee, you can use aggregates. And there's ways that we can actually do this inside of big tables, but aggregates are great for this kind of thing. Row keys. So these are the base keys on the queries that are used. And, we want to make sure that these row keys need to be short. You can't keep them long. So a very small row key is actually going to be better. I usually keep mine to be 4 kilobytes or less. Long row keys will take up additional memory and storage, and it'll increase the time it takes to get responses from the big table server. I use multiple delimited row key values in each row. So because the best way to query a big table efficiently is by what's known as the row key, and it's often useful to include multiple identifiers in your row key. And so when your row key includes multiple values, I usually just have a clear understanding of how that data is going to be used. Row key strings should be human readable, and that's something that I'd have with a delimiter, like some type of segment that I'll have. So I'll maybe use a colon, a slash, or a hash symbol, something like that. The first segment or set of this is the row prefix, and the last segment is the row key suffix. And you want to start your row keys with a common value. And so that's really all the things that I do. So for example, if I'm dealing with phone numbers, I want to have my row key say phone and then the hashtag symbol, and then a whole bunch of other stuff, like maybe some alphanumeric keys, and then another hashtag symbol and another alphanumeric keys. And so this is going to allow me to retrieve things such as device type, and I'll have more human readable information such as an ID for that device, and the last one could be like a user ID. And so this allows me to look at the device type, the device ID, and the user ID that's attached to that device, and then that could work. So that's just an example of how you want to handle these kind of keys. But really with Bigtable is that it's quite powerful if you just stick to these best practices on how to use it, and you'll get the most bang for your buck by using this service.
In this video, I'm going to show you how we can actually set up a big instance table and just what the steps are to actually create an instance. So provisioning a Bigtable instance, we have to use either the Cloud Shell and make sure that we have the CLI already set up. That's the recommended way to do it. Or you could do it directly in the console, but I find that with the command line interface, it's a little more straightforward to do. You just type a command and you're pretty much good to go. You want to make sure that you have a project that's already been created and you have it selected in the Google Cloud CLI or the console itself. Then what you're going to have to do is enable your billing or your API for the actual Bigtable service. And now that billing is enabled for our project, you have to enable Bigtable and the Bigtable admin APIs. And you can grant roles to the individual Google account to be able to actually navigate to Bigtable. I'm assuming that you're not using an administrator account to do this, which you should not do. You should actually do this to grant roles to those kind of Google accounts. And you want to be able to install the Cloud Bigtable components on top of that. So then those are the SDKs that are for the programming language that you're working with. So Python, Node, they all have their own. And that's primarily how you're going to send information and retrieve information to the Bigtable instance. There is actually no way to insert the data in the console. You'll have to actually use the CLI or some type of programming interface to actually send information for it, because this is meant for a very large-scale application. It's not like a user-friendly kind of way to actually insert data like we saw with Firestore. You're going to actually have to provision and create some code to actually do this insertion. Now, the Bigtable instance, there's a few different ways to actually provision our commands. Again, creating a project, here's command line tools to actually do so. You use gcloud projects, you've created your project directly in the CLI. You then select that existing project by going into the configuration, setting your project, choosing the project ID. Then what you can do is enable the Cloud Bigtable and Cloud Bigtable admin APIs. So this involves things like gcloud services to enable Bigtable and Google APIs. You can also enable the Bigtable admin.googleapis.com. So those are the actual APIs that you're enabling. You can just enable them both with a single command with the gcloud services enable, and then the URIs for both of those APIs will just need to be added. Here's how we can grant roles to our Google account, gcloud projects. We can add an IAM policy for this project and give it a member, which would be our user email address, and provide it a role. And then that's how we can give it the Bigtable API role. Then what I recommend you do is you install some of the CLI components, the CBT, which stands for Cloud Bigtable. This allows us to actually interface with Cloud Bigtable directly through gcloud. So you can actually do gcloud components, install CBT, and then you can use the CBT command line tool out of gcloud to interact with our instance. Here's how we can actually create the instance. So we want to make sure that we have an instance name and an ID. They have to be unique and human readable. We have to also select the SSD or HDD for the storage type. SSD is meant for quick retrieval, low latency, but they cost more. HDD is higher latency, but they cost less. Depending on what you're doing, if you're working with real-time analytics or you're looking for users that are going to be interacting with this instance, I recommend you use an SSD. But if this is for archival storage or something that you don't need to pay for that kind of low latency performance out of an SSD, I'd recommend going for HDD for the cost savings. You can configure the first cluster and then select the region for that cluster. You can always add clusters later on, but for now, the first one, you have to select the region. I recommend you select the region where your users are. And then you can choose things like scaling and encryption options, where you can say, okay, every cluster has 1 node minimum, 10 nodes maximum. You're free to scale between 1 and 10 nodes, depending on the traffic and how heavy each node is being used. So I can say that when one node is 60% utilizing the CPU by 60%, then I know, hey, I'm going to add another node to sort of decrease that load. And it's intelligent enough to scale up and scale down like that. Finally, once you have those options all selected, all you got to do is just create the instance and it's ready to go. So how do we connect to the Bigtable instance after it's created? Well, we can use the CLI, the CBT CLI, to use our project and our instance. And all we got to do is just, create a CBT-RC file and then send over the project variable with our project ID. So project is equal to project ID, and that's what you're seeing right here. You can also echo the instance name, which is the quick start -instance. Here's an example. That's what I called it. but you can actually call it anything you'd like. But that also goes into a special dot file for the CBTRC. And then what you're going to do is you're going to verify that the CBTRC file is correctly created and you will then be ready to go. So creating a big table is now going to be straightforward. Now, all I got to do is CBT, create table, the name of the table, and I called it temp-table. Then what you're going to do is you're going to list your tables, which is your CBTLS, and you should see your table that you've created. Now what I can do is I can add a column named CL1 very easily. I can just say CBT, create a family, and give it the name of the table and the column name that I'm going to be creating, which is CL1. And then from there, I can just list the column families by going CBT, LS, and the name of the table, and then that'll tell me all of the column families that are included in that table. Here's where I can do some write and read operations as well. So now I've created some tables, I've created some column families in that table. What do we do now? Well, now I can write values to the temp table to a row called R1 and a family called CF1. So I can say CBT, set my temp table to be R1, that's my row, and send it to CF1. And now I can give it a column value where I can say column family 1, column 1 in this family. I set that equal to test-value1. Do the same thing for the second column. So CBT set temp table, row 1, CF1, colon C1 equals test-value2. And then we've got CBT read temp-table. That's another one. And what we can do is now do the CBT delete table or temp table, which will allow me to delete any information. And here is another command where it allows me to CBT delete instance or quick start my instance. And I can also delete the CBTRC file, which will allow me to remove those files if I want to completely remove it. And that's just the configuration files for my CBT table. And then from there, I can revoke the gcloud CLI credentials by going gcloud auth revoke, and I should be good to go from then on. So that is how we can actually, the commands that we use to create a table, create an instance, create a column family, and then write and read to that table with its row and column families that we're interested in. And then finally, I can actually tear everything down with just a few commands and start from scratch if I have to. And that's a little bit on the gcloud command line interface tool and how we can actually send information through the CLI. In this video, I'm going to show you how we can actually create a big table using the console, the Google Cloud Console, without any command line interface tools. So the first thing I want to do is I want to create a big table instance and select it, just like we were talking about. You have to set the cluster size, set if you're going to use auto scaling, choose an SSD or HDD solution, and then go ahead and do some operation with it. We want to select the tables that we're interested in. And so this is where I want to open the instance in the Google Cloud Console and then click tables in the left pane. That's where I'm going to see that icon. And then I can start entering a table ID for the new table. And so the tables page is going to display a list of tables in the instance. I'm going to go ahead and click a new table and give it a table ID. This is where I can start adding column families if I choose to. I don't have to do that just yet. It could be an empty table. I can add columns either right here or later after the table is created. But a table must have at least one column family before you can even write data to it. So I may as well start adding column families now while I have it in front of me. And so a table will then have at least one column family, and I can start writing to this system. Now, enable table change streams is optional. This is if I'm trying to do some type of change data capture. So make sure that you understand that you'll have increased storage costs and app profile usage requirements. And so you can enable the change stream, or you could not. I leave it off depending on the use case I'm working on. I may turn it on, but then after that, I can go ahead and create the table, and I'll have a table inside of my big table. Now, creating the big table column families using the console. Let's say I can open the list of the big table instances. I can select the table I want to edit from the left-hand side, and then select edit for the table I want to change. And now I can add columns and save the changes to the table, and it's as simple as that. It's all done through the console.
And I can even delete the big tables. Really simple. I can open the list of big table instances, and then I can, if I can delete column families in a table that does not have deletion protection enabled, I can select the table I want to delete, and then I can select edit for the table I want to change. And from then on, I can just select the column I'm interested in deleting, and I can save and confirm the changes. And just like that, that's how it can be done. Just in a few clicks, you can add columns or remove columns. Now, big tables using the console, I can view them by opening the big table instance list. I can select the correct instance I'm interested in, and I can select the table I want to view the information for, and the tables page displays a list of tables in that instance. And then this is where I can click the arrow next to the table ID to expand a list of replications for the table. I can view metrics next to the table name to view monitoring data for the table and see how many writes and reads are coming into it. There's all sorts of monitoring tools that are at this stage, so I can see how the system is performing. And I can even view table information using the console, so I can open the big table instance list and select the correct instance. I can select the table I want to view, and then if you look for this pencil icon to view the table column family names, this table page will display of all of the column family names for that table, and I can edit them. After I'm done editing them, I can close the edit table pane, or I can click cancel. And I can view additional details about the table, including things like table level metrics and all sorts of things like the replication state on the columns. And that's pretty much what we can do to view table information. Now, what I can do is I can even manage big tables using the Google Cloud CLI. And this requires me installing the command line tools using gcloud. I can use gcloud big table instances table and create, which will create a table ID. And I can add things like the instance ID, the project ID, and the column families that I'm interested in creating. And this is a comma-separated list of column family names. I can add more column families later, but these are basically the 4 pieces I need to create the system. And what I'll do here is if I view list of tables, I can go gcloud big table instances, tables list, and then an instance with all the instances IDs. And that'll tell me all of the tables that are attached to this big table instance with that ID. And then I can go ahead and view individual table information names by going gcloud big table instances tables describe, and then give it the name of the table ID and the instance ID, and I can see all sorts of information there. Another thing that I can use the big table command line tools. So this involves me installing some components with gcloud using CBT. So I can say CBT create table with the table ID. I can have CBT create table with the table ID and the families is equal to family name, and then I can give it, some other operations. So this is really all the families that I'm interested in. I can also add column families later by going CBT create family with the name of the table and the column family 1, that's one family name, CBT create family my table, and column family 2 for that. And then if I change my mind, I want to delete column families, it's not create family, it's CBT delete family, and the name of the table and CF2. And then I can list the tables in the instance ID, and I can even view the table information this way. And that's just a little bit on what can be done with the gcloud and CBT command line tools, components that you can install. And you can do all of these commands here, either in the command line interface with the CBT tool or directly in the Google Cloud Console. You will get the same results either way. So use whichever one is more convenient and comfortable for your use case that you're trying to accomplish. In this video, I'm going to show you how we can actually create an instance of our data. So we're going to create a NoSQL big table database and define its schema by adding a few column families and columns into the system. Okay, so what I am going to do is I'm going to first go ahead and go to the Google Cloud Console and search for Big Table. Now, Big Table is the actual service that houses my instance, and underneath the instance, if I click it, you'll see that there is basically a kind of a summarization of what's actually happening to my instance right now. So if you go over to the left side of my BigQuery table, you'll see that little left-hand menu will pop up. And if you hover your cursor over the tables and go ahead and click tables, you will be met with this page. Now, this page is where we're going to list all of our tables. Now, I'm going to use the Google Cloud Act shell. So I've already opened this. You can open it by opening the little square icon, clicking on this icon next to the notifications and Gemini AI chat, and opening this up here. You'll be able to open this and go to Cloud Shell, and here is where you can deal with your Google account. Now, this little black screen is what's basically just a Linux environment, and what we're going to use here is we're going to use this to install the CBT components for gcloud. So we can do so by going gcloud components, install CBT for Cloud Bigtable. I'm going to go ahead and click enter, and it will ask you, depending on the Linux version that you're using, to go ahead and use a different command to install it. So I'm going to use sudo apt get install google-cloud-cli-cbt, and it's going to install this information. Now, I already have it installed, so it's just going to do a check and make sure that it's all up to date. You can see for me, 0 has been upgraded, 0 newly installed, 0 to remove, and 9 upgraded. So everything is good. So I'm going to hit clear. The next thing is, now that I have CBT installed, and I can test it by going CBT and then hitting enter, and you'll see that there's a little help, like a little help page that pops up when I type CBT. And this is good. This means that the Cloud Bigtable tool is installed. So what I can do is now start to authenticate. Now, to authenticate is I'm going to use the vim command to create a file called cbtrc. So .cbtrc is the actual configuration files that I'm going to be using. And it's going to be just a simple key value name separated by equals. So the key here is project. This is my Google Cloud project. Now you can identify what this project is by going back to the Cloud Console, clicking the My Project, whatever your project name is, this little drop-down menu, and you'll see that there's the project ID. We're going to copy this project ID and go back to the Cloud Shell on the other tab, and then click project is equal to and paste your valued BIVAC instance. So this is my name of my project. Yours will be a little bit different. So it's going to be project equals, and your name will be pasted there. Then what I'll do is I will give it the name of my instance. Now, the instance of my cloud instance, my Cloud Bigtable instance, is called example-instance. So I'm going to copy and paste that into my Cloud Shell. And that's exactly what you're seeing right here. Now, when I'm done and I've got these values formatted just like you see on screen, I can quit Vim, and now I should be able to start creating tables. So the first thing I'm going to use is the CBT command to create my tables. So I'm going to go CBT space create table, like so, and then space the name of my table. Now I'm going to call my dash table like this, and it's going to take a couple seconds to create a table, and you'll see that no errors have popped up. So I'll go back to the other tab, and I will click refresh here on the tables page, and you'll see there's my table. It has been created. Now what I can do is I can actually create a column family. So a family of columns is something that I want to reference later down the line. So I'm going to type CBT space create family for column families, like so. And then I'm going to give space the name of my table that I'd like this column family to be on. So it's going to be my dash table, and then space the name of the column family. Now I'm going to call this EMP for employees, and I'm just going to hit enter, and it just takes a moment. Now my table has the employee column names. Now I can actually use the CBT command to add individual rows with their columns, and it's quite simple for me to do. And that's basically the entire schema. Now I've created a table, I've created a column family. The next step now in the next topics, we'll be discussing how to actually add data using the CBT tool to the Google Cloud Console. So in this video, I'm going to show you how we can actually use the CBT tool that's already been configured to install or to insert data into my table that I have created for this instance, example-instance. So as you can see, I already have a table called my-table. It already exists in example-instance. And what I'd like to do in this situation is go ahead and just start inserting some data. Now I have a family name, a column family name already created called EMP for employee. So I'm going to now use the CBT tool to start adding information. So let's say that I have a CBT That's the command line tool. It's already configured. I'm going to go ahead and hit set and give it my dash table, and then hit set and give it a row 1. This is the row identifier. So I could have called it anything, but let's just say I called it row 1 in this case. I'm going to hit space and then give the column family name, which is EMP for employees. This is like an employee table. I'm going to give it a name, which is the name of the column that I want to add to the column family EMP. So this is going to be the employee's name, and I'm going to set it equal to John, something like so. Okay, I'm going to hit enter, and it's there. Now I'm going to go ahead and do the same thing. This time maybe changing, instead of same thing on the row, I have added their name to the same employee column name, employee family name. I'm going to give it a new column. Let's say I've got their name, maybe I've got their position here. So this is going to be a position of manager, something like so. So we hit enter. There we go. So now we've just added some data. So I'm going to give it just 2 columns, name and position. And I'm just going to go ahead and hit CBT, set my dash table. Let's go ahead and add another row, row 2. Let's go employee. Let's give them their name as Jane. And let's hit enter. Again, no errors are coming up. I'm going to do the same command again, CBT, set my dash table, the row identifier, and I'm going to give it the column family name. And this time I'm going to give it a position, and I'm going to set that equal to engineer. Okay, so I'm going to hit enter here. There we go. Now what I'm going to do is I'm going to see if I can read from the table. So reading from the table is quite easy. I've added some data. So let's go ahead, CBT space read my dash table. We'll hit enter. And there we go. You can see here I've got 2 columns of the same name in John there from earlier when I was doing this as an example. But row 2 is now going to have an employee name of Jane, an employee position of engineer. And now every row has their own identifier. So I can go ahead and keep adding rows, editing rows, or deleting rows from this system, all by using CBT as a tool. So that is the whole concept of being able to send information to our Cloud Instance table here. The thing that is a little different here is the fact that we can't use a graphical user interface to send information to this table. We actually have to use either an SDK or the CBT command line tool to be able to programmatically send information to this instance. It's not designed for something user-friendly like the Cloud Firestore, which is a NoSQL data store that can be used with anything, really. You can hop on and see your data and edit your data in the console. This here, you have to use a programmatic way to actually send information to do any basic CRUD operations on our data. And that is how we can use the CBT tool to insert data into the table. In this video, I'll be talking a little bit about billing in different services on Google Cloud for database or data store services, as well as some of the use cases of using each of these services. So let's get started with understanding how Firebase real-time database is built. So what's going to happen is that we are going to be billed based on the number of connections that we have, the number of simultaneous currently open real-time connections. This is a way that we can actually get some type of estimation for our bills. So this will include things like real-time connections, such as WebSockets, long polling, HTML server events, but it doesn't include things like API requests from your REST APIs. But we're also going to be charged based on the amount of storage that we're using, how much data is stored in our database. And this doesn't really include Firebase hosting or data stored through other Firebase products, but it's actually just meant for this real-time database. The total bytes of data that's being downloaded. So all bytes downloaded from our database, including things like our protocol and the encryption overhead, that's going to cost something. And as well, there's going to be a load on the database. And that just gives me an idea of how much CPU I'm using for this system. So looking at things like processing requests over a given 1-minute interval, I can see what's happening here on the performance scale. And then I can figure out, okay, this is how much CPU I'm using in this Firebase real-time and database. So then I'm going to be charged a certain amount based on those 4 factors. Now, when it comes to semi-structured data service prices in Firestore, we're talking about the total documents that we read, write, and delete from. So that's going to affect our cost, the number of index entries that are read to satisfy a query, the storage usage by the database as well as the total network bandwidth used. That's all going to affect it. When we get to Bigtable pricing, we're referring to the instance type and the number of nodes in my instance clusters. That's going to affect the pricing. The storage amount, that's the Bigtable is using. All those tables that I have stored there, they're going to take up some space. That's going to affect the cost. And then, of course, the amount of network bandwidth that I use to move data to and from Bigtable is going to affect the cost as well. Now, when we're talking about the compute prices, we're talking about the cost per node. So if our cluster has 4 or 5 nodes in them, every node is going to cost a certain amount. But there's ways that I can get a cost per node with a 1-year committed use discount, where I can say, hey, I need 3 nodes for this cluster. I'm committed for 1 year, and I'll get a little bit of a discount because I'm paying ahead of time for that system. Another one that I'm doing is a cost per node with a 3-year committed use discount. Again, a little bit longer. If I know that, hey, I only need 3 nodes in this cluster, it's not going to go up or down. Let's go ahead and commit for 3 years, and I'll be able to save some money based on me prepaying. Another thing that I'll see with Bigtable storage prices are the 2 main factors is whether or not I'm using a solid state drive, which I'm charged with a certain amount of gigabytes per month. I'll be charged for that. And hard disk drives storage. Now, HDD storage is slower than our SSDs. SSDs are typically used for more real-time instances. They're much faster to read and write to than a hard disk drive. Now, the thing is that SSDs are faster, but the trade-off is that I'm paying 19 cents per gigabyte per month versus with an HDD, I'm paying 3 cents per gigabyte per month. So there's a 6 times difference between the price between the two. So you have to choose what your use case is and if it makes sense to pay for the SSD storage, or if you can get away with using an HDD storage for that. Let's talk a little bit about use cases when we get to Firestore. What we're using these typical Firestore databases for is real-time collaboration applications, such as applications that require updates and collaboration, like messaging or document editing. I'll use things like for content management systems. So this is where data structures can evolve over time. I can have that there. I can use it for e-commerce platforms that need to manage product listings, customer orders, and inventory. They can leverage this, as well as I can use social networking applications. So it's ideal for social apps where there's going to be user feeds and notifications and interactions that need to be updated in real time. A couple of things that I can use the Firebase real-time databases for are things like our chat application. So this is a good fit for basic chat applications that require real-time messaging, but they have a simpler data structure. You'll sort of see that they're used in live dashboards that need to display live data, such as monitoring systems or analytics dashboards. This is great for the real-time database, low latency updates that we have. So as soon as an update happens in the database, the dashboard can see it immediately. We can see a location tracking applications. This is involving real-time location tracking. A real-time database can efficiently handle and update that location data. And we'll see things like our simple multiplayer games with basic real-time features that used to manage things like player scores or leaderboards or even the game state itself. Bigtable use cases I want to discuss here require things like logging data systems. So data logging systems are used for this. We can look at the parallel architecture, and it allows for rapid processing of petabyte scale data. So this is where we'll use log data for this. We'll have sensor data, for example, from IoT applications, and we'll use things like geographic information for this. And then we've got something known as a reporting system. So it should be noted that things like a wide column databases, they have a much narrower application than traditional SQL databases. So you'll use things like Shopify, for example. They'll use Bigtable as a sink for streaming events, and then they can find a majority of data that can be modeled in a relational fashion there. So this is where we'll use things like our Bigtable, and this is what's actually meant when we're referring to either a real-time database or Bigtable or Firestore. They all cost a little bit different, but they each have their own niche use cases for what we're trying to use them for. In this video, I'm going to see if I can identify some common issues that can arise with Firebase and how we can troubleshoot these things. So troubleshooting Firebase, well, there's a few different pieces in Firebase that allows us to troubleshoot them. One of the things is known as Firebase Crashlytics. This allows us to get clear,
actionable insight into app issues, and it has a great crash reporting solution. And it works for things like our Apple, our Android, our Flutter, our Unity applications that we're building. And it allows us to know when this system is crashing. So it's a lightweight real-time crash reporter. And from there, I can use it to track, prioritize, and fix stability issues that can stop our app quality. It can erode our app quality. And it saves us the troubleshooting time by intelligently grouping our crashes and highlights what caused those crashes to happen. So it's quite useful for this. And you can even determine if a particular crash is impacting a lot of users or if it's not. You can get alerts when an issue suddenly increases in severity. And another one that's great useful is the Firebase Performance Monitoring. Now, the performance monitoring can gain insight into our app's performance issues. It's a service that helps you to gain insight into the performance characteristics of our Apple, Android, and web applications. Okay, so the other thing that we can use is the Firebase Test Lab. This tests our apps on devices hosted in the Google data center. It's a cloud-based applications that testing infrastructure lets us test our app on a range of devices and configurations. We've also have the Firebase Crashlytics features, which are used for organized crash reports. Now, Crashlytics will synthesize all of our crashes into a list of issues that's very manageable. And it gives us contextual information for what caused those crashes. And the great thing is that it will intelligently highlight the severity and the prevalence of crashes so we can actually pinpoint the root cause much faster. Another thing that we have is the Crash Insights. So this is going to be telling me a little bit about helpful tips that highlight common stability problems, and it'll provide resources that makes them easier to things like troubleshoot or triage. And Google Analytics integration, it can capture our app's errors as what's known as an app exception in our analytics table. And the events will simplify debugging, and it gives us access to events that are leading up to each crash. And this is going to allow us to determine what is the root cause of those crashes. Real-time alerting is useful for when we're trying to obtain new issues and regressed issues. And if there's issues actually growing, that might require immediate attention. So we'll get alerts to our team so that we can actually respond to that problem in the software. Now, Crashlytics is actually utilizing some AI insights with AI assistance. So we've got things like our summary and cause. So it's a concise bit of information that helps us determine what happened to the user and what caused the issue. We've got our debugging options powered through Gemini that'll offer a potential few ways to either reproduce the error or provide steps to further debug the issue. And it gives us some next step actions. Now, Gemini is not always going to have all of the context about our issues, but you'll notice that AI assistants in Crashlytics will use the Firebase's tools for knowledge for mobile app development. And it'll also identify what the best practices are. So part of the triage process is really just determining exactly what to do to future-proof our apps so that these types of issues don't recur. And this is where Gemini comes in useful because it's able to look at thousands of pages of Firebase documentation and provide us with possible approaches to resolve the issue so that it doesn't happen again. Now, the Firebase performance monitoring features comes in a few different flavors. It allows us to monitor the key performance metrics, which is great for this. It also allows us to gain some performance insights and optimization steps so that we can improve our applications. So we can look at when we don't know exactly why the app is failing, so it can be quite challenging to determine what's the cause. This is where performance monitoring will see the performance metrics, and we can look at things like the attributes like country, device, app version, and operating system level that allow us to see exactly what's causing those problems. We also have this thing known as custom code tracing. So I can actually instrument custom code traces to capture the app's performance in specific situations. So an example would be when I load a new screen or display a new interactive feature, what happens? Show me the logs after that. And I can create this custom metrics on these custom code traces to count events that I define during those traces. So figure out exactly what's happening in this block of code in this certain situation. And I can even monitor the performance over time. So I can identify significant changes in the performance and resolve some major app performance issues. Things like network outages is something that we can determine quickly from this, and it's vital to the success of the application.
Now, Firebase performance monitoring alert triggers will happen at application start time. So when I configure an alert for app start time, that's where I can get the alerts triggered if the following conditions are true, such as the Firebase recorded at least 100 samples of the app start trace within the last hour, the duration of the app start trace, and there was no alert previously related to the same threshold in the last alert. These are things that allow me to determine when a particular event happens, such as the application starting. We also have things like our custom code traces, like I was discussing before. I can configure an alert for this custom code trace metric, and this allows me to determine if the Firebase recorded at least 100 samples of the custom code trace, for example, within the last hour. So I know that over this custom code trace, this line of code triggered this event, and this is how many that we received in the last hour. If it reaches a certain threshold, alert me. We've also have things like our network requests. So when you configure an alert for a network request metric, the alert is going to be triggered. For example, if I have 100 samples that matched a URL pattern across all versions of our apps in the last hour, that means everyone's making the same network request. That could tell me something, and that's quite useful for that. Screen rendering is another alert that I can get. So when I configure an alert for screen rendering metric, the alert is triggered if, again, I get 100 samples of screen rendering for the latest version of my app in the last hour, meaning that the screen is being drawn all at the same time, so that lets me know. Useful for when I'm looking for things like frozen frames or slow frames, I can identify that with screen rendering. Page loads. So when I configure an alert for a page load metric, this metric is going to alert me when there's 100 samples of the page loading for the app in the last hour. So this is great if I'm looking for things like what's known as the first input delay, which is the aggregated value exceeded the set threshold and the configured percentile of this page being loaded. And this is quite useful for when I'm trying to determine what page is actually being loaded the most on the application and if there's any problems loading that page. So these are just the different performance monitoring alert triggers that I can set up in these 5 basic categories, and they're quite useful for when we're trying to monitor the application. Now, there are some key capabilities that I want to discuss. So this is available for the Android and iOS applications. So this is our test lab features. I can run tests on a wide range of Android and iOS devices, and it's all hosted by Test Lab. And this includes things like virtual Android test devices and iOS test devices. And so performing tests on real devices is quite useful because it allows us to take an actual physical device, such as an iPhone or an Android phone, and I can actually find issues that only occur on specific devices and configurations. And it also integrates with workflow. So workflow integration with the Firebase console, Android Studio, and the G Cloud command line interface. So this is integrated with the 3 systems here, and you can use this even with a continuous integration system so that I can actually do some testing programmatically as part of my continuous integration process, my CI process. So that's a little bit about testing when it comes to Firebase and how we can actually troubleshoot those systems. In this video, I'm going to identify some common issues that can arise with Bigtable and how we can actually troubleshoot them. Let's first understand how the CPU and disk usage works. So when it comes to troubleshooting, it's important that we understand the CPU because whatever tools that we're going to use to monitor the instance, it's essential to monitor that CPU for any type of erroneous processes that could be running on the Bigtable instance. The CPU usage is the CPU usage of our nodes inside of our clusters because they're all using CPU resources to handle things like reads, writes, and even administrative tasks. So what we can do as well is we can also look at the disk usage. Once we understand that each process is also using CPU to either read or write, how we see the disk being used, how often it's being queried, how much space it's taking, that's also going to affect the performance of the system. Now, this Bigtable will deliver highly predictable performance that is linearly scalable. And from here, these 2 systems are going to enable us to identify any performance issues. So if I see a high CPU usage and a high disk usage, that must mean that there's some program somewhere that's actually doing a lot of writes at the same time, and that could lead to a locked state of the table. So that is going to affect our performance. Now, the thing that I'd want to do here is also monitor the Bigtable CPU usage by looking at things like the average CPU utilization. This allows me to look at all nodes in my cluster and see, on average, how much CPU is each node using. This is quite useful for determining if the cluster is exceeding the recommended value for a configuration that I have for more than a few minutes. I can add nodes to the cluster. We have something known as the hottest node, so not all nodes are going to be used equally. In this case, CPU utilization for the busiest node in the cluster, or the hottest node, the metric will continue to be provided over continuity over a certain period of time. But you'll notice that in most cases, you should use the more accurate metric for high granularity CPU utilization. One of the hottest node high granularity CPU utilization is quite useful for this. And this gives us a fine-grained measurement of CPU utilization for the most busiest node in the cluster. So this is quite useful to identify what's going on for the CPU utilization of the hottest node because this metric is more accurate. And then another thing that we can do is we can use something known as this change stream CPU utilization. This is just the average CPU utilization that's caused by this change stream activity across all nodes in the cluster. And we also have things like our app profile method and our table CPU utilization. Now, when it comes to monitoring the big table disk usage, we're looking first and foremost at the physical storage utilization. This is measured in bytes, so the amount of data that's stored in the cluster is what we're interested in. And this value is what's going to affect our costs. And we'll also notice that there's a different type of storage utilization in bytes, but there's also a percentage of storage utilization. This is a percent of the maximum. So the percentage of the cluster storage capacity that is being used. The capacity is based on the number of nodes in our cluster, and any change stream usage is not included for this metric. Physical change stream storage utilization is important for this. Again, this is measured in bytes. The amount of storage that's consumed by a change stream records for tables in our instance. It does not count toward the total storage utilization, but you are charged for change stream storage. It's not included in the calculation of storage utilization that we saw before in the percentage. Disk load, the percentage of your cluster that it's using of the maximum possible bandwidth, specifically for HDD reads. And this is available only for hard disk drive clusters. It's not necessary for SSD systems that you spin up. If you notice that this value is frequently at 100%, what you're going to start to experience is increased latency. And to prevent this, you want to add nodes to the cluster to reduce the disk load's percentage. Here are some more common issues that you'll notice with Bigtable on Google Cloud. You'll notice that there's a data flow cluster issues. Those are a possibility when we're moving data. So when writing to Bigtable from data flow, you should at most use the number of Bigtable nodes you have. So if you have 3 CPUs, multiply that for every Bigtable node that you have. That's how many you're going to use. Otherwise, Bigtable will be overwhelmed and it'll throttle the writes and the reads. So that's just a rule of thumb. Another thing that we want to use is cell compression size. Bigtable doesn't compress our cell values greater than 1 megabyte, so make sure that your cell values are less than that. We also have the Jetty ALPN or NPN, and this has not been properly configured. This means that you just have to check your versions of the gRPC Netty or Netty Handler or the Netty TC native boring SSL static packages and make sure that they are compatible for this system. Another thing that you have is the key structure design. Your row should not contain common parts at the beginning of the key. So doing so would overload specific Bigtable nodes. And if your row is identifiable by a user ID and a date key, you should not use the date and the user ID instead. User ID, comma, date to actually filter. And this is in case of our Bigtable versioning timestamps. So this is just a little bit on key structure in this specific example, but it varies from use case to use case. And so you should be paying attention to how you're going to be keying each row in this Bigtable. A few different performance causes. So causes of slower performance can be because you are read requesting overloading. Means that there's too many read requests coming to the instance that it can't handle, it can't retrieve the information correctly. You'll notice that table schema design flaws. If you're seeing some performance issues, go back to how you've designed each table and look at their schemas. You want to look at the large amounts of data per row issue. You don't want to have your row being too wide with too many columns. Each row should be a certain number of columns to sort of make sure that you're retrieving the data as quickly as possible. So the performance estimates should contain about 1 kilobyte of data per information. A large number of cells is important here. So you are trying to retrieve a lot of cells. The rows in your big table will contain a very large number of cells that just requires more CPU usage to actually retrieve them. For example, if you're storing 1 kilobyte of data, it's much more space efficient to store that data in a single cell rather than spreading the data across multiple cells that each contain 1 byte. If you split your data across more cells than necessary, you're not going to get the best possible performance. So try and keep each cell about 1 kilobyte, store it all in kind of in one location, and then that's going to increase your retrieval times. Another performance cause that I want to talk about is not having enough nodes for a cluster. So a cluster node will provide things like our compute instances. So obviously, if a cluster contains many nodes, if the nodes get overloaded, they all become hot. The disk usage is going to be high. In that situation, what you want to do is just start to add more nodes to that system. Now you can turn on things like auto scaling, and that will start to add automatically the number of nodes to a cluster. You set a minimum number of nodes per cluster and a maximum number of nodes per cluster. And based on the traffic, based on what's happening to your compute, your CPU, or your storage, you can actually, the system will automatically add nodes or remove nodes to reduce cost. So CPU and storage per node issues is important for this. You might want to vertically scale each node if possible, and that's something you have to monitor for this. But the number of nodes was recently scaled, and this is after a number of nodes in a cluster is increased. It takes about 20 minutes under load before you start to see a significant improvement in the cluster's performance. There's a bit of a delay. It's not automatic. So Bigtable will scale the nodes in a cluster based on the load it experiences. And the clusters are using what's known as HDD disk or hard drive disk. In most cases, your cluster should use solid-state drives, which have significantly better performance than hard disk drives. They're great for faster reads and writes. So if latency is an issue for your application, make sure that you're using an SSD system. Some Bigtable performance causes as well. This is now talking a bit about network connection issues. This is a possibility that this could be an issue. So networks can reduce throughput and cause reads and writes to take longer than usual. This happens if your clients are not running in the same zone as our Bigtable clusters. So if your clients run outside of Google Cloud or in a separate zone, that's going to create some networking bottlenecks. You have some outdated client libraries, and if you can determine what those library values should be, what versions you should be using, you can just upgrade and it shouldn't break your code. But really, this should be a process to make sure that you're using the latest versions of the client libraries to match what's in the cloud. We also have replication that it's enabled, but you don't have enough nodes. So in an instance that uses replication for data, each cluster must handle the work of replication in addition to the load it receives from our other applications. If you have under-provisioned clusters that can cause increased latency, you can actually look at these instances' CPU usage to determine exactly what you should do if you have something that's under-provisioned. But really, it's if you have replication enabled and you notice that the system is slogging a little bit, it just means that you may have to add more nodes to the cluster. So that's a little bit about some of the Bigtable performance causes and some common issues that occur. So in this course, we've examined how to design and manage resilient NoSQL databases using Firebase services or Google Cloud Bigtable with a focus on cost control, migration, and availability. We did this by exploring Firebase Mobile NoSQL, Firebase Real-Time Database and Provisioning, Indexed NoSQL with Firestore, data models, creating a Firestore database, and adding data. Cloud Bigtable schema design, provisioning a Bigtable instance, table and creating and defining data storage, loading and querying data in Bigtable, pricing out semi-structured data services, and troubleshooting Firebase and Bigtable. In our next course, we'll move on to explore how to utilize BigQuery and Looker to analyze, share, and optimize data-driven insights effectively.